This in-depth course provides a comprehensive exploration of all critical linear algebra concepts necessary for machine learning. You'll learn the mathematical foundations to excel in AI. Tadev from Lunar Tech developed this course. She has created many popular machine learning courses.
Machine learning is at the forefront of the innovation, powering the most advanced and transformative systems for the companies like Apple, Tesla, Netflix, Amazon, OpenAI, and many others. It enables the creation of the intelligent systems that can predict trends, personalize user experience, and automate complex tasks. To develop these practical applications, a deep understanding of the underlying mechanics is important. This requires a solid grasp of mathematics behind the machine learning, so all these technical details, with a particular focus on linear algebra. This all-encompassing course explores the linear algebra in an interactive and machine learning-focused manner. Welcome to the Linear Algebra for Machine Learning course. You will acquire the critical principles needed to build, optimize, and analyze sophisticated machine learning models. From designing custom algorithms to enhancing current technologies, this course provides the mathematical foundations with vital interests for those for pioneering advancements in machine learning. For those dedicated to mastering the mathematical aspects and the technical details behind machine learning, our extensive 26+ hour course of Fundamentals of Machine Learning within the Mathematics Bootcamp, as well as a separate course, offers an in-depth exploration. This extensive program includes certification and is tailored for individuals that are serious about advancing their career in the field of machine learning and AI engineering. This crash course in mathematics will serve you as a great starting point. By establishing a robust foundation in linear algebra, you will be well prepared to excel as a machine learning practitioner equipped with the mathematical knowledge that drives the innovation and efficiency in this field. So, if you're ready, I'm really excited, and without further ado, let's get started.
Welcome to the course on the Fundamentals of Linear Algebra, presented by Lunar Tech Academy. My name is Date Vaslayan, and today we are going to start with some basic concepts that are important for understanding linear algebra. Linear algebra is one of the most applicable areas of mathematics. It is used by pure mathematicians that you will see in universities doing research, publishing research papers, but also by the mathematically trained scientists of all disciplines. This is really one of those areas in mathematics that you will see time and time again appearing in your professional life if you want to become a job-ready data scientist or you want to do some hands-on machine learning, deep learning, and AI stuff. But also linear algebra is used in cryptology, it is used in cybersecurity, and in many other areas of computer science and artificial intelligence. So, if you want to become this well-rounded professional, you want to go beyond using libraries and you want to truly understand the mathematics and the technical side of these different machine learning algorithms, from very basic ones like linear regression to most complex ones coming from deep learning like architectures in neural network, how the optimization algorithms work, how the gradient descent works, and all these other different methods and models, then you are in the right place. Because you must know linear algebra such that you will understand these different concepts, from very basic ones to most advanced ones in data science, machine learning, deep learning, artificial intelligence, data analytics, but also in many other applied science disciplines. So, before starting this comprehensive course that will give you everything that you need to know about linear algebra, first I'm going to tell you what we assume that you already know. Because linear algebra, it comes from about third year of bachelors of different highly technical studies. And here we are assuming that you already know certain concepts. So to ensure that this course stays really on the topic of linear algebra and that you understand all these concepts really well, for that we need to be able to know different topics. So before we dive into these concepts, let's familiarize ourselves with the basic prerequisites and notations used throughout this course. And you will really need to know this in order to understand these concepts really well, such that instead of memorizing, you will actually just hear me once or maybe twice, and then every time you hear later on, or you see it in the papers or in some algorithms, you will recognize this is something that we already learned. So some key prerequisites overview is here. First of all, to fully grasp the upcoming material, you should be familiar with some basic concepts like real numbers, vector spaces. So you don't need to know this idea of vectors, though you already most likely are familiar with this, given that you know how to plot different lines, you know the idea of x's and y's and how to plot these different graphs. But here we are going to touch base on this. Every time when we come close to these concepts, I will refresh your memory and we will go through these numbers, the idea of norms and distance measures. Because when it comes to the vectors, when it comes to the magnitude and all these different topics that we are going to discuss as part of linear algebra, knowing what norm is and what is the definition of distance, what is the length between 2 points when we plot it in the 2-dimensional space or 3-dimensional space, those are all very basic concepts that usually you see as part of a basic pre-algebra or just common algebra courses and lessons. In order to truly understand what linear algebra is about, to understand this direction of vectors, the angle, and then the dimensionality reduction, how linear algebra is applied, for instance, in different algorithms in machine learning, deep learning, data science, statistics, you really need to understand this Cartesian coordinate system. So this is not only important for linear algebra, but I assume you already know it given that you have passed those other courses like calculus, or usually they are covered as part of pre-algebra or algebra. So the Cartesian coordinate system, I mean here understanding what is, for instance, the common description of them. For instance, when we write like x and then y on the vertical axis, and then we have here 0, and then we can always plot these different plots. You know, we have a clear understanding what is this y is equal to x line. We understand how by knowing certain points we can plot different plots. For instance, that this is the y is equal to x line, that here it means that if we have here 1, then this is just 1, 2, this is 2. So we understand when we have the function of the line and we have a certain value, whether it's our y coordinate or x coordinate, then the corresponding coordinates can be found. Then you also need to know some basic things that I just didn't mention right now. So for instance, that the numbers here can be like 1, 2, 3 up to infinity. So you understand this concept of infinity, and then here the same story. Then here we have -1, -2. And then this is then used later on, and we will be touch basing this when we will be describing our vectors and how we can visualize our vectors in a 2-dimensional space like we have here, because this is 2-dimensional, so we have x and y, but we can also, of course, visualize it in 3-dimensional, etc. So this idea of basic coordinate system is really important, usually covered as part of algebra, if not pre-algebra. Then we have basic trigonometry, which means that you need to have a clear understanding what sinus is, what cosine is, what tangent is, and their reciprocals. And here I mean that you know, for instance, what is cosine function, what is sine function, that you have an understanding, for instance, that what is this line, whether it's a sinus line or cosine line. You have also an understanding what this pi is. One thing that I didn't mention, but it just goes around all these topics, some basic things that you understand what is x, what is y, why we use them, and this idea of variables. And also you need to understand this idea of square, or, a 90-degree angle, and then Pythagorean Theorem. Here we have the same. So what is this relationship between different sides of a triangle that is a very unique triangle, and that has one of the angles as 90 degree, and this idea of, the sides, how this relates to the sinus, cosinus, tangent, cotangent, and also how the Pythagorean theorem applies when we have triangular, but it is no longer with the angle that is 90 degrees. What is the sum of all the angles of triangle? So those are basic stuff that are commonly covered as part of trigonometric lessons or part of general geometry. Then another prerequisite is this understanding of identities and equations in trigonometric lessons, something part of which I already covered. And this just goes around of having a basic understanding of algebra and geometry. Those are super important to understand more advanced techniques from linear algebra. Then we have finally this idea of orthogonality, perpendicularity in vectors. So this also comes from geometry and from trigonometric lessons. So you understand that if we have, for instance, these two lines that don't have any intersections, then we are talking about two orthogonal lines. And otherwise, for instance, if we have two lines like this, then we are talking about perpendicular vectors. Those when you have two lines that are actually parallel, so they don't have any intersection and you won't find any point that is common for the two. So when it comes to this R, so as part of real numbers and vector spaces, R represents the set of all real numbers. So you can be dealing with, for instance, an integers like 1, 2, 3. This will also cover all the negative numbers like -1, -2, -3, but also the floating numbers like 1.223 and all the other numbers that you can think of. Those are the set of all real numbers. So this is in one-dimensional space, right? So you can see that I'm writing just one number, 2, 3, and other numeric numbers. Then we have the idea of R2, R3 up to Rn, where all these numbers, they represent, in this case, the n. It represents the n-dimensional Euclidean space. So when it comes to this idea of n-dimensional numbers, so for instance, R2, here we just mean 2D plane. So I'm pretty sure you are familiar with this idea of, for instance, x-axis and y-axis. Here we are dealing with two-dimensional plane. So for every point that we can find here, we can describe them by assigning them a value x, so coordinate x, and a coordinate y. That's exactly what we mean by saying that the number can be represented in a 2D plane. So here we are dealing with this two-dimensional space. This is our two-dimensional Euclidean space. And every number in here that is part of this R2 can be pictured here, can be represented in this visualization. So for instance, if I have this number, and let's assume that the value on the x-axis is 2, and we can see here that the corresponding y is 0. I can describe this number, which I will call a. I can describe this by writing down first the x coordinate, which is 2, and then the y coordinate, which is 0. So I'm then saying that a, which is a point with x coordinate 2 and y coordinate 0, it is part of my R2. And it's part of my two-dimensional Euclidean space. When it comes to R3, similar thing we can do with that, only in that case we need not just x-axis and y-axis, but we need to add our third dimension. So here, for instance, when it comes to the R3, then we need to do y-axis, we need to have x-axis, but also we need to have some z-axis. So, such that every time, every point in the space, we can then describe by x, y, and z coordinates. So if we write it in terms of the vector, something that we will see very soon as part of our first unit of this course, we will then need to represent every number in this three-dimensional Euclidean space by writing down first the x coordinate, let's say 1, and then y coordinate, let's say another 1, and then z coordinate, which is 1. Or even better, even easier, let's do 0, 0, 0, which means that we are dealing with this initial number, which is the center of this three-dimensional Euclidean space. When it comes to the n-dimensional or the higher dimensional spaces, it's much harder to visualize Therefore, usually when it comes to visualizations, we usually only visualize the one-dimensional, two-dimensional, and three-dimensional spaces. Above then, it just no longer does make sense to visualize it. But we definitely deal with them, and they are part of applied linear algebra. So understanding the spaces is very important for analyzing vectors, for their interactions, and this holds not just for this two-dimensional and three-dimensional, but really for multi-dimensional spaces. Let's now quickly define this idea of norm. So the norm of a vector denoted by this v, which you can see kind of like similar to the absolute value from pre-algebra. You can see here that we have this double straight lines like from absolute value. And then we have the name of the vector or the variable name that we are assigning to our vector. And then you might notice here on the top of this arrow. This basically says that we are dealing not with just a variable, but really we are dealing with a vector. This is really important because you can see that there makes a huge difference if we have, for instance, just v or v1, I have to say, or just v. Those are really important and things that you need to keep in mind when it comes to linear algebra and trying to differentiate vectors from a point. You will notice that when it comes to norm, we can represent it either by this notation or this. Usually it's a common notation in machine learning or in data science with these two bars. And when we do this, we automatically also know that we are dealing with Euclidean distance. We call it also L2 norm. And this is something very common and usually used as part of retrogression, which is an application of linear algebra, and it's used in regularization. So we are regularizing our machine learning algorithms. So when you get into machine learning, you will see time and time again this notation. So next time when you see this, then you know automatically that you are dealing with L2 norm. And L2 norm, which is also used a lot in machine learning, it is referring to the usage of L2 norm in the retrogression. And retrogression or L2 regularization is a very popular regularization technique as part of machine learning. So right now, even you can see this intersection of linear algebra or this idea of norms in machine learning. All right, so now let's see why we call it actually L2 norm or often referred as Euclidean distance. So Euclidean distance, you can see here, which is also in this case, this v, which describes the norm of the vector v, is equal to square root, and then we have all these coordinates, assuming that the vector comes from an n-dimensional space. So you can see here the Rn. The v vector, the Euclidean distance, or the norm of this vector v, is equal to square root, and then v1 squared plus v2 squared plus, and all this in between numbers, plus vn squared. So here basically it means take the square root of v1 squared, then v2 squared, plus v3 squared, blah, 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 plus vn squared. So basically take all the units that form this vector and then, so are on this vector, and use them, square them, and then add them, and then take the square root of that. That's the distance, or I have to say the norm of this vector. So why this is important, this idea of norms and Euclidean distance, beside of being used in machine learning, and why is it used? So norms, they provide a way to measure the size or the length of a vector in vector spaces, which means that when we want to measure a distance, a similarity relationship between, for instance, vectors, then it becomes much easier to use this idea. And Euclidean distance is not only used in regularization techniques like L2 regularization or retrogression, but it's also used in other machine learning or deep learning algorithms as a way to measure the distance or the relationship or the similarity between two different entities. Those can be variables, those can be two people that we want to compare in our algorithm, or two entities. For instance, the norms or the Euclidean distance, they are also used as part of k-means algorithm, something that you might have heard. And if you follow later on the machine learning and the clustering section of machine learning, you will see that Euclidean distance is used as part of k-means algorithm that aims to cluster observations into different groups. So this is also yet another highly applicable topic that you must know in order to understand different linear algebra topics, but also machine learning topics. Let's now talk about simple topic that we must know about and refresh our memory very quickly before moving forward to our next topic that is a prerequisite for this course. So the Cartesian coordinate system is just a fancy word of describing this idea of x and y or x, y, z when we just want to visualize them and showcase these numbers related to the space. So we just learned and I just quickly was talking about this idea of x's and y's and how we can visualize that in a plane. So the Cartesian coordinate system is a framework for specifying points in a plane or a space using ordered list of numbers. So we know, for instance, when we plot this, then here we need to put x and the y in our two-dimensional space, R2. And we know that here in the middle we have 0, and here we have 1, 2, 3, 4, and the same here 1, 2, and then 3, 4. Which means that everyone that is in the industry, whether it's in mathematics, in physics, in data science, or ML or AI, we all universally agree on this system. We know that this is this ordered list of numbers, and we know that if we have, for instance, a point here, then for this point, we know that the x-axis and y-axis is definitely positive, even if we don't know the corresponding numbers. And then once we have more general lines here, so not general but specific lines, then we even know the exact coordinates and values here. And we definitely know that this number should be, so the x-coordinate should be between 2 and 3. So first we have the 2 and then 3, and not the other way around. So this ordered nature helps us to understand how we can put all these different numbers and organize them in our two-dimensional space. And we also know the corresponding y. So we know that, for instance, our y is not -3 because it's lying in here, in this part of our coordinate system, and not somewhere here where the y-axis are negative. And why do we know that? Because it's an ordered list of numbers that we can visualize in this 2D plane. And here you also need to keep in mind, and we need to remind ourselves about this idea of these 4 different parts that we got. So we have the first part, the second part, the third part, and then the fourth, a part of our coordinate system. And here we are dealing with a 2-dimensional plane. But if we were to deal with the 3-dimensional plane, we no longer have just x-axis and y-axis, where x-axis were on the horizontal and y-axis on the vertical, but we have our third line, which is the z. So we have now 3 different dimensions, so x, y, and z, and we are basically extending our 2-dimensional plane to 3-dimensional. So this system is fundamental for visualizing and working with vectors geometrically. So then we can just use this 2-dimensional plane in order to visualize this vector, for instance, knowing what are all these points that appear on this vector. What is its direction? Where is it headed? What is the beginning? And then we can also find out the relationship of these vectors with all the other vectors. For instance, if we have another vector here, then we can use the coordinates of them and information about these vectors to understand that we are dealing with 2 parallel vectors that don't have anything in common, so no intersection points. Versus if we have another vector like this, and we know that here we are dealing with perpendicular, orthogonal vectors. So this is why this Cartesian coordinate system is important, and it's not just important for linear algebra, but just in general for mathematics and for data science and for AI. And you will see this coordinate system time and time again in different visualizations, even when you want to visualize the mean of your data, or you want to visualize the probability distribution function describing your population from statistics or from data science, you want to visualize, for instance, how your optimization is working, or you want to visualize how your model is performing in terms of its evaluation matrix. For all these cases and for any visualizations, this idea of the Cartesian coordinate system is going to become very handy. Let's now talk about this idea of angles and the idea of circles, radian, the pi, as well as this degree sign. So this comes usually from geometry or trigonometry. And this is very important when it comes to the vectors, because when we have two different vectors, then we want to understand their relationship. Do they form this less than 90 degree, or so are we dealing with sharp corner, sharp angle, or we are dealing with 90 degree angle, so we are dealing with this type of vectors where we have 90 degree, or we are dealing with this type of vectors when the angle is 180 degree, which is, by the way, something that we are referring as pi. And here is one thing that is important here is that it's not just pi, but it's pi radians. Why? Because in mathematics, we also have this idea of pi, which is usually a number that is 3.14. So we should not confuse this pi with pi radians. So the relationship between the two is something that we have also seen as part of our pre-algebra and algebra courses. So if it's something that you want to just refresh your memory on, this will be super helpful to check our very initial course on all these basics. So pre-algebra, so this number comes from pre-algebra, and then this idea of p radians, and just in general, all this information about what is 180 degrees, what is this angle, what is 360 degrees, and all the information that comes from trigonometry and geometry can be found in our corresponding course. So the next topic is the unit circle. Unit circle is highly related to this idea of radians, degrees, cosine, sine, but also understanding the Cartesian coordinate system will help you to understand the unit circle. So this also comes from trigonometry and geometry. And it's basically a fancy way of saying we have x-axis, we have y-axis, so we have here 0. So our common Cartesian coordinate system. Only we are trying to focus on this part of the system where we have here 1, we have here 1. So on the x-axis, we have 1, and then here -1, here -1 for y-axis, and here y. The y is equal to 1. So we have here all these points. And then we have the circle with a radius of 1. So here is this, this is the radius. And here we plot the circle. And this will help us to understand these concepts of sinus, cosinus. This theta is just a variable that we use to describe the angle. And for instance, here we are dealing with 45 degrees. This angle is 90 degrees. This entire thing is 360 degrees and half of it, so this part only is 180 degrees. So those are all important part of understanding this idea of unit circle. So you might have already guessed that unit circle refers to this idea that we have here 1 unit, here 1 unit, 1 unit, 1 unit, forming this entire circle. So with the radius that is equal to 1. All right, so this is something that is very easy, and this comes from the geometry and trigonometry. You also need to understand this concept of sinus and cosinus, and how sinus and cosinus are related to this. What do we refer by the sinus and cosine? What is this? What are these points? So 1, 0, for instance, we understand that here the x is equal to 1 and y is equal to 0. So here, this point is simply 1, 0, so this point. And then we have 2p radians. So what is this idea of p? So we know that a p radians, so p radians is simply the 180 degrees, which means that you also need to understand this concept of p2, which is simply the 90 degrees. So you can see here, one thing that I forgot to mention, you need to understand this concept, the relationship between the pi, and so pi radians and this unit circle. You need to know that here, the pi divided to 2 is simply this angle, and then the entire pi is this angle, and then this entire thing, the entire angle with 360 degrees is equal to 2 pi. So 2 pi radians is simply this entire thing. So those are very easy concepts that come from geometry and trigonometry. And if you want to refresh them, then head towards those courses, because this will help you to understand all these concepts from scratch. Let's now continue our refreshment when it comes to trigonometric identities. And we just spoke about this unit circle. We talked about the sinus, cosinus. It's really important to relate this back to a bit more advanced topics coming from the same domain and from the same area of mathematics. And here we need to know this concept before learning linear algebra. A few other things that would be really great if you know, but it's actually not a must to understand all these different topics. It is the idea of Pythagorean identity. So don't confuse this with Pythagoras theorem. This is the Pythagorean identity. So this one, that the square of the sine of an angle plus the cosine squared is equal to 1. And all these different rules that go around the sine and cosine, and also what is, for instance, the sine to theta, which is equal to 2 sine of theta and cosine of theta. Those are all different rules that would be handy to know. And if you are so far, I assume that you also know geometry and fundamentals to trigonometry, which means that you also know these rules. But this might be just a great time to go ahead and quickly refresh your memory on these concepts, because those might become handy in your applied linear algebra and applied mathematics journey. But for now, I would say this is not one of the most important things to know to learn this and to go through this course, but just something to keep in mind. So when it comes to the trigonometric equations, this can become very handy later on when we want to prove something in linear algebra. So to follow along, it's actually a good idea to know, for instance, how you can solve these different equations. And this will go back and refer to the unit circle that we just saw. For instance, if the sinus theta is equal to 1 divided to 2, then you will need to quickly remember what is that angle for which the sinus is equal to 1 divided to 2. Then you realize that is actually the angle where you take the p, and remember that pi is equal to 180 degrees, and that is the one corresponding to, and then pi divided to 6 is simply 180 divided to 6. So this is basically the 30 degree. So those are things that you can do when you know, for instance, all these different sinus and cosinus. So you have memorized for these different angles. So what is the sinus and cosinus for 30 degree, for 60 degree? Let me actually remove this to make it easier. So this type of problems is very easy to solve when we keep in mind and we memorize what are these different values for sinus and cosinus when it comes to different angles. For instance, for the angle equal to 0, let me actually remove this and clean this part for better understanding. So if we have, for instance, 0 degrees, then we know that the sinus for this is 0 and the cosine of this is 1. So we are basically dealing, so if I plot a unit circle, we are dealing with this number. So remember that sinus and cosinus, those refer to the y and the x on our unit circle. So keep this one in mind. So if the cosine theta is then equal to 1 and the sinus, so y is equal to 0, we are dealing automatically with this number. And you can see that here the angle is also 0. So here we are dealing with 1 and 0 coordinate. So this is our cosine of 0 angle, and this is then our sinus of 0 angle. So we automatically, even from this graph, can see very easily that the sine of 0 degrees is equal to 0 and the cosine is equal to 1. All right, so let's quickly also refresh our memory on a few other degrees. So for the 30 degrees, which is simply the pi divided to 6, so this is 30 degrees. Then the sinus or the y-axis is equal to 1 divided to 2. And the cosine or the x-axis value, x-coordinate, is equal to square root of 3, 2. So we are dealing with this corner or angle, so 30 degree. So even from here, you can see that the coordinates make sense. Then we have the pi fourth, another famous value, which is corresponding to the 45 degree. It's simply this angle. And for this angle, the x-axis, which is the cosine, so this number is equal to 1 divided to square root of 2. And then for the sinus, the y-coordinate is equal to 1 divided to square root of 2, as you might have guessed, because in this number, the x-axis and y-axis is the same. So you can see that this distance and this distance is the same because we are dealing with this type of figure. So here we have 45 degree, here we have 45 degrees, so these values are the same. And this is something that you would know knowing the Pythagorean Theorem. So then you can go ahead and refresh your memory for the 60 degrees. So here I'm referring to the pi divided to 3, and then the 90 degrees, which is the very easy case, this one. Obviously, the x-axis is equal to 0, so here you should have 0, and the y-axis is equal to 1, so here you should have 1, and so on. Alright, so we went into quite detailed here, but I think this is a very important topic. Knowing this idea of trigonometric equations, identities, this idea of unit circle are super important because they are highly applicable to different fields in artificial intelligence, data science, machine learning, and will definitely set you apart. Alright, let's now talk about the law of sines and cosines. Those are things that I won't be going on into too much details. I just wanted to quickly showcase to you. If you want to get the proof of those, definitely check out our corresponding courses. But for here, I'm assuming that you already know. So you know the law of sines, which means that if you have this triangle, you have these different sides. So you have an angle A, the corresponding side is A, and then you have angle B, corresponding side is B, and then here C, and the corresponding side is C. Then you know that A divided to sinus of that angle is equal to B divided to the sine of that angle, and then it is equal to C divided to the sine of that angle. So basically take this value, divide it to the sinus of this angle, right in front of it, is equal to taking this value and then dividing into the sinus of this angle. So the proof of this law is outside, so out of the scope of this course, but knowing this will help you to understand different concepts. And then the law of cosine is simply saying, take the side of a target angle. So in our triangular, we have here A, we have here angle B, and then C. And if we go and look into this specific angle, so angle C, just randomly picking one of the three angles, then the side right in front of that angle, so the C squared is equal to, if we take this, the other two sides forming that angle, so A and B, is equal to A squared. So this is just a constant, a distance of this side, A squared plus B squared, so this side squared, minus 2 times A times B times the cosine of that angle. This is what we are referring as the law of cosines. Quite easy, we are not going to prove it again. If you want to get the proofs, make sure to check our other courses on the geometry and trigonometry. We're almost done with the prerequisites, just a quick refreshment. We saw already the norm. Here is just another example what the norm is, and on a specific two-dimensional vector, when we have, for instance, that the vector is equal to 3 and 4, which means for the first dimension, let's say on x-axis we have 3, and then on y-axis is equal to 4, then the norm or the Euclidean distance, so this is equal to, we take the x value, so 3, and then we square it. So v, you can see here, this is the case when n is equal to 2. This is simply equal to square root of v1 squared plus v2 squared, and as v1 is equal to 3, so this is our, maybe I can make this just v1, and this is my v2, then the norm or the Euclidean distance for this vector, so this thing is equal to v1 squared plus v2 squared, which is equal to 3 squared plus 4 squared. And this value is square root of 25, and it's equal to 5. So let's now see the difference between Euclidean distance and the norm. So you can see here the norm. Here we have just one vector, like here, And this norm, it has just two corresponding values into two-dimensional space. You see here, we have just 3 and then 4. So this is V1 and V2. When it comes to the Euclidean distance, this is kind of the generalization of this idea of norm. So the Euclidean distance between 2 points A and B in Rn, so in the n-dimensional space, is the norm of the vector connecting A to B. So we see that the norm and the Euclidean distance are highly related to each other, only we are talking about the norm when it comes to one vector, but when we have this vector A and the vector B, this is simply the Euclidean distance. So for the Euclidean distance, we know already this idea of distance, how we can measure it, and you can see that this comes very similar to what we see here. Notation, and here we are saying, well, we have this vector, and then it has these two coordinates in n is equal to 2 in two-dimensional space. When it comes to the Euclidean distance helps you understand what is this distance between 2 points in an n-dimensional space. So the Euclidean distance between 2 points, let's say A and B, in n-dimensional space is the norm of the vector connecting A to B. So for instance, if we have a point A and we have a point B, we are connecting this, and this is the vector connecting these 2 points, then the Euclidean distance is simply the norm of this vector. So this is the Euclidean distance. So we can see that the norm and the distance, they are highly related to each other. In the Euclidean distance, we are using this idea of norm, and specifically the norm 2, as I mentioned before. So here you can see that the definition of Euclidean distance, so the distance between A and B, those 2 points, is equal to square root of A1 minus B1 squared plus A, and then here we have basically A2 minus B2 squared, and then plus A3 minus B3 squared. Those are things that we cover as part of this ... and then plus up to the last point when we have an minus bn squared. So here what we mean basically is that if we have 2 points, here is A and here is B, and this is our vector, and we know all these different points, so A1, B1, A2, B2, A3, B3, blah, 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 and then here AN, BN. We know all these points lie in here, in this distance. Then we are taking them and using them to calculate the Euclidean distance. So here, for instance, if we have point A and B, so in this example, let's do a quick one. Specific example, when we have a point A, which has coordinates 1 and 2, so this is basically A1, A2, and then point B with points in it like B1, B2, you can notice that the DAB, so the distance or the Euclidean distance of these 2 points, which is equal to the norm of this vector, where here this is A and this is B and this is this vector. This is equal to square root of 4 minus 1. So it takes the B1. So this is B1. And this is A1. Takes the square and then says plus B2 minus A2 squared. Takes the square root of that and says this is equal to 5. Now, you might be wondering, but hey, why do we do then, instead of 1 minus b1 squared, we do b1 minus a1 squared? And the answer to this question lies in the properties that we learn as part of pre-algebra. Because it doesn't matter when we take a1 minus b1 squared or b1 minus a1 squared. Because this squared ensures that it doesn't matter which one we take first and subtract the other. Now, the proof of that is outside of the scope of this course. This is part of pre-algebra, but I just wanted to put this out there to ensure that you are seeing what we are seeing here, because here it says a1 minus b1, but in this example we are taking instead the b1 and we are subtracting a1. This is a common thing that we do in pre-algebra, and just in general in different Euclidean distance or distance-related cases. So I just wanted to put this here to ensure that later on this is something that can be clear from the first view. Right, and in here we will quickly refresh our memory on the Pythagorean theorem, which basically says in the right angle triangle, so if we have this type of triangle, so here we have 90 degrees. This is a right angle triangle. The square of the length of the side opposite to the right angle, so this side, this we often refer as C, and this as B, and then A. Those two are not very important, but this is commonly referred by C. So the side opposite to the right angle. Then we know that the square of the C, so C squared, is equal to A squared plus B squared. This is super important theorem and a fundamental principle for defining the norms, the distances in Euclidean spaces, and in many other applications. So the angles play a crucial role in understanding the direction of the vectors and how they can be measured in degrees or in radians. We saw also the pi radian, this idea of that the pi radian is equal to 180 degrees. Those are all very important when it comes to linear algebra and just in general application of mathematics, in machine learning, in AI, and other applications. The relationships between these angle measurements and the trigonometric functions is foundational in solving different problems that are about these vectors and their orientations. For instance, this angle of sine, cosine, what is this idea of tangent? They are very important. Just to give you an idea, a tangent is specifically used as part of the activation functions. We call it tang activation function. And knowing this tang will help you to understand the activation functions that are used as part of deep learning, which are more advanced machine learning type of models. And they are fundamentals in all these different new and cutting-edge techniques, large language models, transformers, encoder and decoder-based algorithms, etc. They are also important in this idea of computing dot products. So very important and a must-know when it comes to linear algebra. So this is just a simple example when it comes to this right angle triangle and Pythagorean theorem and how it is applied. I will skip this for now. It's also important to understand this idea of orthogonality. So the two vectors, let's say A and B, they are orthogonal to each other if their dot product is 0. So later on, as part of the vectors, when we will talk about dot product, we will see what we mean when we say that the dot product is equal to 0. And here you can even see that if the A vector, so you see here, and B vector, if those vectors, if we multiply them to each other, their dot product is equal to 0, it means they are orthogonal. So this angle that they form is equal to 90 degrees. Orthogonality implies that the vectors from a right angle with each other, they are in, we are dealing with that in R2, in R3, so they are super important when it comes also to visualizing them correctly. This concept is visually represented all this, vector A and then vector B, and they are perpendicular in the 2D coordinate system. All right, so when it comes to the applications of orthogonality plays a crucial role in various aspects of linear algebra. It's fundamental in defining vector spaces, subspaces, in solving systems of linear equation. Later on, when we pass the vector ideas and we go on to the matrices, solving linear systems, so equations with many unknowns, and then we use this idea of reductions or Gaussian reductions, we will see how this idea of orthogonality can be important and how also it relates back to the norm of two vectors. So it's fundamental in defining all these different identities and solving system of linear equations, and also orthogonal vectors are used in finding the shortest distance from a point to the plane, something that is important when it comes to the optimizations. And here you can see an example, the vector A, which is equal to 2, 3, and then vector B, which is equal to -3 and 2. You can see that when we multiply 2 by -3, so we obtain basically the dot product. By the way, this is something that we are going to cover also as part of this course, But for now, you can see that if we take this number, we multiply with this. So 2 times minus 3. We take this number, multiply with this. So we take 3 and multiply with 2. You can see that this is equal to minus 6. This is equal to 6. So minus 6 plus 6 is equal to 0. So you can see that the dot product of these two vectors is simply equal to 0. And this is what we are referring as orthogonality. This means that these two vectors form a right angle, where we see here this angle is equal to 90 degrees. Why these prerequisites matter and why I mentioned those. Understanding this concept is very crucial. They underpin this geometric interpretation of linear algebra. They will help you to better understand these concepts and not just to memorize them, but really understand. And later on, when you go into your machine learning and AI journey and in your data science journey, seeing these concepts will help you to better understand those different algorithms, these optimization techniques, what we mean when we say we want our optimization algorithm to move towards local minimum, global minimum, this idea of movement, this idea of vectors. Later on, you will also understand these different concepts in deep learning, how these models work, how the neural networks work. And those are essential concepts that you need for solving different systems of linear equation, a core part of this course. They also help you in visualizing vectors, spaces, which are critical to understand this concept of linear algebra, the applications of linear algebra when it comes to the real-world applications. So those are things that you can definitely master by following some of our other courses. But for this course, I assume that you are already familiar with these concepts. Right. So now we are ready to actually begin. And with these prerequisites in mind, you are prepared to start your linear algebra journey. We are going to learn everything in the most efficient way, in such a way that you will learn the theory. You are going to see many examples. We are going to learn everything in detail, but at the same time, you're going to learn the must-know concepts, and I'm not going to overwhelm you with these most difficult concepts that you will not be seeing in your career. I'm going to give you this bare minimum when it comes to really knowing and the must-know for linear algebra, such that you will be ready to apply linear algebra in your professional journey, whether you want to get into machine learning, deep learning, artificial intelligence, data science. Knowing these different concepts in linear algebra, you will be a pro in your field. I'm going to give you everything that you need, the theory, examples, implementations, everything in detail, but at the same time, you will be doing that in the most efficient and time-saving way. So without further ado, let's get started. Let's now quickly define this idea of norm. So the norm of a vector denoted by this v, which you can see kind of like similar to the absolute value from pre-algebra. You can see here that we have this double straight lines like from absolute value. And then we have the name of the vector or the variable name that we are assigning to our vector. And then you might notice here on the top of this arrow. This basically says that we are dealing not with just a variable, but really we are dealing with a vector. This is really important because you can see that there makes a huge difference if we have, for instance, just v or v1, I have to say, or just v. Those are really important and things that you need to keep in mind when it comes to linear algebra and trying to differentiate vectors from a point. You will notice that when it comes to norm, we can represent it either by this notation or this. Usually it's a common notation in machine learning or in data science with these two bars. And when we do this, we automatically also know L2 norm. And this is something very common and usually used as part of retrogression, which is an application of linear algebra, and it's used in regularization. So we are regularizing our machine learning algorithms. So when you get into machine learning, you will see time and time again this notation. So next time when you see this, then you know automatically that you are dealing with L2 norm. And L2 norm, which is also used a lot in machine learning, it is referring to the usage of L2 norm to in the ridge regression. And ridge regression or L2 regularization is a very popular regularization technique as part of machine learning. So right now, even you can see this intersection of linear algebra or this idea of norms in machine learning. The norm of this vector v is equal to square root and then v1 squared plus v2 squared plus and all this in between numbers plus vn squared. So here basically it means take the square root of v1 squared, then v2 squared plus v3 squared, blah blah blah, plus vn squared. So basically take all the units that form this vector and then are on this vector and use them, square them, and then add them, and then take the square root of that. That's the distance, or I have to say the norm of this vector. We saw already the norm. Here is just another example what the norm is, and on a specific two-dimensional vector, when we have, for instance, that the vector is equal to 3 and 4, which means for the first dimension, let's say on x-axis we have 3, and then on y-axis is equal to 4, then the norm or the Euclidean distance, so this is equal to, we take the x value, so 3, and then we square it. So v, you can see here, this is the case when n is equal to 2. This is simply equal to square root of v1 squared plus v2 squared, and as v1 is equal to 3, so this is our, maybe I can make this just v1, and this is my v2, then the norm or the Euclidean distance for this vector, so this thing is equal to v1 squared plus v2 squared, which is equal to 3 squared plus 4 squared. And this value is square root of 25, and it's equal to 5. So let's now see the difference between Euclidean distance and the norm. So you can see here the norm. Here we have just one vector, like here. And this norm, it has just two corresponding values in the two-dimensional space. You see here we have just 3 and then 4. So this is v1 and v2. When it comes to the Euclidean distance, this is kind of the generalization of this idea of norm. So the Euclidean distance between 2 points A and B in Rn, so in the n-dimensional space, is the norm of the vector connecting A to B. So we see that the norm and the Euclidean distance are highly related to each other, only we are talking about the norm when it comes to one vector, but when we have this vector A and the vector B, this is simply the Euclidean distance. So for the Euclidean distance, we know already this idea of distance, how we can measure it, and you can see that this comes very similar to what we see here. Notation, and here we are saying, well, we have this vector, and then it has these two coordinates in n is equal to 2 in two-dimensional space. When it comes to the Euclidean distance helps you understand what is this distance between 2 points in an n-dimensional space. So the Euclidean distance between 2 points, let's say A and B, in n-dimensional space is the norm of the vector connecting A to B. So for instance, if we have a point A and we have a point B, we are connecting this, and this is the vector connecting these 2 points, then the Euclidean distance is simply the norm of this vector. So this is the Euclidean distance. So we can see that the norm and the distance, they are highly related to each other. In the Euclidean distance, we are using this idea of norm, and specifically the norm 2, as I mentioned before. So here you can see that the definition of Euclidean distance, so the distance between A and B, those 2 points, is equal to square root of A1 minus B1 squared plus A, and then here we have basically A2 minus B2 squared, and then plus A3 minus B3 squared. Those are things that we cover as part of this ... and then plus up to the last point when we have AN minus BN squared. So here what we mean basically is that if we have 2 points, here is A and here is B, and this is our vector, and we know all these different points, so A1, B1, A2, B2, A3, B3, blah, 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 and then here AN, BN. We know all these points lie in here, in this distance. Then we are taking them and using them to calculate the Euclidean distance. So here, for instance, if we have point A and B, so in this example, let's do a quick one, specific example when we have a point A which has coordinates 1 and 2. So this is basically A1, A2, and then point B with points in it like B1, B2. You can notice that the DAB, so the distance or the Euclidean distance of these 2 points, which is equal to the norm of this vector, or here this is A and this is B and this is this vector. This is equal to square root of 4 minus 1, so it takes the B1, so this is B1, and this is A1, takes the square, and then says plus B2 minus A2 squared, takes the square root of that and says this is equal to 5. Now you might be wondering, but hey, why do we do then instead of 1 minus B1 squared, we do B1 minus A1 squared? And the answer to this question lies in the properties that we learn as part of pre-algebra. Because it doesn't matter when we take A1 minus B1 squared or B1 minus A1 squared. Because this squared ensures that it doesn't matter which one we take first and subtract the other. Now the proof of that is outside of the scope of this course. This is part of pre-algebra, but I just wanted to put this out there to ensure that you are seeing what we are seeing here, because here it says A1 minus B1, but in this example we are taking instead the B1 and we are subtracting A1. This is a common thing that we do in pre-algebra and just in general in different Euclidean distance or distance related cases. So I just wanted to put this here to ensure that later on this is something that can be clear from the first view. So why this is important, this idea of norms and Euclidean distance, beside of being used in machine learning, and why is it used? So norms, they provide a way to measure the size or the length of a vector in vector spaces, which means that when we want to measure a distance, a similarity, a relationship between, for instance, vectors, then it becomes much easier to use this idea. And Euclidean distance is not only used in regularization techniques like L2 regularization or ridge regression, but it's also used in other machine learning or deep learning algorithms as a way to measure the distance or the relationship or the similarity between two different entities. Those can be variables, those can be two people that we want to compare in our algorithm, or two entities. For instance, the norms or the Euclidean distance, they are also used as part of k-means algorithm, something that you might have heard. And if you follow later on the machine learning and the clustering section of machine learning, you will see that Euclidean distance is used as part of k-means algorithm that aims to cluster observations into different groups. So this is also yet another highly applicable topic that you must know in order to understand different linear algebra topics, but also machine learning topics. Welcome to the course on the fundamentals of linear algebra. My name is Date Vaslayan, and today we are going to start with some basic concepts that are important for understanding linear algebra. Linear algebra is one of the most applicable areas of mathematics. It is used by pure mathematicians that you will see in universities doing research, publishing research papers, but also by the mathematically trained scientists of all disciplines. This is really one of those areas in mathematics that you will see time and time again appearing in your professional life if you want to become a job-ready data scientist, or you want to do some hands-on machine learning, deep learning, and AI stuff. But also linear algebra is used in cryptology, it is used in cybersecurity, and in many other areas of computer science and artificial intelligence. So if you want to become this well-rounded professional, you want to go beyond using libraries, and you want to truly understand the mathematics and the technical side of these different machine learning algorithms, from very basic ones like linear regression to most complex ones coming from deep learning like architectures in neural network, how the optimization algorithms work, how the gradient descent works, and all these other different methods and models, then you are in the right place. Because you must know linear algebra such that you will understand these different concepts, from very basic ones to most advanced ones in data science, machine learning, deep learning, artificial intelligence, data analytics, but also in many other applied science disciplines. So before starting this comprehensive course that will give you everything that you need to know about linear algebra, first I'm going to tell you what we assume that you already know. Because linear algebra, it comes from about third year of bachelor's of different highly technical studies. And here we are assuming that you already know certain concepts. So to ensure that this course stays really on the topic of linear algebra and that you understand all these concepts really well, for that we need to be able to know different topics. So before we dive into these concepts, let's familiarize ourselves with the basic prerequisites and notations used throughout this course. And you will really need to know this in order to understand these concepts really well, such that instead of memorizing, you will actually just hear me once or maybe twice, and then every time you hear later on, or you see it in the papers or in some algorithms, you will recognize, this is something that we already learned. So some key prerequisites overview is here. First of all, to fully grasp the upcoming material, you should be familiar with some basic concepts like real numbers, vector spaces. So you don't need to know this idea of vectors, though you already most likely are familiar with this, given that you know how to plot different lines, you know the idea of x's and y's and how to plot these different graphs. But here we are going to touch base on this every time when we come close to these concepts. I will refresh your memory and we will go through these numbers, the idea of norms and distance measures. Because when it comes to the vectors, when it comes to the magnitude and all these different topics that we are going to discuss as part of linear algebra, knowing what norm is and what is the definition of distance, what is the length between 2 points when we plot it in the 2-dimensional space or 3-dimensional space, those are all very basic concepts that usually you see as part of a basic pre-algebra or just common algebra courses and lessons. In order to truly understand what linear algebra is about, to understand this direction of vectors, the angle, and then the dimensionality reduction, how linear algebra is applied, for instance, in different algorithms in machine learning, deep learning, data science, statistics, you really need to understand this Cartesian coordinate system. So this is not only important for linear algebra, but I assume you already know it, given that you have passed those other courses like calculus, or usually they are covered as part of pre-algebra or algebra. So the Cartesian coordinate system, I mean here understanding what is, for instance, the common description of them. For instance, when we write like x and then y on the vertical axis, and then we have here 0, and then we can always plot these different plots. You know, we have a clear understanding what is this y is equal to x line. We understand how by knowing certain points we can plot different plots. For instance, that this is the y is equal to x line, that here it means that if we have here 1, then this is just 1, 2, this is 2. So we understand when we have the function of the line and we have a certain value, whether it's our y coordinate or x coordinate, then the corresponding coordinates can be found. Then you also need to know some basic things that I just didn't mention right now. So for instance, that the numbers here can be like 1, 2, 3 up to infinity. So you understand this concept of infinity, and then here the same story. Then here we have -1, -2. And then this is then used later on, and we will be touch basing this when we will be describing our vectors and how we can visualize our vectors in a 2-dimensional space like we have here, because this is 2-dimensional, so we have x and y. but we can also, of course, visualize it in three-dimensional, etc. So this idea of basic coordinate system is really important, usually covered as part of algebra, if not pre-algebra. Then we have basic trigonometry, which means that you need to have a clear understanding what sinus is, what cosine is, what tangent is, and their reciprocals. And here I mean that you know, for instance, what is cosine function, what is sine function. You know that you have an understanding, for instance, that what is this line, you know, whether it's a sinus line or cosine line. You have also an understanding what this pi is. One thing that I didn't mention, but it just goes around all these topics, some basic things that you understand what is x, what is y, why we use them, and this idea of variables. And also you need to understand this idea of square or, you know, a 90-degree angle, and then Pythagorean Theorem. Here we have the same. So what is this relationship between different sides of a triangle that is a very unique triangle, and that has one of the angles as 90-degree, and this idea of you know, the sides, how this relates to the sinus, cosinus, tangent, cotangent, and also how the Pythagorean theorem applies when we have a triangular, but it is no longer with an angle that is 90-degree. What is the sum of all the angles of triangle? So those are basic stuff that are commonly covered as part of trigonometric lessons or part of general geometry. Then another prerequisite is this understanding of identities and equations in trigonometric lessons, something part of which I already covered. And this just goes around of having a basic understanding of algebra and geometry. Those are super important to understand more advanced techniques from linear algebra. Then we have finally this idea of orthogonality, perpendicularity in vectors. For instance, if we have two lines like this, then we are talking about perpendicular vectors. Those when you have two lines that are actually parallel, so they don't have any intersection, and you won't find any point that is common for the two. Hi there. So let's get started with our first module, which is Foundations of Vectors. In this module, we are going to talk about fundamentals of linear algebra, vectors. We are going to make a differentiation between scalars and vectors. We are going to define them. So first we will learn the theory, then we will implement them into practice by plotting them, by looking into different examples. Then we will look into this representation of vectors by looking into the magnitude and the direction of it and the representation of them just in general. We are going to plot them in our coordinate system. Then we are going to see the common notation of vectors and the indexing of them. Vectors are super important when it comes to linear algebra and application of it, and they matter not only in mathematics but beyond. So vectors help us in many ways, from figuring out how objects move to solving math problems in science and just in general in technology, including in data science, machine learning, artificial intelligence, etc. They are super useful tools. So let's start our journey with looking into scalars. So scalars, they are just plain numbers. And by definition, a scalar is a single numeric value, often representing magnitude or quantity. For example, scalars can be describing the temperature outside. For instance, the temperature of 22 degrees can be represented by a scalar, or a height of a person can be represented, it's a scalar. So let's assume we have a scalar that we will define by a letter s. It's just a variable. This scalar is then equal to 22, for instance, and we are measuring it in degrees. So it means that if this s measures room temperature, then the scalar s, which is equal to 22 degrees, it represents the room temperature. It can be, for instance, 18 degrees or 9 degrees if it's very cold. it just measures a single value. It represents just a single number. Or it can be, for instance, 17, 100, 2.22. So all this, they are just scalars. They represent a single numeric value. They often represent a magnitude or a quantity. Very soon we will see that scalars, they are a value that represent the magnitude of a vector. So now when we are clear on this very basic concept of scalars, let's actually move to this idea of vectors. So by definition, a vector is an ordered array of numbers which can represent both magnitude and direction in space. So vectors, they are a bit more. They represent a bit more than scalars. They are numbers that also show direction, like a car speeding down the highway or a ball being thrown. For instance, when it comes to our previous example where we were using this room temperature as a way to think about the scalar, a scalar, for instance, scalar that we just saw was this room temperature, which was 22 degrees. When it comes to the vector is different. For vector, for instance, we can have an example when a bird, for instance, it flies at 10 kilometers per hour. And I also add here another information which will make this as a vector, which is that it flies south. So here, as you can see, what I'm doing is that I'm not just, well, let me actually remove this part to make it easier to understand. Okay, so in this example, let me write it down that the example bird flies south at 10 kilometers per hour. So you can see that I'm not just adding a scalar, which is in this case the magnitude. We will see very soon the formal definition of it. So I'm writing down the speed, I'm defining the speed, but also the direction. So I'm saying I know that the bird is flying south, that's the direction, and I know also the speed of it, which is the magnitude, so 10 kilometers per hour. So here, in the vector, I have much more information than in the scalar, because in the scalar, I just got temperature, room temperature, single value, but in case of a vector, I not only have magnitude or speed, like 10 kilometers per hour, but I have extra information, which is the direction of it. For instance, flying to the south. So let's now look into some real examples and plotting them to make more sense out of this idea of vectors and what is this magnitude, what is the direction. So let's assume we have a 2D plane. So we have x-axis, we have y-axis. Here, like usual, we have our 0, 0 center. And we want to plot a simple vector. So usually the way we represent vector in tutorials or just writing down is by writing the name of the vector. This can be just a random name. And let's assume that it's a V, letter V. And then on the top, we are always adding this arrow. So this arrow, it says, and it tells the person who is reading that we are dealing with the vector. Arrow on the top is that reference. So let's assume this vector V, it starts from the center of our coordinate system and it goes to this point. So let's say in here, this is our vector V. So let's assume that this point in here is equal to 4, which means that the x-coordinate is 4 and the y-coordinate is 0. As the arrow, it just, as the point in here, it has a y value of 0. So you can see that it goes straight from 0 to this one, to this point. Okay, so what tells this vector to us is that we have a value that describes the length of the vector. So it goes from 0 to 4, which means that the length is equal to unit 4. so it's equal to 4. And we have just learned, and we were just talking about that the magnitude is the length in this case. So the length describes the magnitude in this case. So this means that the magnitude of this vector is equal to 4. And then what else we can see here? We can see the direction of the vector, which means that the direction is also something that we can see here. This is the direction of the vector. So this, going straight from this point to this point in a horizontal way. So independent whether I plot this vector from 0 to 4 in here, or in here, or in here, or in here, or in here, in all cases, as long as the length is this, I'm dealing with the same vector, because I am basically in this entire R2 space, I have exactly the same vector. All I care is about the magnitude and the direction. Where will this vector start and where will it end? I am not interested. I'm interested that the magnitude, in this case the length, is equal to the direction of the vector. So let's now look into another example where we go a bit more difficult on our coordinates and on our vector. We already saw that we had this vector where we went, let me change the color. So this was our vector v, and it went from 0 till 4. So this point, to be more specific, is, so this vector, it goes, the vector v, it goes from 0, 0 to 4, 0. So the coordinate x was 4 and the y was 0. Now let's plot another one where the direction is no longer horizontal for this vector. Let's call it vector w. And for this vector w, we will again start with 0, 0. So we will start again in here. But this time, we will go a bit like this. So let's say we go all the way to this point. So this point has a value for in x-axis of 3. And for y-axis, it has a value of 4, which means it goes from this point to this point. And this is the direction of our vector v. So it goes 2, 3, 4, because this point is 3, 0, and this point is 0, 4. So x-axis is 0, x-coordinate, and y-coordinate is 4. So now you can see that the direction of this vector is like this, while the direction of the vector v was like this. And like in case of vector v, I again no longer care about where exactly my vector w starts and ends, but all I care is about its magnitude, so the length and the direction. So for instance, I can have the same vector in here, the same vector in here. As long as the length, the magnitude is the same and the direction, I am dealing with the same vector. That's all I care. So the magnitude and the direction is all that you care about. All right, so now about the length. That's something that you can see very easily from this specific example, because by using the Pythagorean Theorem or Pythagorean Theorem, we can see very quickly that as the length of this side of our right angle 30 degree, so right triangle, we can see that this side is 3, this side is 4, which means that this side is 5, because 4 squared plus 3 squared, then we take the square root of that, is square root of 25, and it's equal to 5. So the length or the magnitude of this vector v is simply equal to 5. All right, this was about this specific vectors. Let's now look into the common representation of the vectors. So we always use the magnitude as well as the direction in order to represent the vectors, and they commonly are represented by two different ways. Let's now look into the first way that the vectors can be represented, and then we will move on to the next one. So when it comes to the vector v, so we saw that vector v was moving from point 0, 0 till to the point of 4, 0. So we can represent the vector b by 4 and 0. When it comes to the vector w, we can represent that vector. So vector w, we can again do the parentheses, and we can say that it's equal to 3, 4. So by using the coordinates from the coordinate system, we can then represent our vectors. So this is just one way of representing a vector. Another way of representing these vectors is by using these square braces. Given that we are in the two-dimensional space, first we will mention here the 4, then we will mention the 0. In here 2, so we can say 3 and 4. This is yet another way of representing the vectors in a two-dimensional space. So if we were to have a three-dimensional space, so let me actually show it on a new page. So if we were to have vectors in three-dimensional space, so we are dealing with R3, so we have points that can be described by x, y, and z. So coordinate space like this, so x and then y and then the z, then every point, so let's say we have this vector, then we had to represent it by a value, let's say x1, y1, and z1. Or better, let me actually use a different letters, a, b, and c. And this would be my vector v. And I could also represent this vector v, it's the same, so vector v can be represented as a, b, and c. So one thing that you can notice is that unlike the R2, now I have 3 different entries, what we are also referring as rows. And we just got 1 column. So we can often represent, and usually that's a common way of representing vectors, by using these columns. So columns help us to represent our vectors. And you can see very clearly then when it comes to the two-dimensional space, so when we have R2, so then our vectors have just 2 rows. So 3 and 4, 4, 0 like in here. When it comes to three-dimensional space, we have 3 entries, and so on. So the same holds, of course, also for instance, R5. Then for R5, our vectors, so coordinate space can be, for instance, x, y, z, and then gamma, and then let's say delta. And then the coordinates of a vector in that space can be v, and then arrow is equal to, and then we would have, let's say, a, b, c, d, e. You get the idea. So depending on the space, the coordinate space, and the dimension of that space, then the corresponding vectors can be represented accordingly. So the vectors are quantities that have both magnitude and direction, as we just saw, distinguishing them from scalars, which only have magnitude. So we saw that the scalars got only magnitude, while in case of vectors, we saw both for the vector v and for the vector w, we didn't only have the magnitude, so the length of the vector, but also the corresponding direction. So when it comes to the vectors, so this is exactly what we just saw in our example, a vector in a two-dimensional space, so in R2, can be represented by using these square braces and the corresponding entries for x and y, where x is basically the x coordinate in our coordinate system. So in our x and y system, whenever you have this x and y coordinate, then this x coordinate will then describe your magnitude, and the y coordinate will then describe your second entry that you need to put when representing your vectors. So here the x and y indicate the movement in the horizontal and in the vertical dimensions respectively. So for the x's, it's always the x coordinate, so how far you move towards the horizontal direction in here, or independent in here. So always take the x coordinate, that is the value that you need to put first, and then the y need to be put it in here. So indexing in vectors. When it comes to the indexing, the standard mathematical notation, indices in the n vectors goes from I is equal to 1 to I is equal to n. So the notation here can be a bit ambiguous. So AI could mean the ith element of AI, the A vector, or the ith vector in a collection. So let's start with a simple one and then move on to this next part. So what this means and what this means we will look into now. So usually when we have a n-dimensional space, we are having a hard time visualizing it. Therefore, we use this two-dimensional space or maximum three-dimensional space in order to get an understanding of what these vectors are. So we just saw examples of them when creating our vectors in V and W in R2 and also in R3. But we can have similar vectors also in R4, in R5, or all the way down to Rn, where n can be 100, 200, 500, any number as large as you want. The thing is that visualizing R4, R5, Rn is very hard, but we can still benefit from these great properties of the vectors, matrices, and in general linear algebra in order to describe different things that have more than 3 dimensions. Therefore, we have this bit more ambiguous notation where we use Rn, and this n can be any real number and it can be all the way to infinity, so very large number. And let's say we have a vector in this Rn, then this vector is usually described by using similar square brackets like before, only with more entries. So like before, we got just one column, so that's something that we didn't change. But here we have, instead of just 2 entries or 3 entries like in the 2-dimensional or 3-dimensional spaces, now we have A1, A2, A3, all the way down to AN-1 and AN. So we got in total n elements in our column, and this describes our single vector. So this vector in an n-dimensional space. This we can call also A. So one thing that we just saw is that it was saying in our definition and notation that we might also be dealing with the ith vector in a collection, which means that sometimes you will see this, while here the A1, A2, they are vector themselves. So here we saw that these are just entries. So A1 is a number, A2 is a number, A3 is a number, AN is just a number. But it's also possible when you have a much more difficult and complicated case that you got an A, let's write it down with a capital letter A, which is equal to A1, or let's actually remove this. So we got, let's say A1, A2, A3, all the way down to AN-1 and AN, where you can already see what is going on. So instead of having just a number as an entries, instead we have vectors in here. So our first element is actually vector, our second element is actually vector, so A2 arrow, A3 arrow, all the way down to AN arrow. So while here, this can be, for instance, some numbers, let's say 1, 1, 1, all the way down to 1, 1. Here, we have a vector, vector, another vector, and all the way down here, yet another vector. Where, for instance, when we remove this part, where, for instance, A1 arrow is actually equal to A11, A12, A13, all the way down to A1n. One thing that you will notice here is that, unlike in here I got double indices. So I got here A11, and then A12, and then A13, all the way to A1n. So the first index, it doesn't change, as I have here a 1. So I'm writing down the index corresponding to this vector, but the second index, it changes per entry, indicating which element specifically in the vector I'm talking about. So from the first index, you can identify the vector that I'm referring to, which is A1, and from the second index, you can see the corresponding entry or the value that element is positioned in this vector. So you can see that this value is, for instance, in the vector 1, so A1 to be more specific, but then it is in the first position, this is in the second position, in the third position, all the way down to the end position. So this is something that is really important to understand well, because this notation is going to appear time and time again across various applications of matrices and vectors. So it is really important to understand well. Therefore, I want to go one more time through this to make sure that we are clear on what these indices represent. So whenever we have an index, a vector that we want to represent, and it is just a vector, which means that it's not a nested vector in a vector, then we can define it by, let's say, A, and then on the top an array, and it's equal to, and here we can have A1, A2, all the way down to AN. So you can see what we are also referring as dimension of this vector is equal to n by 1. So I got n entries and just one column. So n by 1. Which means that this already gives me an indication that most likely this A1 is a number, this A2 is a number, this AN is a number. So let's say this is equal to 1, 2, 3, blah, blah, blah. And then here I have, let's say, 100. But if I'm dealing with a nested vector, later on we will see that this can be represented by a matrix. Then I can also define this by capital letter A, which is a common way to refer to either matrices or nested vectors. And then this is equal to A1 arrow, A2 arrow, A3 arrow. This already sends a message to the reader that we are dealing with no longer a constant within a vector, but rather vectors in a vector. And what can we see here is that the dimension of this nested vector, or which we can also refer to as a matrix, here the number of rows, so the number of entries, these elements, we can see it's equal to n. But then this time, the number of values that form these vectors is no longer 1, because we are not dealing with just a constant. This is not some constant, but rather this is yet another vector. So let's assume this vector has a length of m. So let's say this has a length of m. Then the dimension of this matrix A is equal to m. So something that we will see also when talking about matrices. So let me actually clarify this bit more. For better understanding, let's say we look into one of those, one other example of an entry. So let's say we look into this specific vector, which is in the third vector within this vector capital A. So this A3 vector. So one thing to see here already is that I assumed that these vectors, they got m elements. And keep in mind that all these vectors, they should be of the same size. So it means that I already know that this specific vector A3 has m elements. So m elements. So I'm representing this A3 vector from here. I'm taking this out from this entire nested A vector, and I just want to represent this. And now, unlike these elements that got an arrow on the top, this time I will have constants forming the A3 vector. So I no longer have vectors, but I have elements in it. So in here I will have A, let me actually write down all the A's. But to refer and to make sure that I recognize that I'm dealing with the third A vector, so A3 arrow, here I will put 3, all the way here 3. So they all come from the same third A3 vector, but then their positions is different because this is, let's say, 1, 2, and then all the way down to mth position. So these indices help us to keep track what are the position that these values are taking part in the vector A3 arrow. This might seem a bit complicated at the moment, but once we move on to a bit more complex material like matrices, it will make much more sense. This is a bit of an extra. I just wanted to showcase this, but this is what is at its core and what you need to understand at the moment. To understand this concept of vectors, so you need to know that vectors can be represented by this arrow on the top. So let's say vector A, and it has, let's say, n elements, then you can write these square brackets, and then you will need to mention A1, A2, all the way to AN, which means that you have n different entries describing your vector. So you have A1, which is the first element in your vector, A2, the second element, all the way to AN, which is the end element. Where here you can see, for instance, so if I add here A3, that A1 is simply equal to 1, A2 is equal to 2, A3 is equal to 3, all the way to AN is equal to 100. So these numbers I'm basically taking and I'm representing them and putting them in here within square braces in order to get a representation of my vector. So my vector A has all these different entries, n different entries, and it starts with 1 and it ends with 100. This is a vector. And then when it comes to the vectors within vectors, here we need to be a bit more careful because here we not just have constant values forming a vector, but we have vectors that form yet another vector. So our vector A, our nested vector A, which we later will refer as matrix A, has actually entries that also are vectors. So we have A1 vector, A2 vector, A3 vector. They are not just constants, but on their own they are vectors. So here, for instance, we have defined also an example of it. We have said, let's look into this third specific vector that is part of A, which is A3 vector. And that one has m different elements. Here we have then the index referring to the which vector from the nested vector A it is, which is the third one, because we have taken it from here. But then on its own, this vector has different members, m different members to be more specific. Therefore, we have also an index to keep track of the position of this value, 1 to up to m. And this can be yet another, this time it can contain some elements, an example of which is, for instance, 0, 1, 2, all the way to, let's say, 500. And this can be different numbers. It doesn't need to be ordered. It doesn't need to have a specific pattern. They can be just random numbers describing this A3 vector. So hopefully this makes sense. If it doesn't, don't worry, because we are going to see this time and time again. I just wanted to give you a brief of an intro such that you can remember this when we come back to a bit more complex topics like indexing in matrices. So now let's talk about special vectors and operations. Here we are going to talk about zero vectors, unit vectors, the concept of sparsity in vectors, as well as vectors in higher dimensions like we just saw about this n-dimensional space. We will also talk about different operations we can apply when it comes to vectors like addition, subtraction, and then later on in the next module, we will also talk about multiplication. We will also be looking into the properties of vector addition after we have looked into some detailed examples when it comes to operations on vectors. All right, so let's start with the zero vectors and unit vectors. When it comes to the zero vectors, you can see here already that the 0 and arrow on the top, it basically refers to the vector like we saw before, only with the difference that all its members are 0. So you can see here that we have 0 and then an arrow, and then underneath here we have some number 3, And then this is described by this common representation with the square braces and then 3 different members, 0, 0, 0, so all 0. And then it says in R3. Okay, so why are we doing this? Well, when it comes to different linear algebra operations, sometimes we just need to add 0 vectors, or we just want to create 0 vectors. It's just easier to work with. We want to just create an empty vector. We know the length, but we want to keep it empty such that later on we can add something on the top. Or knowing that when we add a 0 on a number, the number stays the same, we can make use of this property to do different tricks when it comes to programming in Python, in Scala, or in C++, etc. So therefore, this idea of 0 vectors can become very handy. Now, one thing that you need to notice here is that we are not just writing down this 0 to emphasize we are dealing with a vector, but like before, we have this arrow on the top, emphasizing that we are dealing with a vector. Then what we are doing is that we are also adding the dimension of this vector. So in what dimension, in what space are we creating this 0 vector, that this vector is located? Is it in R2, in Rn, in R3? In this specific case, you can see that in this example, the index that we got here is 3, which basically indicates we are dealing with a 0 vector in 3-dimensional space. So in the R3. In general, we would just note this by n, keeping the notation general, which means that we are dealing with 0, 0, all the way down to 0. So it has n by 1 dimension in Rn. All right, so this is about 0 vectors. It is just a way to make our programming life easier, also to use it in different algorithms when it comes to a bit more advanced algebra. The next type of special vectors that we will look into is this unit vectors. So vectors with a single element equal to 1 and all the others 0, denoted as EI for the ith unit vector in n dimensions, are referred by unit vectors. So what we mean here, when it comes to the unit vectors, if we have, for instance, E1, it means that we have a vector where the ith, in this case, the first element is equal to 1. So you can see that E1 is equal to 1, 0, 0. So in the first element, we got 1, and the remaining is 0. And this is really important that we are dealing with vectors that contain only elements of 0s and 1s. And the only member that is equal to, the only element in that vector that is equal to 1 is the ith element in the entire vector. All the remaining ones are 0. And you can see here that the dimension is no longer specified, but just the index of the entry where the 1 is located. So let's look at another example. In here, for instance, when it comes to the unit vector, yet another unit vector is E2, which basically means that in the second element, so in the second place, the vector contains 1 and all the other members are 0. So here you can see 0, here you can see 0. Only in the second element we have 1. And then in the E3, what we have here is that the third element is 1 and all the other ones are 0. So let's actually look into one bigger vector in higher dimension to make it even more sense. So first I will define and assume that we are dealing with a vector in Rn, so in an n-dimensional space. This gives me an idea that we are dealing with so we are not dealing with a nested vector, we are dealing with a simple n-dimensional vector. So it has n rows and 1 column. So using the square braces, I'm going to represent my vector. So I have all these different members, n members. See, so E, let's say it is E5. So what does this mean? It means that I is equal to 5. And this ith element, so the fifth element, is equal to 1, and all the other entries, the elements in this vector, are zeros. So let's look into this is 0, 0, 0, 0. I'm approaching the fifth element in my vector. So it's this one, this is 1, and the remaining all zeros. So this is a unit vector in an n-dimensional space. And I'm defining it by E5 because my fifth element is equal to 1. Now, those are very handy when it comes to some other techniques in linear algebra and just in general. Think about techniques like row echelon form, solving linear equations, something that we will see as part of the next unit. So many things we can do by using unit vectors. Unit vectors are super important, so you need to understand this concept very well, such that later on you will understand more advanced concepts in linear algebra. Let's now look into the topic of sparsity in vectors. So by definition, a sparse vector is characterized by having many of its entries as 0. So its sparsity pattern indicates the position of a non-zero entries. So what we are basically saying is that if we are dealing with a vector that contains too many zeros, we are dealing with a sparse vector. So this sparsity pattern indicates also the positions of a non-zero elements. So if we have unit vector, it means that we are already dealing with a sparse vector. This is a concept that is super important when it comes to linear algebra, but also in general data science, machine learning, and AI. Because having a sparsity in your vector, it means that you don't have much of an information. Usually a value 0, it means you don't know much about that specific value. And if you got just too many of zeros and too few numbers, which do provide information, it means that you are dealing with a vector that doesn't provide you much information. And there's always a problem when it comes to data science, machine learning, and AI. So sparsity is something that you need to be aware of. You need to know how to recognize it. And you also need to know whether there's a problem in your specific case or not. So let's look into an example. Let's say we are dealing with this vector x that has 5 different elements. So x is a vector coming from 5-dimensional space. So we have, for instance, an element of 3 in the first entry, then we have 0, 0 in the second and third entries, then we have an entry 4, which coincidentally also contains value 4, and then the last element in our 5-dimensional vector x is equal to 0. Now, what do we see here? We see that the majority of elements of a vector x is equal to 0, because we got in total 5 elements, and then we got 3 of it actually being equal to 0, and only 2 of them containing information like equal to 3 and 4. So only 2 elements that are not zeros, are non-zero elements. It means that 3 divided to 4, which is basically 60%, 60% of all the entries in the vector x are equal to 0. So the 60%, it means that is above half, so above 50%. 60% of all the information in this vector, the majority is simply equal to 0. This type of vectors we are calling sparse vectors, and sparsity is really important concept that we need to keep in mind later on. So while we can visualize vectors in the 2 and 3 dimensions, in linear algebra, like we just saw in case of this n-dimensional vectors, visualizing this type of higher dimensional vectors becomes very difficult. So this mathematical flexibility to work with this type of information, so when we can represent information with many entries, we can represent it by vectors, which we can actually not visualize, becomes very handy for complex data structures, for different simulations in physics, and much more. So we just saw in a couple of examples how we can represent vectors in a high-dimensional space using this square braces and this common vector notation representation. We saw that in an n-dimensional space, we could very easily represent this very large matrix or vectors by just using this vector representation. For instance, if we got a vector that had n different entries, where n is, for instance, 1,000, so let's say we have 1,000, then we can represent this vector or this information by using common vector notation. So A1, A2, all the way to A,000. So of course we cannot visualize this. It just doesn't make sense. We can visualize two-dimensional vectors. We can visualize three-dimensional vectors, but we cannot visualize 1,000-dimensional vectors. So vector that comes from R,1000. But what we can do is still make use of this very useful information in order to do different operations. And later on we will see that this property, and specifically this part of linear algebra, it helps us to work with vectors in any number of dimensions, whether it's thousands, millions, billions. This mathematical flexibility is super important for more complex data structures, for matrix multiplications, when, for instance, we are doing different algorithms, including how we can represent very large matrices, very large feature spaces. All this different information we can represent just by making use of vectors coming from this specific part of linear algebra. Let's now finish off this module by looking into some applications of vectors. So one common application of making use of vectors is when we are performing different operations while having words and we want to count those words. So this is a super common application of vectors, and we can count these words, and you can even plot a histogram of how often each of these words appear in a document. So a vector of a length n, for instance, can represent the number of times each of these words in a dictionary of n words appears in a document. So just for the sake of simplicity, let's assume that we got a dictionary that contains only 3 words. Of course, in reality, the dictionary, what we also refer often as a corpus, it contains much more many words. But for the simplicity, we will assume that we just got 3 different words in our dictionary. So that's the total. Now, let's assume that we got a document with these different words, and we want to count how many times each of those words that we got in dictionary actually appear in our document. So, if our document is described by this vector, so it contains an entry of 25, 2, and 0, it means that in our document, we got 25 word 1 from our dictionary, so in the position 1, 2 times word 2, and 0 times word 3. So basically, we have a predetermined set of words in our dictionary, in this case 3 words, word 1, word 2, and word 3, and they have a specific index, specific position in our vector. And when we are putting these values in here, then the machine or the computer, the program will understand that if we have 25 in the first position, then the word 1 in the dictionary appeared 25 times in our document, whereas the second word appeared only 2 times, and the last word, word 3, didn't appear at all, so 0 times in the entire document. So let's look into a practical example, actually, to make even more sense. So this is, by the way, a common practice to count different variations of a word. They are a common application in n-grams, large language models, transformers. They are just a cornerstone of many language models when we want to count the words in the document to understand how often the word appears, because this gives us an idea what this document is about. Knowing how many times the same word appears in that document, it gives us an indication of the topic of the document. Also, we can make use of it to do sentiment analysis to understand what this document is about, not only in terms of the topic, but also is it a positive, is it a neutral, or a negative document, so to say. So, for instance, if we got the following words that correspond to our dictionary. And in our dictionary, we got just, let's say, 6 different words. Then what we can do is that we can say 3, 2, 1, let's say 0, 4, 2. And the corresponding words are word, row, number, horse, eel, and then document. What this means is that we have a text, what we refer as a document, that contains 3 times the word word, that contains 2 times the word row, contains 1 time the word number, 0 times the word horse, and 4 times the word eel, and 2 times the word document. So this is basically a common way representing the frequency of the words in the document. Let me actually give you another example. And in here, I want to emphasize another thing, the concept of stop words. So let's say I make this 10, and then here I say there is a 3 times the word I, 2 times the word reading, 2 times the word library, 4 times the word book, 0 times the word shower, and 10 times the word So you can see that in here we are dealing with a document that contains 10 times the word which is something that we refer as a stop word. So those are things that actually don't give us too much information about what the document is about, because is just used everywhere, but it is appearing too often. So you can see 10 times the most frequently appearing word. This is what we refer as a stop word. And then another thing that we can observe, the second thing we can observe, is that we are dealing most likely with a document that describes library, reading, because you see the words like reading, you see the word like book, library, but another word, shower, that is totally unrelated to reading, book, or library is appearing 0 times. So even by looking at these counts, we can already get an idea what the topic of this document is about. So you can see already now from this very basic example where I made too many assumptions regarding how small the dictionary should be, you can even see now how we can use these counts in our dictionary from our text in order to get idea about the topic of the document or topic of the conversation. It can be a topic of the tweets. If you have a tweet data, it can be topic regarding a book. If you have many book texts, it can be, for instance, the topic of the review. If you got product reviews from Amazon, for instance, using this count can help you to get a topic regarding topic from that text. Then you can also use it to remove the stop words, because usually the stop words are the most frequently appearing words. It can also give you an idea about the sentiment. For instance, here we are dealing with a neutral sentiment. It's not positive, it's not negative. It's just reading a book in library, that kind of topic. So all this can be super helpful when it comes to natural language preprocessing. That's a field where this text processing, text cleaning, and then using that for modeling purposes is what plays a central role. It also plays a super important role in the large language models, in the transformer models, and in the simple matters like bag of words or in the TF-IDF. All these, they are based on this idea of counting words and how we can use this information. And you can see how vectors come into play in these different applications of linear algebra in data science, natural language preprocessing, in artificial intelligence, in machine learning. So they are super important. Another application of vectors can be representing customer purchases. For example, an n vector P, so let's say P, can record customer purchases over time, with PI being the quantity or dollar value of an item I. Now, what does this mean? So let's say we have a vector P that represents the customer's purchases, and we are dealing with a single customer, and we are just saving over time that information, how many times this customer has made purchases over time. So the quantity is in the dollars, so the dollar value of item I purchased. So we are basically keeping track of what is the value of the item I that the customer has purchased. So what we can do is we can assume that in here, actually, it already makes that assumption. It says n vector, which means that the number of rows or number of items that the customer purchases is n. Now, what the problem says that it represents is that in each entry, and here we have in total n entries, we got a dollar value of item I, which means that here if I have P1, P2 all the way to Pn, and here somewhere in the middle I got Pi in the east position, it means Pi represents the value of item I. So, for example, if I'm dealing with a customer that buys, let's say, courses, and the first item that the customer is buying is a mathematics course. So I'm writing mathematics course, and this is the first course that it buys. E is, by the way, just a way to refer to the ETH purchase. So let's say here, somewhere in the middle, the customer decides to buy a deep learning course. Deep learning course. And then it continues buying, the customer continues buying courses, and the last course that the customer buys is, let's say, career coaching course. Now, let's say the mathematics course costs around $1,000. Let's say the deep learning course costs $3,000. And then let's say the career coaching service, which is usually one of the most applied and personalized one, can cost all the way to $5,000. Now, we see that in the east position, this is the east position. Let me change the color, by the way. So let's say this is the east position. This is the first position, and this is the last position. So those are just indices. We can see that in the east position, we got the 3,000, which means that the PE is equal to $3,000. So this indicates that in the east purchase, the customer purchased deep learning course, and the value of that item was equal to $3,000. All right, so now we are ready to go on to next major topic, which is about vector addition and subtraction. So we are going to do some operations and apply these operations to vectors. So let's first formally define this idea of vector addition. So two vectors of the same size are added by adding their corresponding elements. The result is a vector of the same size. So let's unpack this. It says two vectors of the same size are added by their corresponding elements. So here it refers to two different vectors, let's say vector v and vector w. And it says let's add them, what we refer as vector addition. And says for that what we need to do is to take all the elements of v and then all the elements of w, and using their corresponding elements, so indices, that helps us to understand where those elements are located, we are using in order to add each element in the vector v to the element of the vector W in the same position. And do note that in the second part, it says the result is a vector of the same size, because we are adding two different vectors of the same size. It's mentioning here. It means if we add two different vectors that have the same size, we are going to end up with a vector that has the same size. Now, once I go into the examples, it will make much more sense. Let's quickly also look into this concept of subtraction. So on its own, subtraction is very similar to this idea of addition. So if we have a subtraction, let's say we have vector v, we subtract vector w, then we are doing basically what we just did to the addition, only instead of doing add, we are doing subtract. So again, we are just subtracting from vector v, vector w. They have the same size, so we end up having the result, which is a vector of the same size. Only one thing that you can see is that this can be also rewritten as v vector plus and then minus w. So we basically can represent subtraction on its own as a way of adding, only we take the negative, so the opposite directed vector. So this will make even much more sense once we go on to the examples. So let's look into our first operation example where we are adding two different vectors. This is a basic example. We got just two-dimensional two vectors. We got vector A that has entries 2, 3 and vector B that has entries 1, 4. And what we are doing is that we are adding vector A to vector B. We just learned that A, we need to have the same size of vectors. So you can see that vector A has a dimension 2 by 1. Vector B has a dimension of 2 by 1. So their sizes is the same. Both they got two entries only, two elements. And at the same time, we just learned that what we need to do is to take their corresponding elements and add them to each other. Now, what does this mean? It means that we take from A the first element 2, and then we take the first element of the second vector, which is the B. So we take the 2 from here and 1 from here, the first element of A and the first element of B, and then we are adding them to each other. 2 plus 1 is equal to 3, and then the same holds for the second entry. So 3, which is the second element of vector A, and then 4, which is the second element of vector B, we are saying 3 plus 4 is equal to 7. So let me write it down even in a simpler manner such that it will make much more sense. So vector A has elements 2, 3. In the first element, we got 2. In the second element, we got 3. So A. Then we want to add B, which has in the first element equal to 1, and the second element is equal to 4. This means that if we want to add these vectors, 2, 3 plus 1, 4, this is equal to, we need to take 2, we need to add 1, so this element and this element, and then we need to take 3, we need to add to 4, so this one and this one, which is equal to 2 plus 1 is equal to 3, 3 plus 4 is equal to 7, so we got vector 3, 7. Do note that this vector, the result vector, contains again two elements and just one column, so 2 by 1. So you notice that the size is the same of this result vector. Now let's actually generalize this concept before moving on to the next example. So if we got, let's say, vector A that contains n elements, A1, A2, all the way down to AN, and it is from n-dimensional space, and we got vector B that also has n elements, so remember that they both need to have the same size, so B1, B2, all the way to Bn. So they come also, so B comes also from n-dimensional space. So then when we add A to B, this is equal to A1, A2, all the way to AN plus B1, B2, all the way to Bn. So n by 1, the sizes, this is equal to, let me actually use this color to make it even more visible. So for the first entry, for my result vector, I will get A1 plus B1, then A2 plus B2. So all the way down onto the nth element, which is AN plus, let me use a different color, A1, B1, B2, Bn. So you can notice now, in general terms, what we are doing here. So we are taking the A1 coming from the vector A, we are adding in the same position the value that comes from vector B, which is B1. We are saying take the A1 plus B1. This is the first element, so the position stays the same, and then in the result vector. So we take all the corresponding values that have the same position in the corresponding vector, first from vector A and then vector B. We are adding them, and this forms our new vector. And this new vector will again have a size n by 1. So you can see that the sizes of the two vectors are the same, both have n elements, and then we are using their corresponding elements to add them to each other element-wise, and then we are getting the result that has the same size, so n by 1. So this is a more general description of how you can add two vectors. Let's now look into the specific example. So we have a vector with the entry 0, 7, 3. So this comes from R3, you can see, so three-dimensional vectors. The second vector is 1, 2, 0. And then the final result is 1, 9, 3. So how we got this? We took 0, we added 1, 7, we added 2, and then 3, we added 0. So you can see all these elements, element-wise. And then this is equal to 0 plus 1 is 1, 7 plus 2 is 9, and then 3 plus 0 is 3. Exactly what we got here. So again, the same sizes, and the result is from the same size. So quite straightforward. Now when it comes to the vector subtraction, what are we doing what are we doing here? So we are doing kind of very similar thing. We are taking this element 1, we are subtracting the other one in this first element. Then we are taking the 9 in the second position and subtracting this again from the second position of the second vector. And we are putting in here 1, and then 1 minus 1 is equal to 0. 9 minus 1 is equal to 8. So we get a result vector 0, 8 like in here. And you can see that the sizes stay the same. So also in this case, let's write more general this idea of subtraction. If we got a vector A from Rn, so n-dimensional space, and it can be represented by A1, A2, all the way down to An. So it has n elements, n by 1. And then we got B also from Rn, so coming from the n-dimensional space, which means that it got n elements, so B1, B2, all the way down to Bn, again with the same size, n by 1. Then A minus B is simply equal to A1. Let me actually use the same colors to make it easier to follow. So let me first draw my square races, and then here I will use blue for A and then red for the color for second vector, which is B. Here I will use black minus. Then, given that the same size should be for the result vector. I already know that I expect n different elements for this. And then here, I'm taking this first element that comes from vector A. I'm subtracting from this the first element that comes from vector B. So element-wise subtraction, B1. And I'm already getting the result for the first element in my result vector. So you can see A1 minus B1. I'm taking this element and subtracting them from each other to get A1 minus B1. And then the same holds for all the other values, only coming from different elements from vector A, subtracting from this the corresponding values element-wise from the vector B, so B2, B3, all the way to AN. So you can see that in my result vector, A vector minus B vector, in the first element I get A1 minus B1, then A2 minus B2, then A3 minus B3 in the third element, all the way down to the nth element, which is equal to, this should be B, AN minus BN. So this already should make much more sense. So every time we take the element in the same position from one vector than the other, we subtract from each other in order to get the corresponding element in the final vector. All right, so let's now, before moving on to the properties, I want to show you this only in a coordinate space. So what this means in terms of visualization in a coordinate space. So let's say we have a coordinate space This is my y-axis. This is my x-axis. So this is x and the y, and this is my center. So 0, 0. And what I'm doing here is simply I want to have vector A. Let's say this is just vector, a simple one with the coordinates, let's say 4 and -2. And I got vector B. Let me use a different color. Vector B that has coordinates, let's say -4 and 4. So let's actually visualize them. Let's first start with the vector A, which has a x value of 4, 3 and 4, 1, 2, 3 and 4, and the y value -2. So this is my vector A. And let's now visualize the vector B. So -4 and 4, which means that, let me actually extend this. This is -4, so the x coordinate is -4. So it should be here. And then the y coordinate is 4. So 1, 2, 3, and 4. It's this one, which means that my vector B is this one. Right. So you can see now that the vector A is in here and the vector B is in here. Now, what I want to do is to add these two vectors to each other. So what I want to do is to take this vector A and add to this the vector B, which is equal to 4 minus 4, it was 0, and then minus 2 plus 4 is equal to 2. So 0 and then 2, it is 0 and 2, 2, so this is my result vector. So now when we are clear on how we can add vectors, how we can perform these different operations, and what it means in practice when it comes to looking at the vectors in a coordinate space and adding them or subtracting them, we are ready to look into the properties of vector additions. So this is something that will definitely seem familiar to you from pre-algebra, where we are basically using all these properties that we already know that holds for numeric values, for the scalars, that being transferred to this vector space. So we are going to talk about these 4 different properties that the vectors have. The first one is the cumulative property, which says that if we add a vector A to vector B, then this is the same as adding a vector B to vector A. So basically, the order of the vectors doesn't really matter when it comes down to adding them. So formally, A plus B is equal to B plus A for any vectors A and B of the same size. Then we have associative property, which says A plus B plus C is equal to A plus B plus C. We can write both as A plus B plus C. Now, what does this mean? We know from pre-algebra that this parenthesis means first do this addition and then do the rest of operations. In here, it basically says if you add A to the B first and then you add the C, is the same as first you add B to the C and then on the top of that you add the vector A. So then the third property is addition of 0 vectors, which says if we add a 0 vector to vector A, then this is equal to adding a vector 0 to A, and this is equal to vector A. So adding the 0 vector has basically no impact on the vector whatsoever. Then the final property is subtracting a vector from itself, which means if we take the vector, we subtract the same vector from itself, so A minus A, and we get a 0 vector. So A minus A is equal to 0 vector, and this yields the 0 vector. Now let's look into each of those properties one by one, and let's look into specific examples. In some cases, we will prove this on the example that we have to make this concept much more clear. So let's start with this cumulative property of vector additions. So we want to see whether A plus B is equal to B plus A. So let's say we have a vector A that has coordinates or magnitude and direction that is equal to 1 and 2. Then we have a vector, let's say B, that has a magnitude and direction of -2 and 3. So the first thing that we want to check is indeed whether the A plus B is equal to B plus A. So therefore, let's first calculate this part, and then we will calculate this part that I will define by 1 and 2, and we will see whether we are indeed having the same value, the same vector or not. So let's see. So we have here A. So A plus B, which is the first value that we want to calculate. A plus B is equal to 1, 2 plus -2, 3, and we learned before that this is simply equal to take this value and then add this one, so 1 plus -2, and then 2 plus 3. So this gives us a vector 1 minus 2 is equal to -1, and 2 plus 3 is equal to 5. So we get that A plus B is equal to -1, 5, this vector. Now let's look at the second quantity. So B, vector B plus vector A. This is equal to -2, 3 plus 1, 2, and this is equal to minus 2 plus 1, and then 3 plus 2. This gives us minus 2 plus 1 is equal to minus 1, and 3 plus 2 is equal to 5. So we can already see from here that the quantity 1 is indeed equal to quantity 2, which proves that indeed the A plus B is equal to B plus A. What this basically means is that adding two different vectors, the direction or the order is not important. Whether you add A on the top of the B or B to A, it doesn't matter. At the end, is the same. And actually, you can also see it if you combine this or if you do this in more general terms. So let's say if we have a vector A, which is equal to, in an n-dimensional space, A1, A2, up to AN, so it has n by 1 dimension, and you have a vector B with the same size from the same Rn dimension, and it has elements B1, B2, up to Bn, and the dimension is equal to n by 1, then if we calculate first A plus B, and this is equal to simply A1 plus B1, A2 plus B2, up to AN plus BN. And if you calculate the second amount, which is B plus A, and this is equal to B1 plus A1, B2 plus A2, up to Bn plus An, you can see that A1 plus B1 is equal to B1 plus A1. Simply from pre-algebra, you know that if those are all constants, for instance, 2 plus 3 is equal to 3 plus 2. In the same way, A2 plus B2 is equal to B2 plus A2, and then here up to AN plus BN is equal to BN plus AN. What this means is that all these elements, they are basically the same, which means that we already have a proof, so we get this proof, and we can see that even for the general term, independent what this vector A is, what this vector B is, that A plus B is equal to B plus A. This is exactly what we saw before in the first property, which is called commutative property of the vectors, that the A plus B is equal to B plus A. Now let's move on to the other property, which is called associative property of the vectors. Now what this property does and says is that A plus B, so first we do this, plus C is equal to A plus B plus C. And this is then equal to A plus B plus C. Now let's then see this specific property on an actual example. So what this basically says is that if we have this example where A is equal to, actually I had this before, let me simply just remove this part. Let's then add our third vector, which is C, and let's call it, let's say, it has a representation of 4 and 5. Then the idea behind this property is that what we need to prove here, that A plus B within the parentheses plus C is equal to A plus B plus C, and then this is equal to A plus B plus C. So let's see actually whether this is indeed true for this specific case. Now, this should come very intuitive, so I'm going to do it very quickly. So first we have this quantity, this one, then we have this one and this third one. Let's do it very quickly. So A plus B plus C is equal to 1, 2 plus, and then we add C, so it is simply 4, 5, and then this is equal to, we saw before when doing this, that we were getting 1 minus 2, 2 plus 3, and then we add this 4, 5. This is simply equal to 1 minus 2 is minus 1, and 2 plus 3 is 5, plus 4, 5. Now, given that it doesn't really matter no longer that we have here parentheses or not, this basically means that this value is simply equal to minus 1 plus 4. So here minus 1 plus 4, here 5 plus 5. So this is then equal to 3 and then 10. All right. Let's then now quickly do the second amount, which says first add the vector b to vector c, and only then add the vector a on the top. What this means is that we need to take 1, 2, this is vector a, and we will only add this once we have added the minus 2, 3, the vector b, plus to the vector 4, 5. Okay, so we can see that we are just leaving this in here. Let's first add this 2. Minus 2 plus 4, 3 plus 5. So this gives us 1, 2 plus minus 2 plus 4 is 2, and then 3 plus 5 is 8. So this gives us, let me remove this calculations. So this gives us 1 plus 2 is equal to 3, and then 2 plus 8 is equal to 10. Okay, great. So now we got already the quantity 1 being equal to quantity 2. Let's check whether this is all equal to this one. It should already be something that you see now, given that we know just from mathematics that parentheses doesn't really matter when it comes to the scalars, and adding two vectors is basically very close to this idea of additive property of the scalars. But just let's quickly do it to be 100% sure. So when we take this vector a to the b and to the c, we add all this. This is equal to 1, 2, added 2, minus 2, 3, and then added this to 4 and 5. Now, what this is equal to, let me actually write this in a bit shorter way such that it can be all fit in this small place. So 1, 2 plus minus 2, 3 plus 4, 5. This is equal to basically 1 minus 2 plus 4, and then 2 plus 3 plus 5. And what is this number? One minus 2 plus 4 is simply equal to 1 minus 2 is equal to minus 1, and then plus 4 is equal to 3. So first element is 3. 2 plus 3 plus 5 is equal to 5 plus 5, which is equal to 10. Perfect. So now we get the confirmation that indeed a plus b plus c is equal to a plus b plus c is equal to a plus b plus c. So let's quickly also look into this addition of zero vector and the subtracting a vector from itself properties, and the detailed explanation of this or example of this I will leave it to you. So when it comes to this a plus 0 is equal to 0 plus a is equal to a, so this property, let's say if a is equal to this 2, 3, and then we are adding on this a plus some 0 vector, which basically means take 2, 3, and then added the same size of 0 vector, you can see that this is the same as adding just zeros on these values. Now, what do we get? We get that this is equal to 2 plus 0 is 2, and then 3 plus 0 is 3. There we go. So we already see very quickly that it doesn't really matter whether we add a 0 vector to this original a vector or not. In all cases, it just adding a 0 vector has no effect. And seeing from the cumulative property that a plus b is equal to b plus a, we already know that if a plus 0 is equal to a and is equal to this, then also 0 plus a will be the same. And we can see indeed that we just saw that a plus 0 is simply equal to a. So we basically have quickly proven all this. Now, when it comes to the subtracting a vector from itself, I think this is a very nice one just to see how we take the same vector and subtract from that value and we get 0. And this is very similar to working with just real numbers. In the same way as 3 minus 3 is equal to 0, also when we have a vector consisting of the scalars, like a is equal to 3, in the same manner, if we take this a and we subtract it from itself, so a minus a, then what we will get is 2, 3 minus 2, 3, and this will give us 2 minus 2 is 0, and then 3 minus 3 is 0. So we get a vector 0, so 0 vector. So now when we are clear on how we can perform different operations on our vectors, and also we know what are the properties of adding and subtracting different vectors, we are ready to move on to a bit more advanced topics. So in this module, we are going to discuss this idea of scalar multiplication. We're going to look into the example, how what happens and how we can do the vector multiplication with a scalar. Then we are going to look into the span of vectors, what it means to have a span of vectors, what is this idea of linear combination and the relationship between the span and linear combination and the unit vectors. Then we are going to look into the application of scalar vector multiplication in audio scaling example. And then finally, we are going to finish off this module by looking into the length of a vector and a dot product. And we are going to go back to this idea of distance, understanding vector magnitude, and understanding vector length. So let's get started. Now, before we look into this idea of span and linear combination, I quickly wanted to look into this idea of scalar multiplication and the specific definition of it. So formally, the scalar multiplication involves multiplying each component of a vector by a scalar value, effectively scaling the vector's magnitude. So what do I mean here? Let's say we have a vector, and I will write it in the general terms to keep everything general. So let's say we have a vector A. Let me pick up my pen. A, and this vector A is from n-dimensional space. So it is from Rn, and it can be represented by A1, A2, up to An. And I have this magnitude of a vector, and now I want to scale this vector for which I know the magnitude and the direction. I want to scale it with a scalar. And we learned before that the scalar is just a number. So scalar, in this case, I will be referring it to by C. So C will be my scalar, and this comes from R, which means that it's a real number. Let me actually use a different color to make it easier to follow. Okay, so my scalar will be with the color red. So C, and C comes from R. So what do I mean by scalar multiplication? I mean that I want to find what is this C times A. This is what we mean by scalar multiplying with a vector. Now, what does this definition say? It says when we are multiplying scalar with vector, so the scalar multiplication, meaning multiplying vector with the scalar, it involves multiplying each component of a vector by a scalar value. So if we translate it to this specific example, it means that this amount, so this amount is equal to taking C and multiplying it with each element of this vector. So each component of a vector. And what are the components of my vector? The A1, A2, A up to the point of An. So all these components. So that means that the first element of this new vector, the scalar multiplication result, will be c times a1, c times a2, so all these middle elements, and at the end, again, c times, and then an. And then in both cases, of course, the number of elements doesn't change, so the number of rows of my vector doesn't change, it's n. So here also n. And then number of columns is the same, so it's just a column vector, so one column. So what we see here is that we go from a1 to c times a1, we go from a2 to c times a2, up to the an transforms into c times an. So we see very easily that I keep all the elements from this vector, I take them in here, and instead what I'm doing is that I'm multiplying every element from this vector by the scalar c. So this is exactly what this definition says. And let's actually go ahead and do a hands-on example with some real numbers to have this method and to have this definition very clear in our mind, because we are going to make use of this fundamental operation, scalar multiplication, on and on in the upcoming lectures and just in general in your journey in any applied sciences. So this is an example of scalar multiplication. Here what we are doing is that we want to multiply this vector c. So in this case, the vector is defined by a letter c, and then on the top we can see the arrow indicating that this is the vector now. And here we refer the scalar by a letter k. We are saying we want to perform scalar multiplication, which means that we want to multiply the vector c by the scalar k. So how we can do that? So what we want is to multiply k by c, and we just learned that for that, what we need to do, let me write this over. So this is equal to minus 2 multiplied by 4 minus 3. This is my vector. So this is the k and this is the c. This is equal to, so I take my scalar and I multiply it with each of the element of the c. So minus 2 times 4 and then minus 2 times minus 3. So minus 2 times 4 is equal to minus 8, and then minus 2 times minus 3, so minus minus, it goes away, it becomes a plus, and then 2 times 3 is 6. So my end result, the k times c, is equal to minus 8 sixths. This is my final result. So let's quickly also do yet another example. And this one is a unique one because it's relating to this idea of multiplying something with a zero, which is something that we also know from a high school, that when we multiply a number, let's say 7 by 0, we are getting 0. And here, in this example, the problem is describe the effect of a scalar multiplication by 0 on any vector, which means what we are doing is that in this example is we want to know what is this result of any vector, let's say vector c, so we will use the same example, c, only this time instead of multiplying it with the scalar k equal to minus 2, our scalar will be 0, which means that c is equal to 4 minus 3, and then the k is now equal to 0. And we want to find out what is this k times c. Let me actually write down the k with a different color. Good. K is equal to 0. So what we want to find out is k times and then c. And this is then equal to 0. So I'm taking the k, 0 times, then I'm taking each of the elements of c, which is 4 and then minus 3. And I know that when multiplying the number with a 0, it gives me 0, which means that I end up with 0 here. 0 times 4 is 0. 0 times minus 3 is also 0. So I end up with a 0 vector. Now, this gives me an idea already that I can make a general conclusion that independent of the type of vector that I have, independent what are these values in my C, if I have any vector C and I'm multiplying it with 0, then this will always give me a vector of 0. Because all the members of this final vector will be just zeros. So if, for instance, the C comes from, let's say, Rn, so it has n different elements, it comes from n-dimensional space, then my final result of 0 times C, so this 0 vector, this one, so 0, this one will come also from Rn. So you will be having a vector, so 0 times C will then be equal to 0, 0, blah, 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 0. So n times zeros. So this is then the idea of multiplying, so scaling a vector with 0. And this is our example 2. All right. So let's now move on to our application of scalar vector multiplication. And then after this, we will go back to this idea of linear combinations and the spans. So in this specific application, we have a scalar vector multiplication, and we are looking into application of audio scaling. So the scalar vector multiplication audio processing, this can change the volume, for instance, of an audio signal without altering its content. So you might have noticed that when you are listening to a video, you can simply increase the volume of that video or decrease it. But you will notice that the content doesn't change. You are just increasing the volume or decreasing it. Even on the TV, when you are watching a show, you are increasing the voice or decreasing. Now, what you are basically doing behind, and this is super interesting, is that behind the scenes, what is happening is that there is simply audio that contains that show, and the audio of that show is being multiplied with a scalar. And that scale is simply the volume scale. If you scale it in such a way that you want to decrease the volume, so the audio will then have a lower volume, then you are simply multiplying it, your vector containing the audio information in such a way that those newer volume indications, they will be containing lower numbers. Hope this makes sense. Let's look into the example. This will definitely clear this out. So let's assume we have a vector A that represents the audio signal. And we want to multiply vector A by scalar B to adjust the volume. So B is some sort of number. It can be, so B comes from R, so it's a real number, while A is simply a vector. Given that it doesn't mention it here, I'm assuming that A comes from Rn. So it comes from n-dimensional space. So imagine of A as this vector, A1, A2, blah, 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 up to AN. And each of these values, it basically describes the audio signal. So it represents an amount, so it contains an amount that represents the audio signal of your video or your show. And then the B, in this case, for instance, in this example, you can see that the B is then equal to, for instance, 1 divided to 2, or B is equal to minus 1 divided to 2. So you can see that B is equal to 1 divided to 2, which basically is a fancy way of saying that B is equal to 0.5, or B can be equal to minus 1 divided to 2, which is minus 0.5. Now, then it says, then the B times A, which basically means multiplying our scalar beta by the vector containing the audio signal A. So this B times A is perceived as the same audio signal, but at the lower volume. Now, why lower? Because you can see that B is equal to 0.5, or minus 0.5. It means that once you take all these elements of your A and you multiply it with a number that is smaller than 1, in this case 0.5, then all these numbers will decrease, which means that also your audio volume will decrease. So let me actually show you an example. So let's say our talk show is very short and the audio variation is very low. You have a vector A that is quite small. It comes from a three-dimensional space, so R3, and it has numbers like 3, 6, and then 5. So 3 by 1 vector. And then we have our audio adjustment scalar, beta, which is equal to 0.5. Now, when we take the beta, we multiply it by our audio signal. Then what we do times, it's clear, so times, what we are doing is that we are simply taking all the elements of our A, so 3, 6, and 5, and what we are doing is that we are multiplying it by 0.5, 0.5, and 0.5, or you can also say 1 divided to 2. So what this is equal is that 3 times 0.5 is 1.5, 6 times 0.5 is 3, and then 5 times 0.5 is 2.5. And you can see that all these numbers, 1.5, 3, and 2.5, they are smaller and specifically 2 times less than all the original values in the original audio. So original audio is A, which was 3, 6, and 5. And the new audio, the scaled one, is, so audio scaled, so B times A is equal to 1.5, 3, and 2.5. So you can clearly see this transformation where this element 3 is larger than 1.5, 6 is larger than 3, and then the last element 5 is larger than 2.5, which means that this audio is much at a higher volume. So the volume 2 times higher than this audio. So this is basically the idea of applying scalar multiplication to our audio preprocessing. I will leave the other example to you that will show that when your scalar is equal to minus 0.5, you again will end up with a lower volume. Only that time, the volume will be much, much lower than the original one. So now that we know how we can perform scalar multiplication in theory, as well as we have looked into an example how we can do it in terms of the numbers and multiplying them, and we have also seen applying scalar multiplication in practice. So we have seen in this audio processing stage the multiplication process. We are ready to look into the visualization of it. This will help us to get a better understanding on what exactly happens when we are scaling different vectors. Let's look actually in the following example. So let's assume we have a vector. Oh, let me remove that. So let's assume we have a vector, and that vector is, let me get a color, this one for instance, a vector A, and this vector A consists of elements 1 and 2. So where does this vector lie? The vector is with 1, so here in our coordinate system, this is our x-axis, this is our y-axis, and here we got, let me actually pick another color, let's say black 1. And then we got 1 and then 2, right? This is 2, this is 1, so it is this one. So the line that we get here, it is this one. So this is our vector A. Now let's assume I want to multiply my vector A. So I want to scale my vector A by a constant 3, by a scalar 3. So I have a scalar, let's say I call it K, and this K, It's a different number. Let's say k is equal to 3. So what I want you to do is to perform a scalar multiplication. So I want to obtain k multiplied by a. And we learned that this is simply equal to 3 times, and then 1, 2, and then this is equal to 3 times 1, 3 times 2, which is equal to 3 and then 6. So let's also visualize the scaled vector. So let me pick this yellow color. This will be our scaled vector. So we have done scalar multiplication and we are going to visualize that. So we have 3 and 6. So this is 3, 1, 2, 3, and this is 6. So we have this point. So you should already see what is going on here. So we got 3a here. So you can see that this part is our vector a, and this longer one is 3a. And even visually you can see that this longer vector is simply the 3 times of the shorter vector. So we got this, and then if you add on the top of this the same 3 times, you will then end up with the original, so scaled version of that. So basically, this is a, this is a, this is a. We combine 3 different, so we scale a 3 times, and we simply get a 3 times longer version with the same direction. So you can see that when we are scaling, even visually, it makes sense. So we are scaling our vector a 3 times, and we are just getting that vector. So we are transforming. Well, let me remove this. So basically, we are taking this vector and we are scaling it up to this point. If I would do it only 2 times, then it would be something like this. Or 1.5 times, it would be something like this. So only half of it. So now this should make much more sense. Let us actually do yet another example to make sure that we are clear on these visualizations, because we are going to make use of it when looking into this idea of linear combination in a span. So let's say we have a vector b, and this vector b has elements 0 and 3. So let's visualize and plot this vector. So it contains elements 0 and 3. So 0 and 3. So this is the x element and the y element. On the y-axis, we can see this is 3, which means that our vector b is this vector. All right, perfect. So this is our b. Let's now multiply, so scale our vector b by a scalar 2. So let's say we want to get 2 times b. So what is this amount? This is equal to 2 times, and I'm simply taking each of those elements, 0 and then 3. So this is then equal to 2 times 0 is 0, and then 2 times 3 is equal to 6. So this is my new scaled vector, 2 times b vector, this one. So let's visualize this. The x-axis value is 0, so we are still here. And then the y-axis value is 6. So what is 6? This thing. All right. So you already should see that this is very similar what we had before. So this is 2b. All right. So this all should make sense. Also, we learned as part of the high school when visualizing different plots. So this is quite similar to this idea of having y is equal to x and then scaling it, getting like y is equal to 2x. So in this case only, we know exactly where the vector starts and ends. So we have a much more specific definition instead of having all this infinite number of points on the line. But the idea stays the same. So we are taking this vector and we are then scaling it 2 times, so we get 2b vector. And I could do the same, only instead what I could also do is I could do like 0.5 or 1 divided 2 times b. So I take the half of it, which means I would get this vector. Or I could multiply it with -1, so minus 1 times b. So I would scale with -1. And then I would simply get the negative version of my original vector. So this thing. This would be minus b, or -1 times b. So this is basically the idea of scalar multiplication when visualizing it in our coordinate system, Cartesian coordinate system. And now when we know all this, we are ready to move on this idea of linear combination. And now when we know all this, we are ready to move on this idea of linear combination. So let's now formally define this idea of linear combinations. A linear combination of vectors a1 up to am using scalars b1 up to bm, or what we also refer as beta 1 to beta m, is the vector beta 1 times a1 plus up to beta m times am. And the scalars are called the coefficients of linear combination. And any vector b in n dimensions can be expressed as a linear combination of the standard unit vectors e1 up to en. The coefficients in this combination are then the entries of b itself. Well, this is a whole bunch of information. Let's unpack them one by one. Firstly, I want to mention about this m. So far, we have seen this idea of n. So I just wanted to experiment with a different one just to ensure that we are clear that you can use any sort of identifier to describe the size of your number of vectors that you got. And in this case, we got m different vectors, because so far we were using this n in order to describe the size of a vector. And now we are no longer talking about the size of a vector, but the number of vectors. Therefore, I specifically didn't use the letter n. So here, m is simply the number of vectors. So don't confuse this with this thing where we were plotting this and we were saying this a1, a2 up to an. Because in here, we basically mean that we are dealing with some vector, a, and this has n different elements. Whereas in here, we are already moving from this idea of one vector, and now we are talking about multiple vectors. So we have m different vectors. They all look like kind of this, only with a bit more complex indexing that we also saw before. All right, but we will learn this, or that's not an issue. I just wanted to mention this to ensure we are at the same page. So then let's move on to this idea of using scalars beta 1 till beta m. So it's a common practice in linear algebra, in general in mathematics, but also definitely in data science, statistics, and in artificial intelligence, to use beta 1 as a way to describe the coefficient. So what do we mean by coefficient? It is just a scalar. So it's just a constant or a number. So in this case, for instance, this beta 1 can be 0.5, beta 1 can be 2, beta 1 can be, let's say, 100. It just describes how much we are multiplying, scaling this vector a1. So far, we have done a lot of scalar multiplication already, a lot of details there, and we have seen different times different scalars that we use. We can use 0 as a scalar, we can use any other number, as long as it's a real number. So this beta 1 should belong in the real number space. So it's a real number. And of course, the same holds for all the other betas. So we have m different vectors, which means we are going to have m different scalars, because each of those vectors we are going to multiply with their corresponding, so respective scalars. So beta 1 is basically the scalar or the coefficient that we are using to scale A1. Maybe I can actually write this down on a new page such that we can save this as a slide page for you. Let's write it down. So what do we have as this idea of linear combination? So linear combination simply involves taking several vectors to go from this formal definition to more practical terms. So we got this A1, A2, up to AM. And what we want to do is to take the linear combination of these m different vectors. So we got m is the number of vectors. And to get a linear combination, we need to scale each of those vectors, which means that we need to have these different scalars, let's say beta 1 for A1, and then plus beta 2 for A2. So each time we are scaling each of those vectors, where beta 1 is the scalar or the coefficient of the vector A1, and we are performing scalar multiplication of our scalar beta 1 with the vector A1, and then we are adding to this our beta 2, which is the coefficient corresponding to the vector A2, and then adding beta 3 times A3, and then ... So all these different vectors up to the point of beta m times AM. And all this, so A1, A2, up to AM, those are all vectors belonging to the M space. So those are all vectors coming from the m-dimensional space. So in here, this is the linear combination of our m different vectors. And the beta 1, beta 2, up to beta m, those are all constants. So those are scalars or real numbers that belong to R. So those are real numbers. All right, so now when we are clear on that, let's also unpack this idea of coefficients. So the scalars are called the coefficients of linear combination. So basically, all these members, so beta 1, beta 2, up to beta m, that belong to real number space, they are called coefficients. This is what we are referring as coefficients. And these coefficients, this idea and the name is super important because you will see this time and time again appearing in your very basic machine learning models or some other applications of linear algebra, because the end goal is always to find these coefficients. So these coefficients, those are numbers that we are using to scale these different vectors. And the idea of coefficients is very central because those are numbers that define how exactly we are combining all these different vectors. Because this beta 1, beta 2, beta 3, they can be different numbers, real numbers. And every time when we are choosing these coefficients or these betas, we will then end up with a different combination of these vectors. So we're basically mixing all these different vectors, and the way we mix it and how we will mix it, it will depend on the values of this beta 1, beta 2, beta 3, up to beta m. So these coefficients. So therefore, coefficients are super important and they define the end results from our linear combination. So any vector b in n dimensions can be expressed as a linear combination of a standard unit vectors, E1 up to En. So when looking into this idea of unit vectors, we saw already what this E1 is, what this E2 is, up to En. And we saw that E1 is, for instance, if it's from an n-dimensional space, and it says from n dimensions, then E1 simply means 1, 0, 0, dot, 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 0. Then E2 means 0, 1, 0, dot, 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 0. So we already saw this. This is not something new that we are seeing. So 0, 0, blah, 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 and then 1 at the end. And what this definition basically says is that any vector B, as long as the B comes from n-dimensional space, we can represent this by using these unit vectors and by linearly combining them. So this is yet another part of this definition, and we are going to, by the way, go through each of the parts of this definition one by one, going through each of their examples, as well as visualizing them. So now I just want to quickly unpack all the parts in this definition before moving on to step-by-step examples and explanation. So this is about this linear combination of any n-dimensional vector B that we can create by using a linear combination of these unit vectors. I will come to this in a bit. So then the final part of this definition is that the coefficients in this combination are the entries of B itself. So it says that the coefficients, so beta 1 up to beta m, in this linear combination that we can create are the entries of B itself. So we will come to this section once we are done with the first part. So first, let's have a good understanding of what this linear combination is. And we will also touch base and we will also formally define the idea of span. And after that, we will move on representing and expressing any vector B in n-dimensional space by using standard unit vectors E1 up to En, and this idea of coefficients and then entries of B. So let's start with the first one. So let's assume we have two different vectors. We have vector A, and this vector A is equal to 1, 2. So let's plot this 1 and 2 in our coordinate space, that is this one, which means that our vector A is this one. And let's assume that we have a vector B, and this vector B is equal to 0, 3. So 0 is here, and then 3 is here, which means that our vector B is this one. This is vector B. Now, I want to create a linear combination of this vector A and vector B. So we just learned from the formal definition that in order to do so, I need a beta 1 to multiply the vector A and then I need beta 2, which is the coefficient corresponding to my second vector, in order to multiply the second vector, which is B. Vector B. Okay, so I'm getting the linear combination of A and B by taking any beta 1 and beta 2, which are real numbers. So beta 1 and beta 2 belong to R, so they are real numbers. And then I'm getting a linear combination of the two. So let's look into a few examples of a linear combination of vector A and B depending on the different choice of the coefficients like beta 1 and beta 2. So example 1 is that beta 1 is equal to 0 and then beta 2 is equal to 0. Now what is the linear combination of A and B when my coefficients beta 1 and beta 2 both are 0? It just means that I'm getting 0 times A plus 0 times B, which is of course 0 times 1, 0 times 2, plus, and then multiplying vector b with the scalar 0, which is 0 times 0, 0 times 3. So let's quickly do this, what this value is. This is equal to 0 times 1 is 0, 0 times 2 is 0, 0 times 0 is equal to 0, 0 times 3 is equal to 0, and this is then equal to 0 plus 0, 0, 0 plus 0 is 0. So I'm basically getting a vector 0. All right, so this is then equal to 0. So this is equal to vector 0. So I can also say that this vector, or it's actually a point, so this point is simply a linear combination of these two vectors. Now this is a super basic case. Let's look at another case when in our second example, the beta 1 and beta 2, so our coefficients, they are actually not 0. They are some other non-zero real numbers. So in this example, I will then take beta 1 equal to 3, and then beta 2 is equal to 2. And then what I will do is that I will take the minus 2. Then I can also get rid of one of the elements, and I can get actually a 0 for one of the elements. I will show you in a bit. So then the linear combination of A and B using these coefficients beta 1 and beta 2, where beta 1 is equal to 3 and beta 2 is equal to minus 2, is then equal to, so this amount is equal to 3 times 1, 2, and then plus, we got minus 2 times 0 and 3. Now, what does this give us? 3 times 1 is equal to 3. 3 times 2 is equal to 6. Plus, and then minus 2 times 0 is equal to 0. And then minus 2 times 3 is equal to minus 6. So you might have already noticed why I picked the beta 2 equal to minus 2. I wanted these two numbers to actually cancel each other. So you see, because 6 plus minus 6 is equal to 0. So what do I get in my final result as a linear combination of these two vectors? I get 3 plus 0, so 3 plus 0. So 3 plus 0. And then 6 plus minus 6. And this gives me 3 plus 0 is 3. 6 plus minus 6 is 0. There we go. So this is my linear combination of the vector A and B when using the coefficients equal to 3 and minus 2 respectively. So this value is actually equal to 3 and 0 in this case. All right, so let me actually clean this up, because I also want to visualize this idea, and then we will go back to this linear combination. Let's just summarize what we got before moving on to the plotting part. So if we simply take A and we add to this B, so this is the first case. So this is, as you might have already guessed, this is also a linear combination. Here we are saying take 1 times A and take A 1 times B. And this is yet another linear combination. Here the beta 1 is equal to 1, and then beta 2 is equal to 1. So this linear combination gives us a vector that is 1 plus 0 is equal to 1, and then 2 plus 3 is equal to 5. This is our first linear combination when the beta 1 and beta 2 is equal to 1. This is a basic case, so it doesn't require too much explanation here. We have seen already this. Let's now look into the other example that we saw when we use the zeros as our coefficient. So that is 0 times A plus 0 times B. Then this gave us 0, 0. This was our second linear combination when beta 1 and beta 2 were both equal to 0. And then the third linear combination that we saw was that 3 times A plus minus 2 times B. This gave us 3 and 0. This was our third linear combination where beta 1 was 3 and then beta 2 was minus 2. So then the linear combination of these two vectors is basically all the possible combinations of these two vectors that I can get when scaling or when multiplying these two different vectors by different sorts of scalars. So in all these different cases, what I'm simply doing is I'm taking different sorts of coefficients, beta 1 and beta 2, and then I'm getting the linear combination of these two vectors. We saw that in the simple case when we take the A and we add to B, so basically the coefficients are equal to 1, so 1 times A plus 1 times B, then the corresponding linear combination is equal to 1 and 5. It means that we are getting this vector. So 1 and 5 is in here, which means that we are getting this vector. If we take the 0 as a scalar, so beta 1 and beta 2 are both equal to 0, then the linear combination of these two vectors is simply the vector 0, which means that it is this point. Then if we take the linear combination using 3 and minus 2 as coefficients, then we are getting this, so 0 and 3, so 1, 2, and 3, this is 3, then this is our linear combination. I can also take any other scaled version of my B and of my A, and then I will get entirely different sort of vector. So let me actually show you a few more times a couple of other examples. So let's say I keep my A, so I just take the beta 1 equal to 1, but instead I scale my vector B 2 times. So this was at 3. I'm taking 2 times of my beta, which means that I'm here. Then I can take this, I can add this to my A, so this is 2B. This will give me another linear combination of these two different vectors. I can also, you might recall that we said that the starting point and the end point doesn't really matter. For us, what matters is that we have the same magnitude and the same direction for our vectors. So this means that for me, the vector being here and the vector being here doesn't matter. When I scale it with 2, I can be here. With 3, I can be here. So this is the same as my B, only 3 times B. This is basically scaling B with 3. And this in here means that my beta 2 is simply equal to 3. And then this means that I can combine this with my A, which was in here. You remember? So this here. This means that I get yet another linear combination of these vectors, which means that I'm taking 3B and I'm adding on this my A, so 1 times A. My beta 1 is equal to 1, my beta 2 is equal to 3, which means that the linear combination of this is equal to 1, 2 plus, and then 3 times B is equal to 0, and then 3 times 3 is 9. This is then the new linear combination, which is 1 and 11. So the new linear combination is equal to 1 and 11. So this thing, which is the same as this thing. And then you can go on and on. You can also calculate the same with a negative B. So you can take B and then you can scale it with -1. So this is minus B. Or you can go in here. The same holds for A. So you can scale it all the way to here or in the negative side. So this already give us the idea that we will go into the next point, which is the span. So when it comes to the linear combination, and in this specific case, when we have these two vectors, we can combine these two vectors in any way, and we can mix them up by using different sorts of coefficients of beta 1 and beta 2, and we can get any vector in our R2. So this means that any vector in our R2 we can represent by using only these two vectors. And this is not always the case. For this specific case, we are dealing with two vectors that we can use to represent any vector in our R2. So what I mean here is that, let me clean this up. So independent what kind of vector you will give me in the R2, so it has two different elements, it is 2 by 1, I can use a linear combination of A and B. So a linear combination of A and B is beta 1 times A plus beta 2 times B in order to represent this vector, x1 and x2. Therefore, we are saying, and we will come to this in the next slide too, that the span of the vectors A and B, so this is the set of all possible combinations of these two vectors, is equal to R2. Because any vector in R2 can be represented as a linear combination of these two vectors. So we have a linear combination of A and B, and I'm saying that I can represent any vector. So here, vector x, and this vector x I'm representing by x1 and x2, and x1 and x2 can be any real numbers. So x1 and x2, they belong to R, and x is simply a two-dimensional vector. So x1 and x2, those can be any numbers, 0, 1, 2, minus 100, anything. And I'm saying any number in this two-dimensional space, so whether it is this one, any vector, this one, or this vector, or this one, any vector that you give me in two-dimensional space, I can find a linear combination of this A and B that is equal to that vector. So I can represent that vector as a linear combination of vector A and B that we saw before. So let's actually prove that. So I'm going to represent this x1 and x2 by a linear combination of this vector A and B. And how we can do that? So we have beta 1 times A plus beta 2 times B. It is equal to x1 and x2, where beta 1 and beta 2, so beta 1 and beta 2, they are constants, so they are also real numbers. So let's unpack this, which is beta 1 times 1, 2 plus beta 2 times 0, 3. And this should be equal to x1 and x2. Now, this is equivalent of, so beta 1 times 1, beta 1 times 2, plus beta 2 times 0, and then beta 2 times 3. And this should be equal to x1, x2. So this is my beta 1 A, this is my beta 2 B, and this is my x. All right, so now what we get is that, and this is equivalent, beta 1 times 1 is equal to beta 1. Beta 1 times 2 is 2 beta 1. Plus, then here, beta 2 times 0 is 0, and then beta 2 times 3 is 3 beta 2. So we have learned from the operations on the vectors that beta 1, so in this case, when we are adding two vectors, so beta 1 plus 0 is the amount that we need to put as our first element. So when we are adding two vectors, we just need to take their corresponding elements, we need to add them up. So this is equal to beta 1 plus 0, and then 2 beta 1 plus 3 beta 2. This is the result. And this should be equal to x1 and x2. At least this is what I'm claiming. So this 0 doesn't matter. So what we are getting from here is that beta 1 is equal to x1, and then 2 beta 1 plus 3 beta 2 is equal to x2. This is the two expressions that we are getting based on all these different calculations. So let me actually remove all this. So we have beta 1 is equal to x1, and 2 beta 1 plus 3 beta 2 is equal to x2. So here, given that we have already that beta 1 is equal to x1, and here we have two unknowns, I'm going to fill in the value for beta 1 in here. So I'm going to take this, and I'm going to fill in it in here. So for this value. So remember that beta 1 and beta 2 are two unknowns, and x1 and x2 are just numbers that we will get when we know exactly the vector, and we just want to represent that vector as a linear combination of two vectors. So when I take this value for beta 1, which is equal to x1, and I'm going to fill that in here, it means that I'm going to get from here that beta 1 is equal to x1, and 2 times x1, because beta 1 is equal to x1, and here I got beta 1. I'm just filling in that value for beta 1, which is equal to x1. So 2 times x1, and then the rest I'm just taking over. 3 beta 2 is equal to x2. Let me remove this, and from here, what we are getting is that beta 1 is equal to x1, and I will solve this equation for the unknown, which is equal beta 2. So I will just take the 3 beta 2 from left-hand side, I will leave it there, and I will take this, and I will take it over to the right. So I'm taking x2 over, and this 2x1, so this part, I'm just taking to the right of the equation. So minus 2x1, which then on its turn is equal to, so it goes to beta 1 is equal to x1, and then beta 2 is equal to x2 minus 2x1 divided to 3. Perfect. So what do we get here? What is our end result, and why is it significant? So what we are getting here is that based on all this information, without knowing beta 1 and beta 2, we got that beta 1 should be equal to x1, and beta 2 should be equal to x2 minus 2x1 divided to 3. This means that independent what kind of x's you will give me, so what kind of vector we have in our R2, so this x1 and x2, they are just real numbers, we can always find beta 1 and beta 2 that we can use to represent that x1, x2, so our x vector, as a linear combination of these two vectors. Let me actually give you an example. So let's remove this. So let's assume we have a vector x, and this x is equal to 4 and let's say 3. So if we got this vector x, and we are saying we can use this vector a and b to represent x as a linear combination of vector a and b, which means that I can find a real number beta 1 and beta 2 that I can use to multiply the vector a and b respectively, combine them together, so they're linear combination that will be equal to this vector x. So this is my x1, This is my x2. So this is equal to 4 and 3. Now, using this, let's actually see whether that is true. So based on this example, my beta 1 should be equal to x1, which is 4. My beta 2 should be equal to x2, which is 3. So beta 2 should be equal to x2, which is 3, minus 2 times x1, which is 4, divided to 3. And what's this number? This means that my beta 1 should be equal to 4, and my beta 2 should be equal to 3 minus 8, so 3 minus 8 divided to 3. And this is equal to minus 5 divided to 3. So this means that I can use a coefficient beta 1 is equal to 4 and beta 2 equal to minus 5 divided to 3 to represent my vector x as a linear combination of vector A and vector B. So let's actually prove that too as a final step. So let's see whether 4 times vector A, which is 1, 2, plus minus 5 divided to 3, whether this is indeed equal to vector x. So my vector B is 0, 3. So this is the first part. And I want to prove that this is indeed equal to x. And we already know what x is. So this is equal to 4 times 1, 4 times 2, plus, and then here we got minus 5 divided to 3 times 0, and then minus 5 divided to 3 times 3. This is equal to 4 times 1 is equal to 4, 4 times 2 is equal to 8, and then here we need to subtract minus 5 divided to 3 times 0 is equal to 0, so this one is 0, and then minus 5 divided to 3, so 5/3 times 3, these ones are cancelling out, and we got 8 plus minus 5. So here the plus and here minus, just to make sure we got everything right, and this is equal to 4, and then 8 plus minus 5 is equal to 3. So you can see already that this amount that we got here is equal to x, which was equal to 4 divided to 3. And this helps us to verify and to know for sure that indeed, while given any vector in a two-dimensional space in R2, x, independent of what this x1 is or x2 is, we can always find a pair of beta 1 and beta 2 that will ensure that the beta 1 A plus beta 2 B is actually equal to this x, where x, A, and B, they are part of R2, and A is equal to 1, 2, and then B is equal to 0, 3. So we can represent any vector in our two-dimensional space as a linear combination of this vector A with elements 1, 2, and vector B with elements 0, 3. And that's exactly what we saw here. Because we could find any vector and we can represent this vector as a linear combination of this vector A and B, this vector as a linear combination of this A and B, this vector as a linear combination, and any vector or a point in this plane we can represent as a linear combination of this vector A and vector B. And in this specific case with this vector A and vector B, we are saying that vector A and vector B, they span R2. So vector A and B span R2. Now we will come to these definitions of the span, and just in general for different sorts of vectors we will see what this idea of span is. But for now, given that we just proved that we can represent any vector in R2 as a linear combination of these two vectors A and B, therefore, we can say, and we usually say it in linear algebra, that the vector A and vector B, they span R2. Before moving on to this concept of spans that we just touched upon in our example, I wanted to quickly go back to this example that I promised to discuss, which was part of the definition of the linear combinations and unit vectors. Because we saw in our definition, and let me just show you, that the definition was providing these two highlights, these two bullet points, and was saying any vector B in n dimensions can be expressed as a linear combination of the standard unit vectors E1 to up to En, and the coefficients in this combination are the entries of B itself. So let's look into the example and see what we mean by that. In this specific example, we have this vector B. It is coming from the three-dimensional space, which we can see given that we have three entries. So three elements in our vector, so it's 3 by 1. And this means that B belongs to R3. And in here we can see that B can be written as a linear combination of these three vectors. So you can see that B is equal to minus 1 times this vector, 1, 0, 0, so this one. Then we have plus 3 times 0, 1, 0 vector, so this one. And plus 5 times this third vector, which is 0, 0, 1. Now, we already know from the unit vectors that E1 is equal to 1, 0, 0, assuming that we are in three-dimensional space. E2 is equal to 0, 1, 0, and E3 is equal to 0, 0, 1. You can notice that that's exactly what we got here. This vector is E1, this vector is E2, and this vector is E3, where E1, E2, and E3 belong to three-dimensional space. Okay, so another thing that we can see is that here we got coefficients minus 1, here 3, and here 5. So this is basically our beta 1, beta 2, and beta 3 using the common conventions that we saw before when describing the linear combination. So let's actually check that, and then we will comment on these values. So let's check whether minus 1 times E1 plus 3 times E2 plus 5 times E3 is indeed equal to this B. So this is equal to minus 1 times this vector gives us minus 1, 0, 0. 3 times this E2 gives us 0, 3, and 0. And then 5 times E3 gives us 0, 0, 5. And this is equal to minus 1 plus 0 is equal to minus 1. 0 plus 3 plus 0 is equal to 3. And then 0 plus 0 plus 5 is equal to 5. Now, what do we get here? We see that this, which is equal to this, it is equal to this vector B indeed. Okay, so now when we have indeed checked that B can be represented as a linear combination of these three vectors, these unit vectors E1, E2, E3, another thing that we can notice, and I'm sure you already did, is that those coefficients, they are not just randomly picked coefficients. Those are the entries of this vector B. So this is exactly what that definition was about. It was saying that any vector B, including this example, in this case, three-dimensional space, can be expressed as a linear combination of the standard unit vectors, E1, E2, E3, etc. So these coefficients in this combination, so you can see that the beta 1, beta 2, and beta 3, which are our coefficients in our linear combination, they are the entries, so these values of the B itself. So the same will hold for 4-dimensional case, 5-dimensional case, n-dimensional case. So this means that if we write this down for a general case, just to ensure that we are clear on this part of the definition, so if we got B vector in n-dimensional space, so it got B1, B2 up to Bn as the elements of it, comes from Rn, then we can represent this B as a linear combination of unit vectors coming from the n-dimensional space. So we got E1, E2 up to En that belong to n-dimensional space, and we can represent this B as a linear combination of these unit vectors. So by using beta 1 times, so this is a common convention of the coefficients, as you might recall, times E1, then beta 2 times E2, blah, 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 plus beta n times En. And what is important here is that this beta 1, beta 2, and beta n, those are not just some coefficients, but we already know what these coefficients are, because we can then represent this beta by taking the values. So those are the entries, the elements of the vector B itself. So it is B1 times B1 plus B2 times E2 dot 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 plus Bn times En, where B1, B2 up to Bn, they are all real numbers. So basically, knowing what this vector is, these elements of this vector, we can always describe and express it as a linear combination of the standard unit vectors. And if you're wondering why is this important, in some cases when performing different operations or working on different algorithms, it just becomes handy to represent your vector as a linear combination of multiple vectors. And in those cases exactly, you can make use of this property of linear combinations to express your n-dimensional vector B as a linear combination of the standard unit vectors, because everything is then down to you. By having this vector B, you will already know what are the entries that you can use as your coefficients, in this case beta 1, beta 2, so those are all these values coming from your vector itself, and then the remaining is also known because you know exactly what these unit vectors are and how they are represented. So here, for instance, the E1 is basically 1, 0, 0, blah, 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 0, and then this is n by 1 vector. Here the E2 is equal to 0, 1, 0, blah, 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 and then 0 here. So n times 1 again, up to the point where you have the En, where you have all these zeros, only the last element is 1. Again, n by 1 vector. So this is the idea behind this second part of this definition, which says that any vector B in n-dimensional space can be expressed as a linear combination of the standard unit vectors E1 up to En. Let's now talk about other concept which is also super important, which is the span of vectors. So by definition, the span of a set of vectors is a set of all possible linear combinations of these vectors. So if V is equal to V1, V2 up to Vk, and is a set of vectors, then the span of V is written as a span V, and it includes any vectors that can be expressed as C1, V1 up to C2, V2 up to Ck, Vk. So basically, it is a common notation to say that if we got, for instance, vectors V1, V2 up to Vn, so we have n different vectors, then we say that the span of V1, V2 up to Vn, that this is simply the notation that we use in order to describe the span of these vectors. And we briefly spoke about this concept of span when we were looking into our example that we saw before. So you might recall these vectors A and B that we had, and we said that the span of A and B is the entire space in the two-dimensional real number space. So we said that span of A and B is equal to R2, where our vector A was simply equal to 1, 2, and B was equal to 0, 3. So we proved that the span of 1, 2, and 0, 3 was the entire R2. And how we knew that? Because we proved that any vector in R2 could be represented as a linear combination of these two vectors. So you might recall that we solved these equations. We saw that independent what kind of x1 and x2 one will give us, we can always use the, we found this amount. Let me see where I can find it back. I no longer have this. So we saw that for specific values of beta 1 and beta 2, we can always get a linear combination of this A and B in order to get our desired vector x. So beta 1 times A plus beta 2 times E will always then be equal to x1 and x2 if our vector A and vector B are those. But of course, this doesn't hold for all the vectors. So not for all two-dimensional A and B, we can say that the span of these vectors is the entire R2. Therefore, to better understand this concept of span and this concept of span of vectors, I wanted to distinguish 5 different cases, one of which we already spoke about, and that is the case when we had this vector A and vector B, and we said that the span of A and B is the entire R2. But we will also look into the case when we, for instance, have a span of the zero vector, the span of a single vector, and the span of perpendicular vectors. We might also look, if there is time left, we will also look into the span of parallel vectors. So let's now look into these cases one by one. So let's say we have a vector of 0. So we have a 0 vector. So this is a very simple case. We will start with the simplest case and we will move on bit to the more advanced cases. If we have a vector A that is a 0 vector, 0, 0, then independent what kind of scalar we will use to scale this. So let's say we define it by C, so C times 0. Independent what kind of scalar we will use, this will always end up being equal to 0, 0. So if C is equal to 0, C times 0 will be equal to 0. If C is equal to 1, C times 0 will be equal to 0. Or C is equal to 100, C times 0 will still be 0, 0. So independent what kind of scalar we will be using, what kind of linear combination we will create from our vector A, this will always stay in here. So the point, the vector will always stay in here in our two-dimensional space. So this is completely different from what we saw before when we could create and we could take any vector in our R2 and we could represent it as a linear combination of these two vectors that we saw in the previous example. So in this specific case, scaling the 0 with independent of any scalars we use, this will not change the magnitude nor it will change the direction of our vector. So no matter how we scale it, we still get 0. This means that the span of 0 vector is just the 0 vector itself. So you can see that independent of what I scale the 0 vector, I always end up with the same 0 vector. So therefore, the span of the 0 vector is equal to 0, because by definition, the span of set of vectors is the collection of all possible vectors that I can reach by performing linear combination. And in this case, I will always reach this 0, 0 vector. So all possible collections of these vectors are the vector 0, 0, which is single vector and the same as the input. So this is the basic case. Now let's move on to a bit more advanced case. So a bit more complicated than this one, but itself also very easy, which is when we got a single vector A. So let's say A is equal to 1 and 2. Now I want to know what is the span of A. In order to know what is the span of A, we simply need to understand what are all these possible collections of vectors that I can get when I'm combining A, I'm multiplying A with different coefficients. So what are the all possible linear combinations of this vector? Because I got just single vector A. So A is 1, 2, which means 1 in here and then 2 here. My A is this vector. And let's look into different scalar multiplications of this vector. So let's say I want to calculate C times A, so the scalar multiplication of this, where C is equal to 2, C is equal to 3, C is equal to minus 1, C is equal to minus 3, and of course C is equal to 1. So in all these cases, when C is equal to 1, then the linear combination, in this case just the scaled multiplication of this single vector A, so 1 times A is simply equal to 1 and 2, so the same vector A. C is equal to 2, this will give me 2 and 4. C is equal to 3, this will give me 3 and 6. C is equal to minus 1 will give me minus 1, minus 2 for my A, and then C is equal to minus 3 will give me minus 3 and then minus 6. So let's plot each of those. So if we got, for instance, C is equal to 1 case, you can see that we already got that vector in here. So it is this vector. When C is equal to 2, then we got this one. So 2 and 4. So where is that? It is in here. Let me use another color. It is in here. When we got C is equal to 3, then we got, so this one, 3 and 6. So this is 3 and this is 6. So it gives me this vector. In the next example, so in the next linear combination, we have C is equal to minus 1, so we got minus 1 and minus 2. So where is minus 1? It is in here. Where is minus 2? It is in here. So I'm getting this vector. And then finally, when I have, let me change the color. When I have C is equal to minus 3, so this case, then I got minus 3 and 6, which means that here is my minus 3. Here is my minus 6. So we got this thing. So you already should see what is going on here. When we got just a single vector for which we need to know what is a linear combination, and that vector is not a zero vector, it has non-zero elements, but it is just a single vector, then all its linear combinations, given that it is simply a scaled multiplication of it, we are all getting them on the same line. So you can see all the linear combinations of this single vector is just a scaled version of it, and it lies on the same line. So what this tells us is that essentially you can move along the line defined by this vector A, but you cannot leave it. So you cannot get a vector that is in here, that is in here, that is in here, in here. So you cannot leave this line. You will always stay on this line. So this line, essentially, span of A, so when we got a single vector, and that vector is not equal to a zero vector, then the span of A is equal to, and this can be expressed as C times A, given that the C is a real number. So we already saw this, independent of what kind of scalar we will take, any linear combination of it will end up simply the C times A. So therefore we are generalizing this and we are saying that the span of A, so the set of all possible linear combinations of this A, is simply equal to C times A, given that the C is a real number. This is basically the span of a real vector in a two-dimensional space. Let's now look into the next case, the next example, when we will calculate or we will define the span of a perpendicular vectors. So let's now look into another example when we are looking for a case when we want to find out the span of perpendicular vectors. So imagine we have these two vectors, vector A and vector B, where A is equal to 1, 0, and then B is equal to 0, 1. So we are still in our lovely two-dimensional space. So let's first visualize the vector A. It's quite basic. It is this one. And then vector B, it is simply this one. So we can already see why they are perpendicular. So you can see that they are forming this 90-degree angle, so right angle here. And then we know that the span, so that's exactly what we want to find out. So the span of A and B, and this is what we want to find out. And we know that the span of two vectors is the set of all possible linear combinations of these vectors. So we want to see what are these all possible linear combinations of C1. So all the possible outcomes that we will get when we get a linear combinations of these two vectors. So basically, C1 times A plus C2 times B. Because those are all the linear combinations of these two vectors. C1 times A plus C2 times B. Nothing that we can see here quickly is that C1 times A, so this part, those are all the scaled versions of A, so scalar multiplications of A. And this second term in the linear combination, those are all the scaled variations, so scalar multiplications of vector B, which means that, and we already have seen this time and time again, that when it comes to vector A, all its linear combinations, they will lie on the same line. So let me take this color. So if I do 2A, so C1 is equal to 2, then I will be in here. If C1 is equal to 3, then I will be here. C1 is equal to 4, I will be here. C1 is equal to 10, I will be in here. And then the opposite holds as well. If C1 is equal to, for instance, minus 2, then I will be in here. If it's equal to minus 5, I will be, my vector will look like this, and so on. So this means that all the scaled multiplications of vector A will lie on this line. So I can also say that the span of A, so span of A is simply equal to C1A. So you can see in here, so on this line basically. So this is C1A. So this basically means independent what kind of C1 I will take, whether it's 1, 2, 3, 0, minus 5, minus 100, I will always end up on this line. So this line. So this is about the scaled multiplication of A. But of course, to create this linear combination of A and B, we also have the second element, which is the all possible scaled multiplications with a vector B, so C2, B2. So let's see what that looks like. So if I, for instance, take C2 is equal to 0, I will be in here. If I take C2 is equal to 2, I will be in here. C2 is equal to 5, I will be in here. C2 is equal to minus 5, I will be here. So you are already seeing what is happening here. So all the possible scaled multiplications with vector b will be on this line. So now we are then getting that the span of b will then be equal to C2 and then b. And here I'm not using formal notation. I'm just trying to draft the idea of the span of vector A and span of vector B, because we are not done yet. We still need to combine the two in order to find the span of vectors A and B when they are perpendicular. So when this angle is simply 90 degrees. Okay, so let's also add this on our plot. So this is C2 and then B. So this already gives us an idea that all the possible combinations of the two, so when we add these two elements to each other, the outcome will always lie on these two lines. But there is no way that we can find any other coefficient for C1 or C2 that can help us to get a value that will be, so a vector that will be in here, or in here, or in here, or in here. That's just not possible. So just you can try to go ahead and solve that equations like we did before, and you will see that there is no way that you can pick here a line and you can represent it as a linear combination of these two vectors. It's just not possible. And later on we will see why. But just keep in mind for now that once we have this type of vectors, when two vectors are perpendicular, then we cannot find a line, a vector that is outside of these two lines. So here you can see the x-axis and the y-axis, but it can also be like this, it can also be like this, but then you cannot find any other line that lies outside of this area that you can create a linear combination of these two different vectors. And then you cannot say that you can create a linear combination of these two vectors A and B. So therefore, when it comes to defining the span of these two perpendicular lines, we say that the span of A and B, given that A and B are perpendicular, but also given that these values, in this case, A is equal to 1 and 0, B is equal to 0 and 1, then their span, you might have already guessed, is equal to C1A plus C2B, given that C1 and C2 are, of course, real numbers. So in this case, C1 and C2, as expected, are just scalars, so they are just some real numbers coming from R. And this A and B, those are vectors that are being spanned. And in this case, specifically, the vector A is equal to this 1, 0, and vector B is equal to 0, 1. And this expression that we see here, this span, this simply describes the set of all possible vectors that can be formed by adding the scaled versions of this A and B, so C1A plus C2B, in order to form this linear combination. So this set of C1A plus C2B, which is a linear combination, all possible linear combinations of these two vectors, so it effectively covers the entire plane, illustrating that any point in 2B space can be reached by some combination of A and B. Let's now move towards our final example that we saw also as part of our definition for the span of vectors, in order to check and to learn how we can usually check whether the two vectors, they really span the entire space. So in this case, we got two vectors. We got vector v1 which is equal to 1, 2, and vector v2, which is equal to 3, 4. So in here, and also we have in our example that it says the span of v1 and v2 is all over the R2, because any vector in R2 can be expressed as a linear combination of v1 and v2. So the example basically is saying that if we know that we can express any vector in R2 as a linear combination of v1 and v2, then we say that the span of v1 and v2 is the entire R2. So let's actually go ahead and prove that from our example. So we have x, which we can represent as x1 and x2, and x1 and x2 are just real numbers. And we got v1, which is 1, 2, v2, which is 3, 4. And we got in our example that we need to prove that the span of v1 and v2 is the entire R2. So for that, what we need to do is we need to prove that we can express our coefficients C1 and C2 in such a way, using x1 and x2, that independent of what these x1 and x2 are, so what kind of x vector we have, whether this is like 1, 2, or this is 0, 4, or this is 1,000 and 5,000, independent what kind of vector we give here, so x1 and x2 values, as long as those are real numbers, we can always find a set of C1 and C2 that we can use as coefficients in order to create a linear combination from vectors v1 and v2. And in that case, we say then the span of v1 and v2 is the entire R2. Okay, so let's go ahead and actually prove that using our previous knowledge that we already gained. So keeping in mind that C1 and C2 are unknown numbers for us, whereas x1 and x2 are just a way to describe those elements in our vector x that will be provided to us. So x1 and x2 will be basically known, and C1 and C2 are the unknowns that we are chasing. So for that, the first thing that I'm going to do is to describe this linear combination that we got here, C1 v1 plus C2 v2, with actual equations, so unknown equations. And the way I'm going to do it is by simply filling in this vector v1 and vector v2 values. So we have C1 and then C2 here, and then here I got 1, 2 plus, and then 3 and 4 here. And what is this amount? So this is equal to, let me actually go on to the next row. So we can create a set of equations for this. So this is equal to x. And we get C1 times 1 plus C2 times 3 is equal to, and remember that this is x, and we said that the x is equal to x1 and x2, so this is basically equal to, we can better write here, is equal to x1 and x2. So this is then equal to, let's not skip all the steps, x1 and x2. So here, then the second elements need to be added, so C1 times 2, and C2 times 4, which is then the same as C1 plus 3C2, and then 2C1 plus 4C2, and then this, we are saying this vector is equal to x1 and x2. So this is what we have here. And let's move from the vectors to equations. So given that we have this, we are allowed to say that this gives us actually two equations. This means that this element from this part should be equal to this, and this element should be equal to this. Now, let's write it down. We see that C1 plus 3C2 should be equal to x1, 2C1 plus 4C2 is equal to x2. This is all that we see in here. Let's remove this to keep the space clean. Now, what this means is that we have two equations with two unknowns, C1 and C2, and x1 and x2 are the numbers that will be provided to us as part of our vector. So what we want to prove is that we can describe and we can express C1 and C2, which are our unknowns, using x1 and x2. So you see here, this is C1, C2. Those are our unknowns, and we want to describe them by using x1 and x2. And very soon we will also see why. So for now, let's try to express those two unknowns using our nouns like x1 and x2. So here I already see that C1 is alone, so there is no scalar. So I will make use of that opportunity to keep the C1 on the left-hand side, and I will take this amount to the right. So I will say C1 is equal to x1 minus 3C2. Okay, slightly better. So I have C1 at the left. I do have x1 in the right, but I also have 3C2 in here. But another thing that you will notice is that in my second expression here, I got 2C1 plus 4C2 plus x2. I want to have the C2 only, because then I will have an expression of my C2 only using x1 and x2, so numbers that will be provided to me, that are known. So for that, what I'm going to do is basically trying to solve two equations with two unknowns. Exactly the same process. So I'm going to take this C1 from the first equation, and I'm going to fill in the second equation. So I am going to say 2 times, and here I'm going to fill in that C1 expression from here. So x1 minus 3C2. So this is my C1, plus just taking over this part. So 4C2 is equal to x2. Okay, perfect. So now what I end up with is C1 is equal to x1 minus 3C2, just taking it over. And then here I'm opening parentheses, which is 2x1 minus 6C2 plus 4C2 is equal to, here I forgot an x2, is equal to x2. Okay, one step closer. Why? Because in my second equation, I no longer have a C1. I only have a C2, which is great, which means that this gives me an indication that I can rewrite the C2, which is unknown, with nouns, with x1 and x2. So let's make use of that opportunity. The first equation I will just take over, so C1 is equal to, and then x1 minus 3C2, and then here I will do 2x1, and then here we got 2 times C2s, which means we can combine them. So minus 6 times C2 plus 4C2, it gives me minus 2 times C2, and this is equal to x2. All right, let's now solve that part. So what I want to have is just this C2 in the left-hand side, which means I need to bring all this to the right, and I need to get rid of them such that I can leave the C2 in the left entirely alone. So this is what I'm basically chasing. For that, I'm going to once again rewrite C1 is equal to x1 minus 3C2, and this time I'm going to take them minus 2C2 here. I'm going to leave that in the left, but then this one I'm going to bring to the right. So x2 minus 2x1. Here I need to be very careful to not make a mistake, because that will mess up my entire calculation. All right, so now we are one step closer, just taking over the first equation again. So C1 is equal to x1 minus 3C2. And here what I need to do to get rid of this minus 2 is to divide the two sides, so both 2 minus 2, because that will help me to keep the C2 only in the left alone, without any scalar. So the C2 is then equal to x2 minus 2x1 divided 2 minus 2. So this is what I end up with. Perfect. So we are very close. Stay with me. So here, what we are getting is that C2 is equal to this amount. We see that now we no longer have any other C's in here, which is great. And remember that x1 and x2 will be numbers that it will be provided to us. I just wanted to keep everything general. And then another thing that I want to fix is this C2. Because the C2 is an unknown, and I want to fill in this value of C2 in here, such that for the C1, I will have a similar picture. So in the left-hand side, I will have C1. In the right-hand side, I will express the C1 with known numbers, so x1 and x2, but not the C2 or others. All right, so let's then go ahead and do that. First, I will write C2 in a simpler way. So C2 is equal to, here I got a minus. I will just write here minus. So I will take the minus over here, and then I will write x2 minus 2x1 to be super careful with this minus. Therefore, I'm using parentheses. So now I'm going to use this C2, and I'm going to fill that in here. So C1 is equal to x1 minus 3 times. I can also make it plus because minus of here. So minus of here and minus of here will cancel out. Therefore, I will do plus 3 times and then x2 minus 3x1 divided to 2. And this then gives me C1 is equal to x1 plus 3 divided to 2 times x2 minus 2. Almost made a mistake. 2x1. And then C2 is equal to x2 minus 2x1 divided to 2. And here we got minus. Perfect. All right, awesome. So now we have expressed x1 and x2. Well, careful with this. x1 and x2 with only known numbers. Now what I'm going to do is that I'm going to prove that independent what kind of x we will be taking here, we will end up getting the C1 and C2 using this, what we just found here. That will give us a linear combination of these two vectors that will be equal to that x. So for that, so to prove that the span of V1 and V2 is the entire R2, I need to prove that independent what kind of x I will take, so x1 and x2, I can always find the C1 and C2 that I just calculate in here using that x1 and x2, that I can then use to combine with my V1 and V2 to find the linear combination of these two vectors with that C1 and C2, which will be equal to this x. So for that, what I need to do first is to take such a random x. So let's say my x is equal to 0 and 4. This means that my x1 is equal to 0 and x2 is equal to 4. What this means is that this gives me C1, which is equal to, and here x1. So I'm basically filling these two values for here to obtain my C1. So C1 corresponding to this specific vector x. So x1 is equal to 0, which means I end up C1 is equal to 0 plus 3 divided to 2 times x2 is equal to 4. So 4 minus, and then 2 times x1 is equal to minus 2 times 0, which is 0. And then C2 is equal to minus, and then x2 is equal to 4. So 4, and then minus 2 times x1 is equal to 0, 0, and then this divided to 2. Now, what are those numbers? So C1 is equal to 3 divided to 2 times 4, which is 3 times 2, so 6. And then C2 is equal to minus 4, and then minus, so this is 0. This cancels out, which means 4 divided to 2 is 2, and then C2 is equal to minus 2. So basically, I have calculated the coefficients C1 and C2 by just knowing what is this vector. So knowing x, the provided x1 and x2, I have calculated my C1 and C2 using my derivations in here. So let's now get rid of this calculations to clear some space and to do the final part, which is compute the linear combination of vector v1 and v2 for this specific coefficients while knowing what this given vector now is, this example random vector. So the C1 is equal to 6, which means 6 times, and then vector v1 is 1, 2. So this is first part of my linear combination, plus, and then C2 is equal to minus 2 times, then here 3, 4, what is this? This is equal to 6, and then 6 times 2 is 12, plus, now let's calculate the second part. Minus 2 times 3 is minus 6, and minus 2 times 4 is minus 8. So what does this give us? 6 minus 6 and 12 minus 8. This gives us 0 and 4. Nice. So this confirms that we have done everything also correctly, which is great because we have seen that using this C1 and C2 that we have just calculated, we have successfully computed the 6v1, so linear combination of this two vectors v1 plus minus 2, minus 2, and then v2. And we have seen that this linear combination is equal to 0, 4, which is exactly our x. So in this way, we have proven that independent what kind of vector we will pick, what kind of x we will pick here, we can always find and calculate the corresponding coefficients C1 and C2 in the same way as I just did. And then by using those, when we calculate the linear combination of these two vectors with these specific coefficients, this will be exactly equal to x. And this proves that independent what kind of vector we have in our R2, we can always express that as a linear combination of the vector v1 and v2. And this proves, and this concludes our proof that span of v1 and v2 is the entire R2. All right, so we are very close to finishing up this unit. So the next topic we are going to talk about is the linear independence. And all this important stuff that we learned as part of the previous modules are going to become super handy as part of this specific concept. So we just spoke about the idea of span. We have plotted a lot of vectors. We have seen the linear combination of that and how we can find out whether the span of multiple vectors is the entire space, for instance, the R2, or it is just the line, or it's maybe the zero vector. We have seen many examples and many operations. We have also seen this idea of unit vectors, and we are finally ready to come to this very important concept, which is a concept of linear independence. So, by definition, linear independence says that a set of vectors is linearly independent if no vector in a set can be written as a linear combination of the others. Otherwise, they are linearly dependent. So vectors v1, v2 up to vn are linearly independent if and only if the only solution to the equation c1 v1 plus c2 v2 plus cn vn is equal to 0 is c1 is equal to c2 up to cn is equal to 0. In other words, in a linearly independent set, the equation c1v1 plus c2v2 plus cn/vn is equal to 0 has only the trivial solution where all ci's are zeros. So now, what do we mean here? There is a ton of information in this definition, so let's unpack them. Firstly, it's really important to keep in mind this idea of independence and dependence. Independence and dependence, they are things that we commonly use in data science, in artificial intelligence, in statistics. So those are really important. So we basically have linear independent condition. So there is a certain condition that our vectors should satisfy, vectors in our set, in our vector space, for them to be named as linearly independent. And otherwise, we are calling them linearly dependent. And you can see that here there are a couple of parts as part of this definition. First, it talks about being unable to recreate a vector in a vector set while using the remaining vectors in our set. So it says, if you can use the remaining vectors in your vector space and create a linear combination of them, so linearly combine them, and we have already seen the definition of linear combination. So if we cannot create such linear combination from the remaining vectors to get our target vector, then we are saying that we have linearly independent vectors. So if we want to say that all our vectors in our vector set, they are linearly independent, it means that each of those vectors we should not be able to recreate out of the remaining vectors. So we should not be able to find coefficients to create linear combination using the remaining vectors in order to get our target vector. Now, what do I mean by this target vector? What do I mean by this linear combination? I will come to this in a bit. For now, let's just try to unpack this definition. Because with examples, we will definitely go through this step by step in detail, such that this idea of linear independence and dependence is super clear. So in the second part of the definition, it says vectors v1, v2 up to vn are linearly independent if and only if the only solution to the equation, and we have here in the left-hand side, you might recognize the linear combination of our vectors v1 up to vn. So in the right-hand side, you have 0. So you are saying our linear combination of vectors is equal to 0 if and only if c1, c2 up to cn is equal to 0. So linear independence basically claims that we will have linearly independent vectors only if and only in the condition when the only way we can create linear combination of these vectors equal to 0 only if those coefficients are 0. There is no other way that we can get a linear combination that is equal to 0 while those coefficients are not 0. So the only way that we can get a linear combination out of all our vectors equals 0 is only when all of the coefficients c1, c2 up to cn is equal to 0. That's something that we will come later to this again. This is something also that we are going to come back in our next module and the next one. So this one will be also super clear once we go through those modules. But for now, keep in mind that the linear combination of all these vectors can only be 0 in case when all these coefficients are equal to 0. So, and then we have the third part in our definition, which says that, in other words, in a linearly independent set, the equation c1 v1 plus c2 v2 up to cn vn is equal to 0 has only the trivial solution where all ci's are 0. So this explanation is basically what we just spoke about as part of this second part. where we said that only in case the coefficients are all 0, we can have a linear combination of our vectors v1, v2 up to vn, which is equal to 0. And why we would like this linear combination to be equal to 0? Because it's a common way to find solution to our linear system. So this is something that we will also see as part of the next module when we will be discussing the idea of solving linear systems. We will go into more advanced topics. But for now, in order to understand this idea of linear independence, we should just keep in mind that we cannot find any CIs, so C1, C2, so any coefficients that is not equal to 0, and then expect that the linear combination of these linearly independent vectors is equal to 0. So that's the if and only if part, which means that this holds from both sides. On one hand, we have v1, v2 up to vn, which are linearly independent only if the linear equation, so the linear combination of all these vectors is equal to 0 if all these coefficients are 0, but also the other way around holds as well. So if we have a linear combination that is equal to 0 only if those coefficients are 0, that means that we are dealing with a linearly independent vectors. This is the if and only if part, which means that we have these conditions from both sides. If one holds, the other one holds, but also the other way around. All right, so let's now look into specific examples that will make our journey in understanding linear dependence much more convenient. So let's say we have our coordinate system, and we have these two different vectors. So we have vector, let's say, 2 and 3, which is our vector A, and we have a vector B that is equal to 6 and 9. So those two are our vectors, and what we want to understand is whether those two vectors are linearly independent or linearly dependent. So one thing that you can quickly notice is that B looks quite similar to A in terms of its scales. So there is a way that we can recreate vector B by using vector A. Now, you can see that if I take vector A, which is equal to 2, 3, if I take vector A and I multiply it by 3, so 3 times vector A, this is a scalar multiplication, then what I can get is 3 times, and then I have here 2, 3, and this is then equal to 3 times 2 is 6, 3 times 3 is 9. This gives me 6 and 9, which is our vector. Now, another thing that you can notice that is exactly my B. So you can see that those two are similar, which means that 3 times A is equal to B. Now, what this means is that I can recreate vector B by using vector A. So in our definition, we saw that a set of vectors is linearly independent if no vector in the set can be written as a linear combination of the others. So here I can take this 3A as a way to write down a linear combination. So 3A plus 0 times B is then equal to B, which is basically saying 3A is equal to B. So by using these two vectors in a set, I can then create a linear combination of the two. And actually, even basic way of writing this is saying I can use the vector A to write a linear combination from this. So 3A is a linear combination. So just a scaled multiplication in this case, of course, but if we have just two vectors, our target vector is B, and I want to write this, I want to see whether I can rewrite the vector b as a linear combination of the remaining vectors, which is vector a. So I can then write vector b as a linear combination of vector a, because I can say that 3 times a is equal to vector b. So this means that vector a and vector b, they are linearly dependent. This means that I can use vector a to recreate vector b. And of course, I can also do the other way around, right? What I can do is that I can just take vector b. So I can take vector b. I can multiply it by 1 divided to 3. 1 divided to 3 is a real number, so I'm just performing a linear combination using b. And this will give me 6 divided to 3 is 2, 9 divided to 3 is 3, and I'm getting exactly what I have under a. So I can then also rewrite vector a by using vector b. So I created a linear combination using vector b in order to get a vector a. And that's exactly the opposite what we have learned here, because we should not be able to write these vectors using the other ones in our set, because otherwise we have a linearly dependent set. Therefore, we are saying that vector a and vector b, they are not a set that is linearly independent, but they are linearly dependent. Before moving on to another example, I also wanted to visualize these vectors just to see what is going on with this pen and how the two linearly dependent vectors look like in R2. So this is our R2. We have a vector A which has 2, 3 elements. So we know already the magnitude and the direction. This is 2, this is 3, which means here, let me actually use another color. So 2, 3, which means this is my vector A. And then my vector B is simply 6 and 9. So it is this one. So you can already see what is going on. So this is vector A, and this entire thing is vector B. And you can see that those two vectors, no matter how I combine them, I will always get the combination, so linear combination of the two on this line. If I want to get a vector that is, for instance, in here, I can never find a scalars of C1 and C2 in such a way that these vectors, so A and B, they can form a linear combination that will give me this vector. There is no way that I can do that. And that's why we say that the span of these two vectors, so span of A and B with this A and B is this line. And we cannot express any of these other vectors like this one or this one using a linear combination of these vectors A and B. The only linear combinations that we can recreate using these vectors A and B are on this line. So you can see that even if I have two different vectors, I actually just got a single vector because I have 2, 3, and both of these vectors, they are actually scaled multiplication of the other one. So B is equal to, I'm missing here something, 1 divided to 3. So B is simply equal to 3 times A, and then A is equal to 1 divided to 3 times B. So in both cases, they are simply a version of scaled multiplication of this vector 2, 3. So A is simply equal to B times 1/3, and then B is equal to 3 times A. And both of them, they are actually based on this vector 2, 3, on this vector A. So therefore, they both actually form and they span around this single line. And they are both linear, we also call it collinear, and they are linearly dependent. Okay, so let's now move on to the next example where we will have a bit more interesting case, and we will look into this example when we have linear independence. Look into another example, a bit more interesting one, as we want to see whether those two are linearly independent or not. So the first vector that we got is the vector A. The vector A is equal to 6 and 0. So it is this vector. This is vector A. The vector B, it is this one, and it contains element of 0 and 7. So it is this vector. This is the vector B. Now, in our definition of linearly independent vectors, we saw that the idea of linear independence is that the two vectors can only be linear independent if we cannot rewrite one of them by using the other. So this means that we cannot rewrite A in terms of B, and we cannot rewrite B in terms of A. So there is no way that we can scale the vector A to get vector B, and there is no way that we can scale vector B with some scalar in order to get the vector A. So there is no way that we can create a linear combination of this one vector to get the other one, and the other way around. So let's see whether this is the case just from trial and error. We have a vector A which contains elements 6 and 0. For us to go from A to B, that has elements so we need to go from 6 to 0 in this case, and we need to go from 0 to 7. Now, we can automatically already see from the second element that there is no way that we can go from 0 to 7. You cannot find any scalar C that you can multiply with 0 in order to get 7. There is no way that you can do that, because any number, any real number that is a real number, if you multiply it with 0, it will never become 7. And of course, another thing that you can notice here also very quickly is the other way around, right? So here, if you go from this 0 till 6, there is no way you can go from this 0 to 6, because there is no such C that you can take this 0 and multiplying it with that. So here our scalar, and you get this equal to 6. This is just not possible. So what we are seeing here is that there is no way that we can somehow change these vectors. So there is no way that we can scale them in such a way. So this is minus B. So all the scaled version of this, so all the scaled multiplications of vector B, they will always be on this line. And then the same holds for A as well. So all the scaled multiplications of A will be on this line. So then one thing we can quickly see here is that given that those two are perpendicular, the span of A and B is the entire R2. So we can see that by using those two lines, we can recreate any other line in this R2. And this is highly related to this idea of linear independence. And given that we cannot come up with a linear combination using the other vectors to recreate another one, in this case, given that we cannot recreate A using B and we cannot recreate B using A, so no linear combination that exists that we can use to recreate B using A and the other way around, we are saying that vector A and vector B are linearly independent. Let's now look into another example that will clarify this linear independence concept. So we have three different vectors, and the first vector is vector A, 1, 0, 0, vector B, 0, 1, 0, our second vector, and the third vector, 0, 0, 1. You can notice that we are in R3. And then the example goes on and it says that those three vectors are linearly independent. And as an explanation, we have that there is no way to add these vectors together with any scalar multiples to equal the zero vector unless all scalars are zero. Now, before even going on to the next part, it's actually very quickly provable that those three vectors are linearly independent, and you cannot create a linear combination of one using the remaining of the two. Let's look into this example in more detail. So we have three vectors, A1, B. So we got A, B, and C, which are 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now, you can quickly see that if we are in R3, and this is actually our unit vector E1, this is our unit vector E2, and this is our unit vector E3, because in that positions, we got our 1s, and the remaining, they are all 0. And this is actually very similar to the previous example, because we can quickly see how we will not be able to recreate one vector using the other ones by even looking at the positions of the zeros. So for us to recreate vector A, which is equal to 1, 0, 0, it means that we should be able to find a linear combination C1, C2, and then using these vectors, this is the vector B, 0, 1, 0, plus C2 times vector C, which is 0, 0, 1. So, in here, basically, we are already seeing a problem because we have here an element 1, and we somehow need to be able to find C1 and C2 in such a way that 1 is equal to C1 times 0 plus C2 times 0. But we know that there is no C1 and C2 that we can find such that this expression actually is true. Because C1 and C2, they should be real numbers, and there are no real numbers that we can find to multiply with 0, such that this will end up to 1, because this is always equal to 0. And we basically get 1 is equal to 0, which is not true. And of course, the same holds the other way around. You can prove that B can never be recreated by using the linear combination of A and C. And also the C can never be recreated by using a linear combination of A and B. Therefore, we are saying, given that A can't be written as linear combination of B and C, B can't be written, so the same, only this time A and C, and then C can't be written as linear combination of A and B, those vectors A, B, and C, they are linearly independent. And even stronger, you can actually go ahead and prove that the span of these three vectors is the R3. But that's outside of the scope of this example, so we will just pass, but I will leave that to you to prove. Alright, so now when we are done with that, let's actually move on to the last module, which is the dot product and its applications. So the length of a vector in dot product is a concept that we are familiar from the high school. So the length of a vector is deeply related to this dot product idea. The dot product of a vector v with itself gives this square of the length of v. What basically it means is that this dot product of vector v, so this thing, which means take the vector v and multiplying it with the other vector v, is simply equal to the square of a length of v. So this is way to express the length of the vector v, and once we square that, that is the dot product. So that's basically this definition what it's about. So we know what this definition of the distance is, and we define it by this, and then we take the square of that distance, and that is our dot product. And we are going to see this idea of dot product a lot, especially when it comes to matrix multiplications, vector multiplications. Also, in many applications of linear algebra, you will see this idea of dot product coming again and coming back to us. So this is a concept that we really need to understand. So in the two-dimensional space, let's say we have a vector v, which is consisting of these two elements x and y. Then the dot product and the length are related by v by v. This is the way we denote the dot product. So we just simply use the dot. And the name also makes sense because we are saying we are using the dot to perform dot product. So we are multiplying the two. We are creating the product of this vector with itself. And this is equal to x squared plus y squared, which is equal to the squared of the distance of this vector. Now, you might recall from the high school that we have learned this idea of distance. So if we have x-axis, y-axis, then we basically use this x squared plus y squared to get the the formula from our circle. And then we have the x squared plus y squared. We take the square root of it, and then this is our distance. So once we take the square root of that, from this square root of x squared plus y squared, then we are simply getting this to cancel out, which is equal to x squared plus y squared. So this is highly related to this idea because we are again talking about distances, and we are simply taking the distance, we are squaring them up, and then we are getting the dot product. So the double straight lines, this is just a notation that we use, and we spoke about this also before. This comes from the pre-algebra, and this is highly important and related to this idea of Pythagorean Theorem and how we compute the distances. So for instance, when we have this square triangular, so we have this rectangle here, and we have here the 90 grade. So here we have the right angle, and here we have our C, which is the side right in front of this 90-degree angle, and here we have the A and the B, and we say that C squared is equal to A squared plus B squared. And if I were to actually write this in terms of x and y, so if this side is x and this side is y and this is my z, let's say, then z squared would be equal to x squared plus y squared. And this is something that we can see here too. And the two terms are highly related. So the z squared is equal to x squared plus y squared. And this is simply equal to z times z, right? And this is something that we know from high school. Welcome to the module 1 of this new unit, when we are going to talk about matrices as well as linear systems. So those are all fundamental concepts that you will see time and time again when applying linear algebra, not only in mathematics but also in applied sciences like data science, artificial intelligence, when training different machine learning models and trying to see what is this mathematics behind machine learning models, different optimization techniques, when you want to solve different problems using linear algebra. So in this first module, as part of Foundations of Linear Systems and Matrices, we are going to introduce this concept of linear systems. And then we are going to talk about the general linear systems. We are going to see this common labeling of the coefficients, this idea of indices that refer to the rows and the columns. We are going to see what is this differentiation between homogeneous and non-homogeneous systems. So without further ado, let's get started. So the linear systems form the bedrock of linear algebra, modeling this array of problems. Thanks to these advancements in these linear systems and solving it in computing, we can now solve a large amount of problems in a very efficient and a fast way. So the general linear systems can be represented by this set of m equations with n unknowns. In the previous unit, when we were looking into this linear combination of vectors, we saw this notation, which was a1, and then we had c1 multiplied, or rather, let me keep the same notation. So we had this linear combination of vectors. So we had beta 1, and then we had a1 plus beta 2, and then a2, and those are all vectors, plus a3, so beta 3 times a3, dot, 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 and then beta m times am. This is the notation that we saw before. And we said we wanted to come up with the linear combination of these different vectors a1, a2, a3 up to am. And then we use that in order to get a sense of whether we are dealing with linearly independent variables, vectors, or linearly dependent vectors. And then we also commented on the span that these vectors take. Now, when it comes to the vectors and just in general linear systems, we can represent what we had before now in terms of with a bigger system. So in terms of m equations and with n unknowns. So here what you can see here is that we have m different equations. So we have beta 1, b1, b2 up to bm. So you can see it in here. And then each of these equations, it contains n unknowns. So you can see that the unknowns, it stays the same. So the unknowns are those x1, x2 up to xn. So x1, x2 up to xn are the set of all n unknowns. And then m equations that you can see in here are all these equations. So a11 x1 plus a12 x2 dot dot dot, and then a1n, and then xn is equal to b1. And here, one thing that is really important to keep in mind is that the indexing is what we need to focus on. So we need to keep this one in mind, this aij. and this xi. So this is something that we also spoke about when discussing the linear combination of vectors. We slightly touched upon on this topic. So let's now dive into this indexing. And how do we index this A, I, J? What are these A's? What are these J's? And here you can see that we have A11 and then A12 and then up to the A1n. And this is in our equation 1. And then we have in our equation 2, A12. Let me actually write this with a different color. So in our equation 2, we got A21, A23 up to A2n. And these A's that you see here, those are just real numbers. So A11 can be 1, A12 can be 3, A1n can be 100. And then the same also holds for this B1, for this B2, and for this Bm. And all these values, A's and B's, they are just real numbers. The only unknowns that we got here are those. So the x1, x2, up to xn. All right, so what about the indexing now? So we got A, I, J, and as you can see, in this case, the first thing that we can see here, it stays everywhere the same, which is the 1. So we got here 1, we got here 1, and up to the point we got here 1. Whereas the second index, this one, it does change. It grows gradually with 1, and it goes from 1 to 2 and up to n. So you can see here that the first index or index I, it goes from 1, it doesn't change, it's just 1. So it is 1, 1, and 1. So here, in all cases for this equation, I is equal to 1. But another thing that you can notice here is that the index 2, unlike index I, so the second index, which is the j, so you see here that the second index is referred as j. This is a general way of defining the indices. So here, j is equal to 1, 2, ... and then n. So basically, the I doesn't change in the same row, but the j changes. And then, of course, we have slightly different in terms of I, but then the same for j for our second equation. So here, I is equal to 2, and then j is again equal to 1, and then 2, ... and then n. And then here, up to, for the last equation, our I is equal to m, and then our j is again equal to 1 till 2, ... So you might notice that I was looking at this from the row perspective. So I was saying per equation or per row, the I doesn't change, but then the j stays the same, and then it is either 1, 2 up to n, but the set is the same. So it contains all these different elements here. So 1, 1, 2, and then n, but it contains all these different real numbers going from 1 till n, because we are combining and we are creating this combination, the sum of all these values, a11, and then x1, a12, x2, a1n, xn. And another thing that you can also notice here is that here with the second index, so with this j is equal to 1, then here the x's corresponding index is also 1. When the j is equal to 2, then the x's corresponding index is also 2, and then here the same story. And you will notice that while the coefficient contains two indices, 1, 1, 1, 2, or 1n, which are the two indices for the coefficients. For the unknowns, we got just single index, which goes from 1 till n. So basically, for a's, for the coefficients, so I, let me write with the right color. So I can be 1, 2, all the way to m, whereas in case of j, it can be 1, 2, all the way to n. And the indices are basically used to help us to keep track of in which row we are and what is the variable that the coefficient belongs to. Because knowing this second index, this helps us to understand that we are dealing with a coefficient that corresponds to this first unknown, the first variable x1. And then the same holds in here. As you can see in here and in here, we are dealing with the same variable x1. Therefore, the second index, the index j, is then the same both in the first equation and in the second one. In both cases, it's equal to 1. Okay, so now when we are clear on that, let's also understand this high-level concept, because you will see this system of linear systems, this m equations and n unknowns, appearing a lot not only in terms of calculating and finding the solution to this linear system, but this actually has a very common application when it comes to running regression, linear regression specifically. And one thing that you can notice here is that here we got also this b1, b2 up to bm. And you will notice that here the index also goes from 1, but then this time to m. So when it comes to the rows, we have m rows or m equations. Therefore, we also expect when it comes to counting from the top that at the bottom we will see an m. Whereas if we count from this side, so kind of like, imagine it like a column, then we see that it goes from 1 till n. So those are common abbreviations and reference to number of observations and number of features that you will see in your data when dealing with data analysis or modeling data. So just keep those things in mind, this abbreviation of m and then n, m equations and unknowns, because this will become very handy. And the same also holds for this indexing. Just to keep in mind that this I and this j, what those indices are, and how, for instance, the first, the first index changes when we go from up to the bottom, and how the second index j goes and it changes when we go from left to the right, when we go through the columns. But we are going to see this also in the upcoming slides, so we will have time to practice it. So this is what we are calling a coefficient labeling. The coefficient a, I, j, so this thing, in a linear system, they are labeled where the first index represents the row and the second index denotes the column. So when we see a, I, j, we know that this refers to the row and the j refers to the column. So this is something that we use in order to understand where exactly in our matrix, something that we will see very soon, where exactly our unit or our member that is part of our matrix, where exactly is that located, in which row and in which column. The systematic labeling is super important because this helps us to keep the structure, and this helps us to understand what does this coefficient represent. What is this row that it belongs and what is the column it belongs. So for which equation and for which unknown we have already solved the problem, such that we can know what this coefficient represents. So before moving on to the actual linear systems and this definition of matrices, let's quickly understand this distinction between homogeneous and non-homogeneous, because this will help us to also get an understanding how we can solve a system of linear systems. So a system is homogeneous if all the constant terms bi are 0. Otherwise, it's non-homogeneous. So identifying this helps us to really understand the nature of the solution set that we need to get and to understand what kind of strategy we need to use in order to solve this problem. Now, what do I mean by bi? We just saw that we had this system of m equations with n unknowns. And we saw that we have in the right-hand side this b1, b2 up to bm, which means that we had this m different equations with n different unknowns. And to find a solution to the system, it means finding these values corresponding to x1, here x2, xn. So basically finding the set of x1, x2 up to xn that solves this problem. And for us to know how to solve this problem, we need to know whether this b1 is equal to 0 or not. This b2 is equal to 0 or not. And then this bm is equal to 0 or not. This is very similar to this idea of solving any sort of problems that contain unknowns. For instance, if we have 3x is equal to, let's say, 5, solving this is entirely different than if we know that the 3x is equal to 0. So this is a super simplified version, of course, but the idea is the same. Knowing that this b1, b2 up to bm, these are 0, this gives us an idea how we can solve this problem. And later on, we will see this distinction between non-homogeneous and homogeneous system. And whenever these b's, so whenever this b1, b2 up to bm, whenever these b's are 0, then we are saying that the system is homogeneous and we need to solve a homogeneous system. Otherwise, we are dealing with non-homogeneous system. So this means that the bi's are not all 0. Let's now move on to the second module, which is about the matrices. So we are going to define the matrix. We are going to see the definition of it, as well as the notation, this idea of rows, columns, dimensions, some of which we have already touched upon, but we are going to go into the depth of it. We are going to learn properly, as well as we are going to see many examples. Then we are going to talk about matrix types. So here we will talk about identity matrix, diagonal matrices, and also special type of matrices, like matrices containing only zeros and only ones. So by definition, a matrix is a rectangular array of real numbers that are arranged in rows and in columns. For example, an m by n matrix A can be represented as follows. So let's look into this definition and this reference to matrix. We call this matrix or matrix A, and every matrix, it can be described by these rows and columns, where we always have this way of describing this matrix always should be defined by the number of rows and number of columns. So this is super important. And let's look into this specific matrix. So we have a matrix A, and all these values, they are members of this matrix. They form the matrix. And we already saw this labeling of A, I, J, where we said that I is referred to the row. So you might recall that those were all these equations that we got. So this horizontal lines where I was equal to 1, I was equal to 2, I was equal to 3, up to the point of I was equal to m. And then we had the j, so this thing, and then J was referred to the columns, and we had J was here 1 and then 2 and then 3 up to the point of N. So 1, 2, 3 and N. This is exactly what you can see here. So in this matrix, we got all these elements. A11 is a number, A12 is a number, up to the A1n is a number. Those are all real numbers. And one thing that you can notice here is that here we got A11. So this is our first row and first column. Here we got A12. This is our first row and second column. And then we got up to the point of A1n. Actually, let me just write this down even at a bigger scale such that I can make more notes. So let's assume we have this matrix A, and this matrix A even bigger. And we got all these different elements. So we start with our first row. And here we have A1, 1. So here, the row that I will write with, let's say with blue, the row is equal to 1. And then the column is 1. So this is row 1. This is row 1, and this is column 1. Let me write it with red. This is column 1. This is column 2. This is column 3, ... and this is column N. And this is row 2. This is row 3, ... and this is row M. So in total, I got M rows and N columns. I will come to this notation that I'm putting here later. For now, let's keep track of the rows and the columns to get a good understanding what these indices were about that we just learned. So every time I will also mention this reference to Aij to keep track of this. And also let me write it with the right colors. So AI, this is the row, and J, which is the column. So all the elements I'm just defining by this A because it's just a way to reference a part that comes from a matrix. It's just common way to write the entire matrix by a capital letter A, whereas its members we will write with the lowercase a. So this is matrix A. All right. So here in the second row but first column, we got A, 2, and then 1 because it is still in the first column. And then when it comes to this element, we have here A. The row is the first one because we are in the first row. But then we are in the second column, so this one should be 2. Then we go on to the next element in our first row, so A1, and then 3, and then ... And the last element is an A. As we are still in the first row, it will be 1, the I. But then given we are in the last column, the column index, or the J, will be equal to N, because we got in total N columns. So we are now ready to go on to the second row. So here, given that we already have our first element, A21, this is in our second row and the first column. So the I is equal to here 2 and J is equal to 1. Let's now write down the element in the second row and second column. As you might have already guessed, I is equal to here 1, I is equal to here 2, and then the j is equal to 2. And then we go on to the next element, which is in the second row and the third column. So it's A, the row index is 2, so I is equal to 2, and then the column index is 3, ... And then we got A, as we are in the second row, it is the I is equal to 2, and as we are in the last column, the j is equal to n. Now you might have already guessed when I was writing this down that whenever you are in the row and you move on to all the elements in the same row, the I, so the row index, it stays the same, only you need to update the column index. So here, for instance, you got 1, 1, 1, here also 1. So all the way down in the same row, all 1, which logically makes sense because we are in the same row. So the row index should not change, but instead you should change the column index, like here. Column 1, column 2, column 3, all the way to column n. So those are our columns. ... So let me make this distinction. And those are our rows, as you can see. So this kind of mentally helps us to understand why we are writing all these indices. Over time, once you practice more with this will become more natural. Really quickly remove this. So now I will write the rest very quickly. So as you might have already guessed, we are in the third row. So we have A3. So everywhere I will just write down the A's. So first I will write down the A's, and then the rows. The row index will stay the same as I am in the same row, but then I will increase the columns gradually. So we are in the column 1, and then column 2, column 3, up to the column n. So now the remaining stuff you can actually write down yourself to just practice. Let's now move on to the last row and last column. So in the last row, we got A up to here. And in the last row, the row index is m, which means that here I need to have m, everywhere I need to have m. And then the column index is 1, 2, 3, all the way to n. So this last column is very interesting too. You can see here that we have the opposite of what we have here, because in the last column, we see that the column index is the same, so it is everywhere n. Only the first index, the index of the row, it changes. It goes from 1, 2, 3 up to m, which is of course logical because we said that in the last column, if we are looking at it from the perspective of a column, so all these values, these a's, so all the n's, they are logical because we are in the last column, we are in the same column, but then the row changes. Here we are in the row 1, here we are in the row 2, row 3, up to row m. Therefore, we have also at the end a, m, n. Now, let's talk about this idea of m, n. We said that our matrix A has m as a number of rows and n as a number of columns, which you can see, by the way, also here. So we always refer the dimension of a matrix, so the dimension of matrix A, by these two numbers. So first we always write down the number of rows, in this case m. Then as the second element we are writing the number of columns, in this case n. We are always putting this small x in between to kind of emphasize m by n matrix. And we most of the time use the square braces to showcase that we are dealing with dimension. And in this case, we are saying the dimension of matrix A is equal to m by n. So we are dealing with m by n matrix. This is a common convention used in linear algebra, in mathematics general, but also used in data science, in machine learning, artificial intelligence. So whenever you are dealing with matrices A, it is a common convention to talk about this idea of dimensions. And the idea of dimensions is super important when it comes to the idea of multiplication, multiplying vector with matrix, matrix with matrix. So this dot product, dimensions play a central role in here. So keep this one in mind. Once we get to the point of dot products, this one will become very handy. So let's now look into a specific example where we see simple matrix A. So in this case, you can see that we are dealing with a matrix that has a 2 by 3 dimensions. So like we just learned, 2 by 3 means that we got 2 rows and 3 columns. That's something that you can also see here very quickly. So you have a small matrix. On the small matrix, it's really easy to actually count. So you can see that we got row 1 and row 2, and we got column 1, column 2, and column 3. So this basically confirms these dimensions. Therefore, we are also saying that we have a 2 by 3 matrix. And like usual, we first write down the number of rows and then the number of columns. You can see here that here we have these elements for our matrix. So A is equal to 1, 2, 3 for the first row, and then 4, 5, 6 for the second row. So from this, actually, I think it's a good exercise to just verify our understanding of indices. And from this, we can write down that, for instance, all these different elements, like A11 is equal to 1, A12, which means that we are in the first row and in the second column. So we have this element is equal to 2, and then we got A and then 1, 3. So we are in the third column. So this one is equal to 3, and then A21 is equal to 4, A22 is equal to 5, and then A23 is equal to 6. So this is actually a good way to practice our understanding of indices, our understanding of this matrix structure, and the understanding of dimension of the matrix, which in this case is 2 by 3. So this is yet another different definition of a matrix structure when it comes to the rows, columns, and dimensions. So this is exactly what we just spoke about on our example. And let's just quickly look at the formal definition. So the rows of a matrix are the horizontal lines of the entries, while the columns are the vertical lines. So basically it's saying those are, let me remove this. So the rows are the horizontal line, and the columns are those vertical lines. Those are the columns. This helps us to form these columns. So column 1, column 2, and column 3. Whereas these horizontal lines, it helps us to create the rows. So row 1 and row 2. So then we have the dimensions of a matrix are given by the number of rows and columns it has. So an m by n matrix has m rows and n columns. That's something that we already saw. So let's now look into some special type of matrices. One matrix type is the identity matrix. So we saw before we had this identity or unit vector. Now we have identity matrix. So the two are quite similar. So like before, when we had our unit vectors, we had this, for instance, E1 in 3 dimensions, we had 1, 0, 0. Then we had our E2, which had 0, 1, 0. And then we had our E3, which was 0, 0, 1. So you might recall this about our identity vectors, or we were calling it unit vectors. You might notice very quickly that we have formed an identity matrix IN which is a square matrix with 1 on the diagonal and zeros elsewhere, is basically a matrix that is built using those unit vectors. So here we have E1, here we have E2, and here we have E3. So you can also see that this 3 by 3 matrix, because we got 3 rows and 3 columns. So you can see that here we have on the diagonal, so we call this diagonal. On this diagonal, we have all ones, and in here, outside of the diagonal, they are all zeros. And this is the definition of identity matrix. It is this IN matrix where n is the dimension of a matrix, and given that it's a square matrix, it means that the dimension of it is n by n. So all the rows, so the number of rows is equal to the number of columns. On the diagonal, we have all these ones, and everywhere else we got zeros. And do note that we are forming this identity matrix simply by combining these different unit vectors. So like here, E1, E2, and E3. So let me actually give you yet another example, but of much higher dimension, so of this identity matrix. So let's say we have I, and then this I, let us actually use this notation, IN. So let's say we got IN. What this means is that we got actually this large matrix. It's a square matrix, which means that it is n by n, so it has n as the number of rows. And n as number of columns. So the dimension is n by n. You got n as number of columns too, because it's a square. And let us actually write down that how that matrix looks like. It's a large matrix. The n is the size of that matrix. So here we got on the diagonal, we got 1, here we got 1, here we got 1, dot, 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 up to the last point, 1. And the index of this 1 here, so this is the first row, this is the first column basically. And everything else is simply 0. So here we got 0, 0, 0, dot, 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 0. Here we got 0, 0, all the way down to 0. Here also 0, all the way down to 0. And then here also 0. So everywhere here and here we all got zeros. Only on this diagonal we actually got ones. So basically, by using our common notation, we can say that in the identity matrix, we got A11 equal to A22 equal to A33 equal to all the way to ANN equal to 1. And then when it comes down to the rest of the cases, so all the other observations, let's say A21, A31, or A41, anything. So anything that is not A11 or A22, anything that is not on the diagonal, it is simply equal to 0. We also say in those cases that Aij is equal to 1 if I is equal to j, because then it means that we are talking about item that is on diagonal because both the row index is equal to the column index. Otherwise, the Aij is equal to 0 if I is not equal to j. So this is in a nutshell how a large identity matrix in general can be defined. So let's now move on to another type of matrix, which is the diagonal matrix. So by definition, a diagonal matrix is a matrix where all of diagonal elements are 0. So what does this mean? We just saw example of a diagonal matrix, which was our identity matrix, because identity matrix is an example of a diagonal matrix. And what do I mean by that? In our just seen example, we saw that only on the diagonal we had all these non-zero elements, but the rest were all zeros. So all the off-diagonal elements were zeros, like in here and in here. Exactly the same holds for the diagonal matrices, only unlike in the identity matrix, we no longer need to have this diagonal elements equal to 1. Those can be any other numbers. So as long as we have these elements, d1, d2, d3, that are not zeros, but then of the diagonal numbers, so all these elements, they are 0, then we are dealing with the diagonal matrix. So in this case, we got a 3 by 3 diagonal matrix because we have 3 rows and 3 columns. And here we can see that the first, so the A11, the first element from the first row and first column, is equal to D1. So A22 is equal to D2, and then A33 is equal to D3. So D1, D2, and D3, those are all, so D1, D2, and D3, those are all real numbers. Now, when it comes to these numbers, for example, it can be that D is, let's say, 2, 5, 6 on diagonal, then we have those zeros. This is a diagonal matrix. It can also be that D is equal to -3, and then 0, 0, and then 5, 8, and then here we have zeros. So again, we have on the diagonal all these elements and the off-diagonal elements. So if all the off-diagonal elements are 0, then we are dealing with the diagonal matrix. And if you are wondering, well, what happens if on the diagonal we got zeros? Do we still have a diagonal matrix? It's actually a great question. But yes, indeed, we are dealing with the diagonal matrix as long as all the off-diagonal elements are 0. So, for instance, if we got D is equal to, here we have 0, here we have 0, 0, 0, and then 7, and then 0, and then 8, and then 0, 0. So we got this off-diagonal elements. So here are the diagonal elements, and all the off-diagonal elements are those. Given that all the off-diagonal elements are 0, which is the definition of the diagonal matrix, then we can say that our D matrix in here is indeed a diagonal matrix. Let's now look into yet another type of matrix, which is a special type of matrix, and it's called ones matrix. So by definition, a ones matrix is denoted by 1m1, so you can see here. And here it mentions the dimension of it, so the number of rows and number of columns. And it's a matrix in which all the elements are 1. So this is a very unique matrix. We often use it during the programming, so in data science, data analytics, but also in when creating like data structures, when designing algorithms. This becomes very handy. And this idea of ones matrix is that all the elements are just 1. It means that if we want to create a placeholder in such a way that we can then multiply any number in here with some other number and get that number, then it can be done very easily. Because we know that when we multiply a number with 1, then we get that number. So A times 1 is equal to A. X times 1 is equal to X. Now, this property exactly is what motivates us to create and to have this type of ones matrices. It means that we are defining matrix by its dimension, so it is m by n, and here the m is equal to 2 and then n is equal to 3 because we got 2 rows and 3 columns. but you can see that all the elements are the same and they are equal to 1. So A11 is equal to A12 is equal to A13 is equal to A21 and is equal to A22 and A23, and they are all equal to 1. And this is the definition of one's matrix. You can have one's matrix of the size 4 by 10, one's matrix of the size 1000, let's say 10,000 by 100, etc. So any number, any real number, so m and then n are real numbers you can use in order to create this large m by n one's matrix. Let's now look into our final special type of matrix before moving on to the next module, which is about zero matrices. So similar to this one's matrix, a zero matrix denoted by 0 m by n is a matrix in which all the elements are the same, with the one difference that this time all the elements are equal to 0. So in the ones matrix all the elements were ones, but in the zero matrix all the elements are 0. This type of matrices become very handy also during the programming, creating different algorithms, during design, in coding, but for slightly different purposes. Usually we create the zero matrices as a placeholder, such that in the beginning we can have this tuples, or we can have this arrays or nested loops that we want to perform, and then gradually add these values to the existing empty array. So if we create this zeros matrix, and this is a placeholder, then next time we can always add on this new data that we get, and then we know that 0 plus a number is always equal to number, which means that once we have this updated information of A, we can add this to the 0, and we will then have this new updated information in our system. Therefore, the zero matrix is often used as a way to have this placeholder with the provided dimension, where we can always add new information and the information can be updated. So in this specific case, we got a zero matrix that has 2 rows and 3 columns. So you can see 2 rows and 3 columns. So m is equal to 2 and then n is equal to 3. Perfect. So we are done with module 2, and now we are ready to go on to our next module, which is the core matrix operations. So when it comes to matrices, we often perform matrix additions, matrix subtraction, but also matrix scalar multiplication of this matrix, so multiplying matrix with a scalar, and then matrix multiplication just in general, so taking 2 matrices and multiplying them. We are going to look into this concept in detail. We are going to see many examples like before. We are going to dive deeper into this such that we lay the ground on to the next module, which is solving a system of m equations with n unknowns. So solving this general linear system. So for the beginning, we will be looking into this matrix operations where we are adding or subtracting matrices. So by definition, the sum of 2 matrices, A and B, of the same dimensions is obtained by adding their corresponding elements. So by taking the element ij from both matrices and adding them to each other. So in this case, you can see that matrix A and B are here. And the definition says we just simply need to take the corresponding elements from the row I and the column j, take them, add them, and this will become an element in our final matrix. Because when we are adding 2 matrices of the same size, the result is yet another matrix. So we will use the matrix A to add to matrix B, and this will give us a matrix A plus B. And this ij simply refers to the indices corresponding to the row and the column. We will look into an example in a bit, and this will make much more sense. And the same holds also for the difference. So by definition, the difference of the 2 matrices A and B of the same dimensions is obtained by subtracting their corresponding elements, which means that in order to obtain this matrix A minus B, this is a new matrix, we simply need to look for each element. So we are going to index them for a row I and j. We are going to do this pairwise, element-wise subtractions. We are going to see what is that element corresponding to the row I and column j in the matrix A, which we say is Aij. We are going to subtract from this the element in the row I and column G that comes from matrix B. And this will give us our new matrix, which is A minus B. So let's now look into an example. In this matrix A and matrix B are used, and matrix A is of the size 3 by 3. Matrix B is of the size 3 by 3. In order to obtain A plus B, what we are doing is that we are performing element-wise additions. Now, let's verify this. So, what we are doing here is that we are saying A plus B. Let me actually get a larger area here. So, let's say we have these two matrices. I want to add the two in such a way that we do everything one by one, such that this idea of A plus B and addition of the matrices will make sense. So we want to find out A plus B. For that, what we are going to do is that we are going to make use of this definition that A plus B and then Ij is equal to A Ij plus B Ij, which is a fancy way or mathematical way or describing that for each element we need to go and look for the row I and column j and take that element from the column from that matrix A and from the matrix B. So this means that for A plus B, this is going to be a matrix that will have the same number of rows and the same number of columns as two matrices, because both A and B are 3 by 3, which means also their sum is going to be 3 by 3. So this is going to be 3 by 3. And here we are going to do, so we are going to take for the first row and the first column, so for A plus B, 1, 1, so first row and first column, we need to go to the first row and first column of matrix A and the first row and first column of matrix B, and we need to add these two elements. So we need to do 1 plus 1. And then we need to go on to the second column. So the first row and the second column, which means that we need to be here in both matrices. So here we have 0 plus 2. And then we got 2 plus 3. And then we got 0 plus 0. So you can see it in here. And then we have 1 plus 0. And then we have 3 plus 1. 0 plus 1. And then 0 plus 2. And then 1 plus 3. Which gives us, so 1 plus 1 is equal to 2, 0 plus 2 is equal to 2, and then 2 plus 3 is equal to 5, 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, 0 plus 2 is equal to 2, and then 3 plus 1 is equal to 4, 1 plus 3 is equal to 4, which means that our A plus B is equal to this matrix that we got in here. So you can see that we are getting exactly what we have here. Only we have done it manually, one by one. So the same idea holds exactly when we have A minus B. Only instead of adding, you will have to do here minuses. So minus, minus, so everywhere minus. So 1 minus 1, 0 minus 2, 2 minus 3, etc. So let's look into another addition. So in this case, by definition, it is defined as this element-wise of the adding of these two matrices. Here, the only difference in this definition is that it's calling this A plus B as C. So this new matrix that we are getting as a result of adding A to B, it's calling C. So basically, it's the same as calling this matrix as C. you will see also this type of definitions. So in this case, the matrix C is equal to A plus B, which basically means that for each row with index I and with each column with index j, go and look for row I and index j, take the corresponding elements from matrix A and matrix B, add them in order to get that corresponding element in our new matrix C. And you can see that in this example, that's exactly what we are doing. We have A, we have B. We are taking this element and this one. So 1 plus 1, we are getting here 2. And then 0 plus 2, we are getting 2 here. 2 plus 3 is 5. And then 0 plus 0 is equal to 0. 1 plus 0 is equal to 1. And then 3 plus 1 is equal to 4. So now we already go to the next topic, which is about scalar multiplication of a matrix. So by definition, scalar multiplication of a matrix A by a scalar alpha results in a new matrix where each entry of A is multiplied by alpha. The idea of scalar multiplication in matrices is actually quite similar to this idea of scalar multiplication in vectors. So we have already seen in the lecture of the vector multiplication that when we were having this scalar C and we had this vector A, then when we are multiplying C, which is a real number, with vector A, then we simply need to take all the elements of vector A, so A1, A2, all the way down to AN, and we need to multiply them by this same scalar, so C. This is what we were doing with vectors. And that's exactly the idea behind matrices. And when during the scalar multiplication of matrices, only instead of multiplying only just one vector with the scalar C, now we need to apply this to all the rows and all the columns. So here we got just one column, and matrix is simply a combination of multiple vectors, which means that we need to multiply all these elements of all the vectors of all the columns in this matrix. So let's actually look into a specific example. So in this case, we have a matrix A, and this matrix A is this thing. And we have a scalar which is 3. So in here, our alpha is equal to 3, or you can call it C or anything. So you can see that when we are scaling the matrix with a scalar, in this case 3, with this matrix, what we are doing is that we are simply taking each of these elements and multiplying it with the scalar. So 1 by 3 is 3, 2 by 3 is 6, 3 by 3 is 9, and 4 by 3 is 12. This is the idea behind this entire scalar multiplication of a matrix. In more general terms, if we, for instance, have a matrix A, so let's actually look into a high-level general example when we have the A matrix m by n. So we got m rows and n columns, and we want to get a scalar multiplication of this matrix. And scalar that we have here, as in our definition, it is defined by this alpha. Alpha is just a number. You can call it C, you can call it B, anything. So in this case, our scalar alpha is coming from R, so it's a real number. So alpha times A is then simply equal to this new matrix where all of these elements are simply multiplied by this scalar. So I will just take over all these values, H1 up to AM1, and then A12, A22, all the way down to AM2. And then let me also add the last column, just for fun, here A2N, and then here AMN. So here, this new scaled multiplied, so scaled matrix A, so alpha times A is simply equal to alpha times, so all these elements are simply multiplied by the scalar. It is as simple as that. So that's the simple idea behind matrix scaling. So when you are doing scalar multiplication of this matrix, you simply take all the values and you multiply them element by element, per row and per column, by that single scalar alpha. Do you know that you are multiplying them all without exclusion with exactly the same number, which is that alpha? So let's now look into the definition of matrix multiplication. So here we are no longer multiplying a matrix with a scalar, but we are multiplying matrix with a matrix. So the product of an m by n matrix A and an n by p matrix B results in an m by p matrix C, where each entry Cij is computed as the dot product of the each row of A and the jth column of B. Now, what does this mean? Firstly, let's look and unpack this part of the definition. So, we got matrix A, that is m by n. And then we got matrix B, which is n by p. What this means is that in this case, matrix A has m rows and n columns, and matrix B has n rows and p columns. So this is then simply the dimensions of these two matrices. So then it's saying that by definition, the product of these two matrices, so the product of A and B, the product of the two, B, is equal to this matrix C. And each entry Cij, so Cij, is computed as the dot product of the each row of A and the jth column of B. Now this part might seem a bit difficult, but once we look into the actual example and we illustrate this on our common high-level general expressions of matrix A and B and their multiplication, this will make much more sense. For now, before coming to this one, I just wanted to refresh our memory on one thing. I said before, when discussing also this idea of improving these different properties of vectors, that when we want to multiply a vector with a matrix or a matrix with a matrix or a vector with a vector, we need to ensure that from the first element, the number of columns is equal to the number of rows of the second element. This is also very important for this specific case and just in general for matrix multiplication. So you can notice here that the number of columns here is equal to the number of rows in here. And the order is very important. So in case of matrix multiplication, the order is really important, which means that if you have a matrix A and you want to multiply it with a matrix B, then the number of columns of A should be equal to the number of rows of B. Otherwise, you cannot multiply those two matrices with each other. So in case you got a matrix A that doesn't have the same number of columns as the rows of of the matrix B, then there are some alternative things that you can do, including this idea of the transpose that we saw also doing when computing the dot product between this vector A and vector B. That's something that we also do in programming when we are dealing with this matrix and we want to compute this relationship between two matrices, but the number of columns of the first one is not equal to the number of rows of the second one. We are simply manipulating these matrices or removing some data. If that's not hurting our problem, maybe flipping, so transposing our matrix or applying any other source of operation to it to ensure that the two matrices that we are multiplying with each other, the first one's number of columns is equal to the second one's number of rows. So that's just the law, and that's something that you should follow if you want to multiply these two matrices. All right, so now let's move on to this idea of multiplying and the dot product. Let's look into a specific example, and this will help us to understand this process better. So before doing that, I just want to quickly show you this general idea. So if we have a matrix A that is m by n, which means that it looks something like this, like A1, 1, A2, 1, up to the point of AM1. And then here we got, let's say, A1, 2, A2, 2, up to the point of AM2. And then at the end we got AMN, and here we got A1N. So let me also add this one, 2N, and we got a matrix B. This matrix B is N by P, so it has N rows and P columns. So we are fine in terms of dimension here. And we got here B11, B21, up to the point of BN in this case. Let's not confuse the letters. So BN1, B12, B22, up to the point of BN2, because N now is the number of rows for matrix B, unlike for the matrix A, up to B1P, and here B2P, and here up to the point of B, and then NP. This is the last element. In order to perform multiplication between these two matrices, so to obtain a matrix C, which is equal to A times B, what we need to do is we simply need to take pair case, so pair row. For the row I, for instance, we need to take this element, so this row, and we need to multiply it with this. So we need to find the dot product between this row and this column. Then we need to move on to the next one, and then for the second element, we will then take this row and we will multiply it with this one. So this is then something that we need to do in order to obtain these elements. And you might have already noticed that we got this m by n and n by p, so you might have already guessed what will be the dimension of the C. If we got that the dimension of A is equal to m by n, and the dimension of B is equal to n by p, then the result matrix after multiplying the two, so matrix C, will be having a number of rows equal to this and the number of columns equal to this. So this middle part basically disappears, and the number of rows of the first matrix will be then the number of rows of this result matrix C, and the number of columns of the second matrix, so matrix B, will then be our final number of columns. So we will then have a matrix C that will have a dimension. So dimension of C will then be equal to m by p. So we will have m rows and p columns. So how we are going to compute this? So for Cij, which means row I and column j, let's look into the definition of it. It's saying Cij is computed as a dot product of the each row and the jth column. So each row from A and jth column of B. What is the each row of A? The each row of A is somewhere here. So each row of A, it is the A and then I1, then A, and then I2, and then A, and then I3, dot, 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 and then A, I, and then we got in total n columns. And we always do the transpose, right, when computing this dot product. So we then take the transpose. So we take this row I, and we multiply it. So we do the dot product between this one. This is the AI and the BJ. This is column J. It is somewhere here. So it is B, and then we got the first element, which is 1, and then J, and then B, 2J, B, 3J, dot, 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 up to B, and then in total we got n rows in B, so n, and then the J is the column, so it stays the same. So this is then the dot product between each row that comes from matrix A and the jth column that comes from matrix B. So it's always like that actually. So we always take row by row. So we take this different, so every time we take just a row and we multiply with the corresponding column, and then we get the dot product between this row that comes from the first matrix and then the column that comes from the second matrix in that specific order in order to get our dot product and that specific value. And what is this amount actually? So when we calculate this dot product, you can quickly see that we have A, I1 multiplied by B1J plus A, I2 multiplied by B2J, and then dot, 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 AIN multiplied by BNG. And this new matrix C will then have all these elements. So C11, C21, and then C31, dot, 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 and then C, the last row, as the number of rows of C is M, CM, see here, M. So C, and then here it will be 1, 2, C2, 2, C3, and then 2, up to the point of CM, and then 2, and then here the last column will be C1, and then P is the number of columns in C, so C1P, and then C2P, and then C3P, dot, 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 and then C, M, and then P. Okay. So this is what we get. This is our final matrix C when multiplying matrix A and matrix B. So let me clean this up. C is equal to. Now, if you want to find out what is C11, you can easily fill in this general formula that we just calculated. The I is equal to 1 and then J is equal to 1. And this will give you C11 by using this formula. If you want to get the CMP, then just fill in the I is equal to M and then J is equal to P in order to get this value CMP. So you can already see the amount of calculations you need to do in order to get all these elements from these large matrices A and B. Let's actually look into a simple example to clarify this. So we have a matrix A here and matrix B here. And we want to do a multiplication of the two. And we have just learned how to do it. Let's actually do it one by one. So we got a matrix A, which is equal to 1, 2, 3, 4. With dimensions 2 by 2. Then we got a matrix B, which has values 2, 0, and then 1, 2. So it is 2 by 2. And I want to find what is C that is equal to A times B. And I know already by looking at these dimensions that C is going to be equal to 2 by 2. So you might recall that I said that when looking at this final result, the number of rows or the final matrix will be this. So the number of rows of the initial matrix A, and then the number of columns of this final vector C will be the number of vectors, number of columns of this second matrix B, so 2. Therefore, I know already before even doing calculations that the product matrix C equal to A times B is going to have a dimension 2 by 2. Now let's actually do a calculation to check this. So C is then equal to A times B, and it's equal to 1, 2, 3, 4 multiplied by 2, 0, 1, 2. Okay, so I expect to have 4 different elements here, 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 and here. So to obtain the C11, so it is C11 in here, what I need to do is that I need to look at the first row and the first column in here. So first row from A and the first column of B. And I'm doing the dot product, which means 1 times 2 plus 2 times 1. 1 times 2 is 2, 2 times 1 is 1. So here I'm getting 1 times 2 plus 2 times 1, which basically gives me 2 plus 2, and that's equal to 4. So here I'm just writing down 1 times 2 plus 2 times 1. Now, when I want to get this value, which is C12, this means that I want to get the first row and the second column. And that's exactly what I'm doing. So I'm going back and I'm saying, let's look at the first row, but this time we will look at the second column coming from the matrix B. So 1 times 0 times 0 plus 2 times 2. And then I do the same, only this time for the second row, which means I'm picking this row and then this column. So it is 3 times 2 plus 4 times 1. And for the final element C22, I'm taking the second row and the second column, which gives me 3 times 0 plus 4 times 2. Now, what does this give me? This gives me this 4 by 4 matrix, where 1 times 2 plus 2 times 1 is 4, 1 times 0 plus 2 times 2 is 4, 3 times 2 plus 4 is equal to 6 plus 4, which is 10, and then 3 times 0 plus 4 times 2 is equal to 8. So let's check. 4, 4, 10, 8. That's exactly what we have here. So as you could see here, the idea is that every time to follow what element I'm looking for the Cij, and then I just go to the each rows from the first matrix and the jth column from the second matrix, and I do the dot product of the A and then I and then K, let's say. So I'm going to the each row from the first matrix, and I'm taking all the elements, which means I don't even need to mention this index. It just means the entire each row coming from the matrix A. And then I'm doing the dot product between this row and the column that comes from the matrix B, which means B and then J, which then will give me the Cij. So I'm looking at this and taking this, multiplying this dot product, and this gives me the first element, then the first row, and then the second column, which gives me the second element in the first row in my matrix, so this one, and so on. So hope this makes sense. If it doesn't, make sure to reach out, because it's a very important concept. And let's also look into another example to make sure that we got this right. So in this case, as you can see, we have another matrices. So set of A and B matrices, again 2 by 2, a simple one. And we want to know what is AB. So let's say we call this C. We already know C should be 2 by 2. And what we are doing is basically for C11, we are saying let's look at the first row, so first row, and the first column coming from the second matrix B, and let's do the dot product. So 2 times 1, 2 times 1, 2 times 1, 4 times 5, 4 times 5, we get this. And then when we want to find what is C, what is C, and then 1, 2, so in the first row, but in the second element in our final matrix, so I is equal to 1 and J is equal to 2, it means we need to look at the first row from the matrix A, but this time the second column from the matrix B. So it is 2 by 3, 2 by 3, 4 times 7, 4 times 7. And this gives us a number 34. Even if you calculate, you can see that 2 times 1 is equal to 2, 4 times 5 is 5, so 4 times 5 is 20, so 2 plus 20 is 22 in here. And then you can do the rest of calculations, and this will be a good practice to see how we can do a basic matrix multiplication. The idea is actually quite straightforward. When it comes to multiplying it, it comes with a practice when we see all these much bigger matrices. So this is another example. I will leave this one to you to complete it. Just to keep in mind, we always we always look at the dimension first. In here, 2 times 2 and 2 times 2, which gives me an impression already what I can expect. The result will be 2 by 2. And when it comes to the cross elements, just ensure to always look to the ith row and the jth column. This comes from matrix A and this comes from matrix B. Take them, compute the dot product, and then you will find your your final result. Let's call it Kij, because in this case we have a matrix C already. Welcome to the module 4 of this course when we are talking about matrices and linear systems. So in this module, we are going to dive deeper into this idea of linear systems with matrices and solving linear systems using different techniques. And specifically, we are going to learn the concept behind solving linear systems using matrices named Gaussian elimination and Gaussian reduction. Welcome to the module 1 in this unit. So in this case, we are going to talk about algebraic laws for matrices. We are going to discuss 4 different properties for matrices. And the first one is the commutative law for matrix addition, the associative law for matrices, the distributive law for matrices, both the left and the right one. And then finally, we're going to talk about the scalar multiplication law for matrices. So the algebraic laws for matrices, they are like in case of real numbers, like in case of vectors. They help us to do different operations on these entities. They are very similar to the real numbers and the vector cases, where we, for instance, so that if, for instance, A plus B is equal to B plus C, or A times B plus C is equal to AB plus AC, those are all sorts of laws that we learn as part of high school, pre-algebra, and we have applied it to real numbers. We know how helpful those can be, and similar type of laws we have also for the matrices. And we got in this case 4 different laws that we will be discussing. The first one is what we are referring as associative law. The second one is the distributive law. The third one is the scalar multiplication law, and the fourth one is the commutative law for addition. So these laws help us to do different matrix operations. They help us to manipulate algebraically these matrices. And then this can help us to solve different sorts of problems, including solving a system of linear equations. So let's start with the commutative law for matrix addition. So the matrix addition is commutative, which means that A plus B is equal to B plus A. So unlike the matrix multiplication that we have seen in the previous lessons, where the order did matter, and we said that we had to ensure that the number of columns of the first matrix is equal to the number of rows of the second matrix. In case of addition, this is not the case. So we should not care about the order whenever we want to add two matrices. The other thing that we need to keep in mind, though, is that the two matrices need to have the same size. So I mean that both matrix A and matrix B need to have a dimension. So dimension of matrix A should be equal to dimension of matrix B, and let's say it should be equal to m by n. But for the rest, we don't really need to care which one we will put first. Will we put first A and then add the B, or we will do the other way around? So we will then first take B and then we will add A. So this is the idea behind commutative law for matrix addition. So first let's look into all these laws, and then we will also look into the corresponding examples. So for this specific case, it might actually also be helpful to write down the general formula, which will make sense out of this law for the, which is a commutative law for the matrix additions. So let's say we got a matrix A, which is m by n. And this matrix can be represented as A11 dot 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 AM1. So this is something that we saw time and time again. So I'll just quickly write it down, the common notation for this. And then here we have the last column, which is AMN, and this is the matrix A. Then we got matrix B, which is again M by N, and can be represented as B11, and then dot dot dot, and then BM1 dot dot dot, B1n dot dot dot, BMN. So the commutative law says that A plus B should be equal to B plus A. Let's check that, whether this is the case. Let's first compute this part, and then we will do this one. Well, the first one means that we get, so A plus B is, and we remember how we add matrices, right? So we know that we just need to pick their corresponding elements and add them to each other. So we get A11 plus B11, then dot dot dot, and then AM1 plus BM1. This is why also it's really important that they got the same dimension, which means that they got exactly the same amount of elements, or the same amount of columns and the same amount of rows in terms of the matrix size. So then here we have A1n, and then plus B1n, then dot dot dot, and then AM1, and then plus BM. Here I need to put n. We are in the last element of the matrix, so BMN, and that is it. This is our matrix A plus B. Let's now look into the matrix B plus A. So what that amount is. So the matrix B plus A will then be equal to B11 plus A11 dot dot dot, and then BM1 plus AM1, then dot dot dot, and then B1n plus A1n, then dot dot dot, and then the last element will be BMN, and then plus AMN. So In here, if we remember from the real numbers, we know that A plus B is equal to B plus A. For instance, if A is equal to 2 and then B is equal to 1, then A plus B is equal to 2 plus 1, which is equal to 3, and then B plus 1 is equal to 1 plus 2, and it's equal to 3. So we know that indeed for the real numbers, A plus B is equal to B plus A. And making use of that property, we can already state that B11 plus A11 is equal to A11 plus B11. And then the general case is that Aij plus Bij is equal to Bij plus Aij, where I is the index of the rows and then j is the index of the columns from the coefficient labeling. So using this property from the real numbers, given that all these values in the matrix are real numbers, we can quickly see that the matrix B plus A that we just got in here is equal to this matrix A plus B, which means that 1 is equal to B. And this proves that A plus B is equal to B plus A. This is the commutative property of the matrix additions. So the next law is the associative law for matrices, which says that in case of matrix addition, A plus B plus C is equal to A plus B plus C. So basically, this time we go from here to adding one more element, which is the third matrix, matrix C. So we are saying A plus B plus C is equal to A plus B plus C. So it doesn't matter whether we will first take the matrix A and then B and then add them up, and then we add matrix C, or if we first take the matrix B and C, add them up, and then we add A to this sum. It doesn't matter. We will see an example of this in a bit. And then the second part of this associative law for matrices says that for matrix multiplication, A times B times C is equal to A times B times C. So again, in terms of the order when it comes to this specific multiplication, so it doesn't matter whether we will first multiply A by B and then by C, or we will first multiply B by C and then we add the A. At the end, we will end up with the same amount. So A times B and then times C is equal to B times C, and then in the left-hand side, we add the A. So A times B times C. So these properties help us to add or multiply matrices without really worrying about this idea of grouping of the terms. So we can always group them and perform all sorts of operations. So this is this first property that we see in here. Let's say we have this matrix A, matrix B, and matrix C. So let's prove that indeed the order doesn't matter and this associative property holds. So let's prove that. So for that, the first thing we need to do is to compute A plus B, so this part. So A plus B plus C. What is that? First, I need to compute this part, and then I will add C, which is the second part. So A plus B is equal to, my A is equal to 1, 2, 3, 4 plus, and my B is equal to 5, 6, 7, 8. This is then equal to, so 1 plus 5 is equal to 6, 2 plus 6 is equal to 8, 3 plus 7 is equal to 10, and then 4 plus 8 is equal to 12. This is my A plus B. This is the first part. Now, the second part is then to add to this A plus B, this C. This I can, by the way, also call some matrix D. So I can say that this is equal to D plus C. So let's find out what is this amount. So A plus B, or what we're referring as D, is 6, 8, 10, 12. We just calculated it in here. I'm also adding now my matrix C, which is 9, 11, 10, 12. So 9, 10, 11, 12. What is this amount? It is 6 plus 9 is 15, 8 plus 10 is 18, 10 plus 11 is 21, 12 plus 12 is 24. This is my final matrix. So I have checked that the A plus B plus C is equal to 15, 18, 21, and 24. This is the first part. Let's now go ahead and check whether this is equal to the second part, which is this part. So this is 1, this is 2. So this is then A plus B plus C, as you can see it in here. Let's now calculate that amount. And like previously, we will do it in an order. So first we need to calculate this part and then the entire thing. So B plus C is then equal to, the B was 5, 6, 7, 8, 5, 6, 7, 8, plus, and the C was 9, 10, 11, 12. 9, 10, 11, 12. What is this amount? 5 plus 9 is 14, 6 plus 10 is 16, 7 plus 11 is 18, and 8 plus 12 is 20. This is the first amount. Let's refer this as a D. Or we can even call it by some other letter. Let's say K. This is matrix K. So B plus C is K. Then the second part is to take this B plus C, so B plus C, which we have referred as K, say K, and then we are adding to this the A. And specifically, just to ensure that we stay with the same order, I'm saying I will add from the left side the A to this matrix K. And this obviously means this is equal to, so A plus B plus C. This is what I'm referring by. Just in a more simpler notation, I'm just using K in here. So this is my B plus C, or what I'm referring also as a K. And this amount is equal to, what is my A? My A is 1, 2, 3, 4. 1, 2, 3, 4. Plus, and what is B plus C? We just calculated that. That's the K. So 14, 16, 18, 20. So 1 plus 14 is 15. 2 plus 16 is 18. 3 plus 18 is 21. 4 plus 20 is 24. So we have learned that the A plus B plus C is this vector. Now, is this vector equal to the A plus B and then plus C? Well, here we got this 15, 18, 21, 24. 15, 18, 21, 24. So we have just proved that the first part is equal to second part, which means that we have proved that indeed the order doesn't matter, and A plus B plus C is equal to A plus B plus C. So this calculation confirms that the both sides of these equations, they are indeed equal, and this confirms the associative law for the matrix addition. So let's now look into the distributive law for matrices, which says that matrix addition and multiplication, they satisfy the distributive property, which means that if we have a left distribution, A times B plus C is equal to AB plus AC. And then in the right distribution, we basically have the matrix multiplying from the right, hence the name right distribution. A plus B times C is equal to AC plus BC. You might very quickly see and recognize from here that we have very similar, actually exactly the same rule, only for real numbers. We know that A times B plus C is equal to, and then we open the parentheses, we say this is equal to this times this, so AB plus this times this, AC. You can see that we have exactly the same here, only in the capital letters. So in the real numbers, we have exactly the same law. So the same we have also for our left distribution when it comes to matrix addition and multiplication. And the same we have, only with a different order. Here you can see the C. So this one is basically with the different order. Instead of having the matrix multiplied in the left, here we have from the right. And this is similar to the property that A plus B times C is equal to C times A, which is AC, plus C times B, which is BC. Into an example where we will prove that the distributive law for matrices is indeed true. And I have skipped deliberately the example for this one because this AB times C is equal to A times BC, so the associative law for matrix multiplication, it's something that you can calculate for yourself using the same A, B, and C matrices, only this includes multiplication of these two matrices, and it's something that we are going to do as part of this example. So instead of doing and redoing this multiplication, I thought that it's great to leave that for you as a practice and instead focus on a bit more complex problem like this one that one way or the other includes the same matrix multiplication. So I need to calculate the A times B in this case, which means that by providing you this example, I'm also including what is needed to do the previous example. Only it would be a great way to practice the material for yourself. So let's now move into proving the distributive law for matrices. So we got these matrices A, B, and C. And here I'm going to apply matrix multiplication, the same as that is needed for the previous case. And here what we need to prove is that A times B plus C is equal to AB times AC. So this is the first part, this is the second part. So let's go and calculate them separately. So for the first one, we need to calculate A times B plus C, which is then something that we can calculate by first doing the addition. So we will first do the addition of matrices B and C, and then once we are done with that, we will then do A times B plus C. So that's the second part. So let's go ahead and do that calculation. So first we got B plus C. What is B plus C? B is 5, 6, 7, 8. 5, 6, 7, 8 plus, and the C is minus 1, 0, 0, minus 1. So on the diagonal we got minus 1 and minus 1, and then off diagonal, lower and upper parts, we got 0. And what is this matrix? This is equal to 5 minus 1, so 5 plus minus 1 is equal to 4. 6 plus 0 is equal to 6. 7 plus 0 is equal to 7. And then 8 minus 1 is equal to 7. This is our B plus C, which we can refer also as matrix D. So let's call this D, which means that now we are interested in A times D. So for the second part, we need to take this matrix A. So A times D is then equal to, we need to take the matrix A, which is 1, 2, 3, 4, and we need to multiply it with this matrix that we just got, because this is the B plus C or the D that we were referring. 4, 6, 7, 7. Okay, so let me remove this part, because we are going to need some space for this. And let's do this calculation. This is 2 by 2, and this is 2 by 2. I will do the calculations in here. So we need to end up with a matrix that is also 2 by 2. Because we know 2 by 2 matrix times 2 by 2, we will pick this part, so the number of rows and the number of columns of the second one, this will be our resulting matrix, which is 2 by 2. Alright, so for the matrix multiplication, we know that for this element in the place of, so 1A, or let's call this matrix, we don't even actually need to call this anything, we can keep it simple. So let's say that we are in the first row and the first column. So this is the first row and the first column. For this, what we need to do is we need to take the first row from the first matrix, so matrix A, and then the first column of the matrix D, so this one, and we need to do the dot product, which means that we do basically 1 times 4, 1 times 4, plus 2 times 7. So for this element, which is in the second row and the first column, we need to take the second row and first column in here. So we end up with 3 times 4, so 3 times 4, and then 4 times 7, so plus 4 times 7, the dot product between this one and then this one. So for this element, which is in the first row and then the second column of the final matrix, so first row and second column, we need to pick the first row and second column and do a dot product, which means 1 times 6 plus 2 times 7, 2 times 7. And then in here, in this element, we got the second column and second row. So second row, second column, which means that we need to pick the second row and the second column, the dot product of the second row of matrix A and the second column of matrix D, which is 3 times 6 plus 4 times 7. 4 times 7. So let's quickly calculate what this amount is. So this is the A times B plus C, basically. And this matrix is 1 plus 4 is 4, 2 times 7 is 14, 4 plus 14 is 18. 1 times 6 is 6, 2 times 7 is 14, and 6 plus 14 is 20. 3 times 4 is 12, 4 times 7 is 28, which means that we got here 40. 3 times 6 is 18, 4 times 7 is 28, which means we got here 36 and 46. This is our final A times B plus C. Let's now go ahead and calculate the second part. So the second part says that we got A times B plus A times C. So A times B plus A times C, which means that first we need to do this calculation and then this one. And then we need to add them to each other. So let's quickly then calculate what is A times B and then A times C and then add them to each other. Let me clean up some space in here. We're going to need that. Let me write this one in a smaller format. So this is equal to 18, 20, 40, and 46. And let me take over the second element, which we still need to calculate, which is AB plus AC. First, we will do this, and then we will add them to each other. So, A times B is equal to 1, 2, 3, 4 multiplied by 5, 6, 7, 8. 5, 6, 7, 8. Now, following the same approach from the previous example, when we calculate this matrix, I will then quickly calculate what is this A times B. So in here we got first row and first column. So 1 times 5 plus 2 times 7. So the dot product between the first row and the first column from here. Now for this element, here we got the second row and the first column. We need to take the second row and the first column from here, and we do the dot product, which means 3 times 5 plus 4 times 7. In here, we got the first row and second column. So the first row and second column, which means that we need to have 1 times 6 plus 2 times 8. Then here we got the second row and then second column, which means 3 times 6 plus 4 times 8. And then this is equal to 1 times 5 is 5. 2 times 7 is 14, so this is 19. 1 times 6 is 6. 2 times 8 is 16. 6 plus 16 is 22. In here, 3 times 5 is 15. 4 times 7 is 28. So this is then 33 and then 43. So 43. And in here, we got 3 times 6 is 18. 4 times 8 is 32. So we end up with 50. So I hope I haven't made any mistakes in the calculations. So this is the A times B. So A times B is then equal to 19, 22, 43, 50. Let's clean this space and let's move ahead to the second part of the calculation, which is A times C. What is A times C? Well, A times C is 1, 2, 3, 4, 1, 2, 3, 4, multiplied by minus 1, 0, 0, minus 1. So here we are then getting minus 1 plus 0. Here we are getting minus 3 plus 0. Here we have minus 1 plus 0. So, no. So the first row and second column, which is 0 minus 2. And then in here we got the second row and the second column, which is 0 minus 4. Which means that we end up with this matrix, and it's equal to minus 1, minus 3, then minus 2, and then minus 4. Which means that we are getting, as a final step, AB plus AC, which means 19, 20, 20, 43, and then 50, then plus minus 1, minus 2, minus 3, minus 4. And what is this? 19 minus 1 is 18, 43 minus 3 is 40, 22 minus 2 is 20, 50 minus 4 is 46. Okay. So we got that this amount, AB plus AC, is equal to 18, 20, 40, 46. And as you can see already here, this matrix that we got in the previous calculation from 1 is equal to this matrix that we got as part of second calculation, which means that now we have proved that for this specific example, indeed, 1 is equal to 2, which means that A times B plus C is equal to AB plus AC. There we go. So let's now look into another law, which is the scalar multiplication law for matrices. So the scalar multiplication law for matrices says that if we got a scalar R and a matrix A and B, then R times A times B is equal to R times A times B and is equal to A times R times B. So here the R is just a scalar, so it's a real number, and then A and B are matrices. And what this law basically says is that it doesn't matter in which stage you will do your matrix multiplication with the scalar if you have this external scalar. You can first take the two matrices, multiply them with each other, so the A and then B, and then multiply it with R. Or you can take the scalar R, multiply with your first matrix, and then multiply with B. Or you can take your second matrix, multiply with the scalar, and then multiply with A. It doesn't matter. They will all result in the same matrix. So let us actually prove this by making use of our skills from matrix multiplication and scalar multiplication. Here I've picked up a bit more advanced example where A is 2 by 3 and B is 3 by 3. In this way, we will train our multiplication skills for matrices, and at the same time, we will also prove that the scalar multiplication law of matrices holds. So let's go ahead and do the multiplications. So first we have a matrix A. What is that matrix? Matrix A is 1 minus 1, 2. So 1 minus 1 and then 2. Then we got 0, 2, and then 1, which is 2 by 3. And then we got B, which is equal to, it is 3 by 3, with elements 1, 0, 1, 1, 2, 0, 1, 1, and then 3, 1, 0, 2. So it is 3 by 4. So it's 3 by 4, not 3 by 3, but 3 by 4 matrix. Now, the final part that I need here is this, which is R is equal to 2, the scalar value. So R is equal to 2. So the first thing that I'm going to do is to calculate this amount, which is R times A times B. For that, what I need to do is to first calculate this A times B. So let me quickly go and calculate this for us. So given that the A has dimension 2 by 3 and then B has a dimension 3 by 4, I can see that quickly that my dimension criteria is satisfied. The number of columns of A is equal to number of rows of B. So that's fine. And then I also know that the final dimension of A times B is going to be 2 by 4. So it's going to be a 2 by 4 matrix. And how do I know that? Well, because I know that from our all these problems that we have solved, we have already seen that we always need to pick the number of rows of the first column and the number of columns of the second matrix in order to get the final dimension, which is 2 by 4. So let me then go ahead and do the calculation. So we're going to have a 2 by 4 matrix. Let me write it even bigger. So it's going to be a 2 by 4 matrix. So for the first row and first column, I need to look in here the first row and the first column, which means I need to take 1. So it's equal to 1 times 1. So plus 1 times 1 is 1. Minus 1 times 2 is minus 2. 2 times 3 is 6, plus 6. This is my first value. And what is this amount? It is equal to 1 minus 2 is minus 1, and 6 minus 1 is equal to 5. So this amount is 5. 5. So what is this amount? Well, this is my second row and the first column. So I need to make use of second row and first column, which is equal to 0 times 1 is 0, 2 times 2 is 4, and 1 times 3 is 3. 4 plus 3 is 7. So this value is 7. We are ready to go on to the next column. So column number 2. So then this time I need to look at the first row and second column. So we are going to use this one. So first we will use this first row. 1 times 0 is 0. Minus 1 times 0 is 0. 0 plus 0 is 0. And then 2 times 1 is the only non-zero element. 2 times 1 is 2. So I already know that for my second column, I got here 2. And what is this element? Well, for this, I need to look at the second row and second column. So this thing. So 0 times 0 is 0. 2 times 0 is 0. 1 times 1 is 1, which means that here I get a 1. Let's now move on towards the third column. So in here, first I need to look at the first row. So 1 minus 1 and 2. And then this time, we remove this. I need to look at the third column because I'm here in the third column. So 1 times 1 is 1. Minus 1 times 1 is 1. So here I got 1 minus 1. And then 2 times 0 is 0 plus 0. 1 minus 1 plus 0 is 0 because those two cancel out. This means that here in this element I got a 0. And what about this element where I need to look here in the second row and here I need to look at the third column? 0 times 1 is 0. 2 times 1 is 2. 1 times 0 is 0. So 0 plus 2 plus 0 is equal to 2. So this is 2. And now we are left with the fourth column. So for that, I need to look in here. So for the first row, which means first row in here and then the fourth column in here. So first row in here and fourth column here. 1 times 1 is 1, minus 1 times 1 is 1, and then 2 times 2 is 4, which means that I end up with 1 minus 1 and then plus 4. And what is this? This 2 cancel out, I end up with 4, which means that here I need to fill in 4. And what is this final element? It is the second row in the fourth column. So the second row in the fourth column. 0 times 1 is 0, 2 times 1 is 2, 1 times 2 is 2. 0 plus 2 plus 2 is equal to 4. So now we obtained that A times B is this 2 times 4 matrix, as we have expected. So this is then equal to 5, 2, 0, 4, and then 7, 1, 2, 4. So then the next step would be to take the scalar r and multiply it with A times B. Let me actually keep the colors consistent. So A times B. This is A times B. So the only thing that I need to do is to take that in here and multiply this 2 with each of those elements. So I will end up with the same size matrix, so 2 by 4. Only all these elements need to be multiplied with the scalar, which means that I will get 5 times 2 is 10, 2 times 2 is 4, 0 times 2 is 0, 4 times 2 is 8, and then 7 times 2 is 14, 1 times 2 is 2, 2 times 2 is 4, and then 4 times 2 is 8. So this is the result of the multiplication. So this is the first part. This is what we are referring as 1. So we have then checked in here that the r times, actually we have already in here, so I won't be writing again. So as part of the first section, we have already seen that r times A times B is this matrix. Let's now move on to the next one, which is calculating this second part. So this is the first part, this is the second, and this is the third. We have this already. Let's now move on and calculate this one. So for the second case, what we want to calculate is r times A times B. So it is r times A and then times B. This is what we need to calculate. So the first thing that we will do is to calculate this part and then to calculate the entire thing, the second part. So let's go ahead and do that. First, we will take the A and then we will multiply all its elements by scalar 2 to get the R and then A. This amount is equal to 1 times 2 is equal to 2, minus 1 times 2 is minus 2, 2 times 2 is equal to 4, 0 times 2 is equal to 0, 2 times 2 is equal to 4, 2 times 1 is equal to 2. This is R times A. Now, in the next step, so this was 1. The next step, we need to take this amount, this matrix, 2 minus 2, 4, 0, 4, 2, and multiply it with 1, 2, 3, 0, 0, 1, and then 1, 1, 0, and then 1, 1, 2. So basically the matrix B. Let's now move and work our way out with that one. Actually, let me remove this from here and keep the space a bit more clean. R times A, and I will be multiplying this with the matrix 1, 2, 3, and then 0, 0, 1, and then 1, 1, 1, 1, and then 0, 2. Well, I know that this one is 2 by 3, and this one is 3 by 4, which means that the result will be 2 by 4. Let's now go ahead and calculate that matrix. which is equal with the dimension of 2 by 4. Well, for the first row and first column, let me actually go and quickly do those calculations. Let's now go ahead and do those calculations. So we are going to have 4 columns as previously. The dimension is going to be 2 by 4. So let's do it column by column. In here, it means that we are in the row 1 and then column 1. So 2 times 1 is equal to 2, minus 2 times 2 is minus 4, and then here we got 4, so 4 times 3 is 12. So we got 2 minus 4 and then plus 12. And what is this amount? 2 minus 4 is minus 2 plus 12 is 10. So here we got 10. Let me remove this. 10. This is the second row and the first column, which means we got 0 times 1 is 0, 4 times 2 is 8, and 2 times 3 is 6. So 8 plus 6 is equal to 14. So here we got 14. This is the first row and second column, which means that we are looking at this row and second column this time. So 2 times 0 is 0, minus 2 times 0 is 0. The only thing that we care about is this 1 and this element, which is 4 times 1. So this should be 4. Let's now do the same for the second row. 0 times 0 is 0, 4 times 0 is 0, 0 plus 0 is 0, which means we are left with 2 times 1. So here it comes 2. Let's now do the third column. So for the third column, we got first row. 2 times 1 is 2, minus 2 times 1 is minus 2. And then 4 times 0 is 0, which means that here we get 0, because 2 minus 2 plus 0 is 0. Then we got the second row and third column, which is this row and then third column. So 0 times 1 is 0, 4 times 1 is 4, 2 times 0 is 0, 0 plus 4 plus 0 is 4. So this is 4. And then for the first row and then fourth column, so it means that we need to look at this specific column. The first row is 2 times 1, it is 2, minus 2 times 1 is minus 2, and then 4 times 2 is 8. So 2 minus 2 plus 8 is 8. And then finally, for the second row and the fourth column, 0 times 1 is 0, 4 times 1 is 4, 2 times 2 is 4, 4 plus 4 is 8. This is the final matrix, which means that this entire amount that we just calculated step by step, this is equal to this matrix in here. Okay, so this is the second element. Let's check whether the first element is equal to the first one. So we see here 10, 4, 0, 8, 14, 2, 4, 8. As you can see, we are dealing with exactly the same matrix, which proves that indeed R times A times B is equal to R times A times B. So this part we have already proven because we have seen that 1 is equal to 2. Perfect. So the only thing that is remaining is to calculate this third part and to see whether this is equal to this matrices, because we have seen that the two of those are equal. So the remaining thing that is left to prove this theorem is to calculate this third part. Let's go ahead and do that. So the third element says, let's first calculate the R times B and then multiply it by A. So we need to calculate B, R times B, times A. This is what we need to calculate, which means first we need to calculate this and then we need to calculate the entire thing. Alright, so let's go ahead and do that. So R times B is equal to so we need to multiply each of the elements of B by 2. So we end up with this matrix 2, 0, 2, 2, and then 2 times 2 is 4, 2 times 0 is 0, and then 2, 2, and then 2 times 3 is 6, 2 times 1 is 2, 2 times 0 is 0, 2 times 2 is 4. This is that first matrix. Let's now go ahead and calculate the second part, which is A times matrix A. So it is 1 minus 1, 2, and then 0, 2, and then 1, multiplied by this matrix, which is 2, 4, 6, 0, 0, 2, and then 2, 2, 0, and then 2, 2, 4. Okay, perfect. So this is then what we need to calculate. Well, this is 3 times 4. This is 2 times 3, which means the result should be 2 times 4. Let's go ahead and do those calculations. This first amount will be the first row and the first column dot product of those, which means 1 times 2 is 2, minus 1 times 4 is minus 4, and then 2 times 6 is 12. So here we got 2 minus 4 plus 12. And what is this amount? Well, 2 minus 4 is minus 2. 12 minus 2 is equal to 10. So this one, this element is 10. Then for the second row, we need to look in here. So 0, 2, 1, and the dot product of that one with the first column. So this thing. And that is 0 times 2 is 0, 2 times 4 is 8, and then 1 times 6 is 6. So what is 8 plus 6? That is 14. And then for the first row and then the second column, we need to look to the first row in here and then the second column in here and the dot product of the two. Well, 1 times 0 is 0, minus 1 times 0 is 0, and then 2 times 2 is 4. So that's what we are left with, 4. And then for the second row and then the second column, so this element, we got 0 times 0 is 0, 2 times 0 is 0, 1 times 2 is 2. For the first row and the third column, so we need to look in here. 1 times 2 is 2, minus 1 times 2 is minus 2, and then 2 times 0 is 0. So we are left with 0. 0. And then once we do the calculation for the second row, we will see that we end up with 0 times 2 is 0, 2 times 2 is 4, and then 1 times 0 is 0. So we end up with 4. And then here for the final column, 1 times 2 is 2, minus 1 times 2 is minus 2, and then 2 times 4 is 8. The first two cancel out, and we end up with 8. And then for the second row and the fourth column, we look into here again, this time the second row, 0 times 2 is 0, 2 times 2 is 4, and 1 times 4 is 4, and then 4 plus 4 is 8. So if we look in here, this is our third amount. We will quickly see that again we have the same matrix with exactly the same elements. So now we have also proved the third part, and we have seen that in all cases, the R times A times B is equal to R times A times B is equal to A times R times B. Now we are ready to move on towards the second module in this unit, which is about the determinants and their properties. We are going to look into the determinants at high level. We are going to define them and going to understand why they matter and why they are important. Then we are going to see how we can calculate the determinants. We are going to see the calculation for 2 by 2 matrix, then 3 by 3 matrix, and then just in general, how we can do it. And then we are going to see the properties of determinants one by one. And then finally, we are going to see the determinants interpretation from the geometric perspective, so when we visualize it using Python. So, by definition, the determinant is a scalar value that can be computed from the elements of a square matrix, so this is important, square matrix, and encodes certain properties of the matrix. So, the determinant provides a critical information about the matrix, such as whether it's invertible, and the volume scaling factor for the linear transformation it represents. So we see that the concept of determinant is highly related to many other concepts that we have seen before. So first here it's talking about the square matrix, then it's talking about encoding certain properties. So having the determinant, it contains certain information that is related to the properties of the system that matrix is representing. And then it provides critical information about the underlying matrix, because the determinant is calculated from a matrix. We say the determinant of a matrix. So it contains a critical information about that matrix, such as whether it's invertible or not. And this goes back to the concept of inverse. We will see this once we learn the concept of determinant, because the inverse calculation is dependent on the determinant. But keep this thing in mind that the determinant contains information whether we can get inverse from a matrix or not. We will see this concept also in detail in the next section. But for now, we can remember that the determinant contains important information related to the invertibility of the matrix, so having an inverse or not. And then it also contains information about the volume scaling factor for the linear transformation it represents. So here we then go back to this concept of AX is equal to B, and then knowing the determinant, we can then comment on this volume scaling factor for this linear transformation that it represents. So let's go on to the next slide to find out a bit more about the determinants, and specifically how we can calculate the determinant in the mathematical terms when it comes to the 2x2 matrix. Because the determinant of a 2x2 matrix is quite straightforward. So for 2x2 matrix A, with these elements where A, B, C, and D, they are all real numbers, the determinant, which we define by this det A, so det is a short way of saying determinant, and then in here we always write the matrix of which we are computing the determinant, is then equal to, and then we are taking this A times D, so we are taking this diagonal elements, A times D, so they are on the diagonal, and then we are subtracting from this other two, the remaining two elements of the diagonal, so B times C. And this gives us the determinant of a 2x2 matrix. This is just a formula that you need to remember whenever you want to calculate the determinant of a matrix by hand, manually. So the calculation for larger matrices, it involves a bit more difficult calculation. We will see also in a bit the determinant of a 3x3 matrix. It relies on the determinant of a 2x2 matrix. And the idea is that every time we increase the dimension of our problem, so let's say we are in R4, then we will go back to the R3, and then given that R3 relies on the determinant of the underlying 2x2 matrices, anytime we increase the dimension, we again go back to this idea of using 2x2 matrices that form the entire matrix in order to compute the determinant. Only when it is R4, R5, etc., so it becomes much more difficult to describe and to do it manually. Therefore, there are other algorithms which we will see at the end of this course, like decomposition algorithms and factorization algorithms, that can be used in order to calculate the determinant of a matrix that has higher dimension, higher than the 3, for instance. But in this specific unit, we are going to discuss both the calculation of the 2x2 matrices determinants and the determinant of a 3x3 matrices, and we will also see detailed examples of them. So without further ado, let's then go ahead and calculate the determinant of this 2x2 matrix. So let's now look into this specific example where we are calculating the determinant of this 2x2 matrix. So this is the A, and let's keep in mind that this is the A, this is the B in this, not in this way of writing the matrix A. So the letters corresponding to of the elements of this matrix A. So this is the A, this is the B, and then this is the C, this is the D. And we said that the determinant det of A is equal to the diagonal elements. So 1 times 4 minus the off diagonal elements, which is 2 by 3. Because we said that the definition of this determinant is that it's equal to A times D and then minus B times C, which is exactly what we are doing in here. So if we calculate 1 times 4 is equal to 4, and then 2 times 3 is equal to 6, 4 minus 6 is equal to minus 2. Therefore, we say that the determinant of matrix A is equal to minus 2. Let's now go ahead and practice with calculation of determinants on 2 other matrices. So in this case, we are still in the 2-dimensional space, so we have 2 by 2 matrices. We'll first calculate the determinant for matrix A. So we see that we got this element 5, 0, 6, 1. And we know that by definition, the determinant of the 2 by 2 matrix, so that of matrix, is equal to A times D minus B times C, where the matrix has the following form. So we got A and then D in here, and then B and the C in here. So we see that this is basically our A, this is our D, this is our B, and this is our C. The way you can also see it is that those are the diagonal elements and those are the off-diagonal elements. So therefore, it means that we can calculate the determinant of matrix A by taking the 5, multiplying with 1. So it is 5 times 1 minus the off-diagonal element, which is 6 times 0. And this amount is equal to 5 minus 0, and it's equal to 5. Let's go ahead and also calculate the determinant of matrix B. We see here that on the diagonal, we have this 2 elements, 1, 1, and off the diagonal elements are both 0, those 2. Therefore, we can calculate the determinant of this 2 by 2 matrix, which is also sometimes referred as I2. So it is the identity matrix because we got here the E1 and then E2 in the 2-dimensional space. And the determinant of the matrix B using this definition is then equal to 1 times 1 minus 0 times 0. So 1 times 1 minus 0 times 0. And this is equal to 1. And this is actually a special case of determinant. And later on, we will see why it is so important to have this relationship of identity matrix, having a determinant, and having it equal to 1. And this relationship between determinant and identity matrix is something that we see also in the upcoming lesson. So keep this one in mind. So now when we are clear on how we can calculate the determinant for a 2 by 2 matrix, so this is quite simple and straightforward calculation by taking the diagonal elements A and then D and then subtracting from that product A times D, we are subtracting the off diagonal elements products B times C, we can then get our determinant. And now when we are clear on that, we are ready to go on to a bit more advanced calculations, which is calculating the determinant, this time for the 3 by 3 matrix. So now we increase the dimension size and we go from R2 to R3. Because now we have a 3 by 3 matrix. And by definition, given a 3 by 3 matrix A, which has the following elements. So A11, A21, A31, and then A12, A22, A32. So we have already seen this coefficient labeling. This should look very familiar. This is 3 by 3 matrix 2. And the determinant of a matrix A, denoted as det A, is calculated using the formula. And here we see the formula. We are basically using the 2 by 2 matrices that form this matrix A in order to calculate the determinant of the 3 by 3 matrix. And how we are doing that? Well, we are using this element, and then this element, and this element, and every time we are hiding part of the matrix. So when we have, for instance, this A11, so for this first part, we are saying, well, let's hide the row and the column corresponding to this element, which means that we need to hide this row and this column. And what is left is this 2 by 2 matrix. We will calculate the determinant of this 2 by 2 matrix, and we will multiply this with this element that we use in order to remove the corresponding row and column. This will form the first element in here. So you can see A11, which is a simple value. So this is the entry value, which is in the first row and first column, A11, multiplied by the determinant of this matrix. So this matrix. So once we have that, and we already know how we can calculate a determinant of a 2 by 2 matrix, because it's 2 by 2. So taking the diagonal elements and then multiplying them together, subtracting from that the off-diagonal elements product. Now we are ready to go on to the next part of the calculation, which is this time adding a minus here. So you can see here, here is plus, and then here is minus. So we do here minus. And for this second step, what we need to do is kind of similar, only this time the element that we will be using to understand how we can remove the row and the column, so we will then dark it out. It is this one, A12. So then we will need to remove this column and this row, and then the remaining matrix, which is this one, this 2 by 2, and here I mean A21, A31, and then A23, and then A33. This is the matrix that you can see in here remaining, which means remove this one, and then this one, and then the remaining 2 by 2 matrix is what you need to use in order to do your calculations. So you can see that I got exactly the same in here. And once again, we are computing the determinant of this matrix. We are multiplying this with this A12 element, so this element. And now we have also the second element in our calculation. And then we go on to the next step, which is a plus sign here. Let me use the same colors, plus sign here. And then we are using this time our final third element to understand which row and which column we need to dark out, which is this element. So we then remove the first row and the last column. And this is then the matrix, the 2 by 2 matrix that we use in order to do our calculations. So the determinant of this matrix multiplied by the A13. So we could also use in the same manner this row or this row. It really depends on the kind of values. The tip that I will provide to you, or the trick, is that to always look for these 0, 0 values. Wherever I see 0, 0s or I see 1, 1, I'm thinking that, hey, those seem values that give me the most straightforward and easy calculations. Because if I have zeros in my entry, so if I got a 0 here, for instance, 0 times any determinant is 0. I don't even then need to calculate the determinant, right? Because then I know that I'm multiplying that determinant with 0. Therefore, if I know that that entry, for instance, this row contains the majority of zeros, so it is 0, 0, 1, then of course it's a great row to pick to use these target elements. So in that way, I will then know that this is the row that I need to target. But if it is like that for instance, I got a matrix 10, 3, 4, and here I got 0, 1, 0, and here I have 100, 3, and 4, of course, the easiest thing would be to not use this row, but instead use this one. So in that case, I will then have this 0 and 0 as my target values, which means that I will only need to calculate the determinant of a 2 by 2 matrix for this one. For the two cases, I don't need to do it because I know that the corresponding target values, the target elements from my matrix will be 0. So let me show you what I mean by that. So if, for instance, I go for this second row and not the first one, what I need to do is that I can calculate the determinant of A by taking the A to 1. This then will be my target. I will then need to remove this column and this row. Then I will need to do the determinant of A12, A13, A32, A33. This is what then I need to do. Then the next thing I need to do is, of course, here I have a plus, here I need to do minus, because we always need to interchange the values. So here is a plus, here is a minus, here is a plus. So I do a minus in here. Then I do the next element in my row, which is this one. Let me use red color. So A22. So I'm then doing A22 multiply the determinant of, so I'm removing this row and this column, A11, A13, and then A31, A33. And then the final part is, of course, as you might have already guessed, is to look into this element. So it is plus A23 multiplied the determinant of, let me actually write it down in here, the determinant of A11, A12, and then A31, and then A32. So in this way, basically, independent of what row I will take as my leading row that I will do my calculations, and I will just need to pick one row, I can always get the same value for determinant of A. But choosing intelligently which row to pick, it will save you a lot of time and headache in terms of calculations. Because if you are dealing with a row that contains many zeros, for instance, you have 0, 0, 1, or 1, 0, 0, or even better 0, 0, 0, then you know automatically that you will need to calculate here the determinant once, here also once, and here you don't even need to calculate it. You know that you got 0 here, 0 here, 0 here, so it's automatically equal to 0. So I hope this makes sense, because this is a trick that usually you will not come across, but this just helps you to save a lot of time when it comes to calculation of your determinants in a 3x3 settings. So in this case, we have this definition, and we know the tricks that we can use, but I think it's really helpful to go ahead and to solve a problem. So basically, this is the high-level summary of the steps that we just discussed. So the determinant of a 3x3 matrix, it simply involves multiplying the A11 by the determinant of the 2x2 matrix that remains after excluding the row and column of A11. So what we did in here by doing this. And subtracting the product of A12 and the determinant of its respective 2-2 matrix. So this part. And then adding the product of A13 and the determinant of its respective 2x2 matrix. So this part. And the signs alternate. So it means first you always got the plus, then you always get the minus, and then the plus. So they interchange. You start with plus, then you do the minus, and then the plus. So let's go ahead and calculate the determinant of this matrix. So before even looking at the answer, let's actually go ahead and do that on this paper. So we got A, matrix A, which is equal to 1, 2, 3, 4. So basically from 1 till 9, 1, 2, 3, 4, 6, 4, 5, 6, and then 7, 8, 9. And for this 3 by 3 matrix, we need to calculate the determinant. So the determinant of A. The first thing that I'm seeing is that there are no rows with zeros or columns, which means that I cannot use my trick. And instead, I will just need to go with, let's say, the first row. And it's also convenient given that I got as a scalar these values, these much smaller values relatively to the other ones. All right, so first things first, let's go ahead and write down that formula. So the determinant of A is equal to, first we are going to take this one. So our 1 times, and then we got determinant of, and then we have this matrix, which is 5, 6, 8, and 9. This is our remaining matrix. Then the next thing we need to do is to interchange the size, the sign, which is minus. And then we got so the remaining matrix is then determinant of 4, 6, 7, 9. And then finally, plus 3 times, and then determinant of, what do we have? Well, this is the target. So it is 4, 5, 7, 8. Right, so let's go and do those calculations quickly. This is equal to 1 times. The determinant of this is the diagonal element, so 5 times, it is 5 times 9 minus 8 times 6 minus 2 times 4 times 6 minus 7 times 6. Sorry, 4 times 9. So the diagonal elements, 4 times 9 minus 7 times 6, and plus 3 times, and then 4 times 8 minus 5 times 7. This is equal to, so 9 times 5 is equal to 45. 8 times 6 is equal to 48. Then minus 2 times, 4 times 9 is 36. 7 times 6 is equal to 49. 7 times 6 is equal to 42. Plus 3 times 4 times 8 is equal to 32 minus 5 times 7 is equal to 35. So this is equal to 1 times minus 3 minus 2 times, and then here we got 36 minus 42, so that's minus 6 plus 3 times minus 3, which is then equal to minus 3 plus 12 minus 9, which is equal to 0. So let's check it. Indeed, we got the right answer. Perfect. So now when we are clear on how we can do this calculation, let's now go ahead and calculate yet another determinant of a 3 by 3 matrix. And this time I want to show you this simplified version by making use of this trick that I specified. So instead of using this first row as an indicator, I will be using the second row as my indicator. One thing to keep in mind when making use of this trick is that when you start from the second row, so from the even rows, second, fourth, or sixth, then in those cases, you need to flip the signs that you will be using. So while in here you had the sign plus in the beginning, then you got a minus and then a plus when doing all these calculations. So you remember here we got plus, minus, plus. When you start from the second row instead of first one, you need to flip the order of this. So you need to start with minus. You have minus, you got plus, and then minus. So knowing this trick, it also means that you go one step beyond and you know how you need to intelligently reduce the time that you are spending on calculation of the determinant, but it also means that you need to be careful on knowing what kind of signs you need to use. Because if you start from the first row, you start with plus, and then you do minus, plus, minus, plus. So knowing how to start, you already know how you can go on. But when it comes to the second row, so the even rows, you need to start with a minus. So you need to do minus, plus, dot, dot, dot. All right. So let's now go ahead and use that technique in here. So here I see that my first row doesn't contain zeros, but my second row does. So this gives me indication that I can reduce the time that I spend on calculating the determinant, at least one time, because I then no longer need to calculate that determinant. So the determinant of B is then equals to, I will then start with minus, given that I'm going to use this row, and then I have 0 times, so because this is my element, the determinant of 2306, and then plus, then this time the second element, target element, is this one, so it's 4 times, and then we got determinant of 1316, and then minus the 5 times, so this 5, determinant of 1210. And what is this amount? It is equal to this. I don't need to calculate because I got a 0 in here. This trick is all about this, to not calculate the determinant too often. And then this equals to 4 times. 4 times determinant of this is 6 minus 3. So 1 times 6 minus 1 times 3, which is equal to 3. And then minus 5 times determinant of 1210, which is 0 minus 2. So this is equal to 4 times 3, 12, minus 5 times minus 2, which is equal to 12 plus 10, and this is equal to 22. Let's go ahead and check this, and this is the more detailed and formal derivation. So one interesting thing is that I calculated with my second row, and in here in this slide you can see calculation with the first row. This is just a nice way of seeing the difference that you can do. And here in this solution, what we have is that we have manually calculated this first determinant too. So in total 3 determinants. But we again end up with the same determinant. So independent what kind of row you will use in order to calculate your determinant of matrix B, you will always end up with the same, similar volume, unless you have made a mistake in your calculations. So you just need to keep track of the rows that contain many zeros, and you need to be careful in terms of the signs that you need to use and the sign that you will need to start. If you start with the first row, then start with plus. If you start with the second row, then it is minus and then plus, etc. So as you can see here, it's a plus and then minus and then plus. In my case, I did with my second row, therefore I started with minus. All right, so let's now move on to the properties of determinants. So the determinant of an identity matrix is 1. That's something that we have also seen when doing our calculations, because we saw that in one specific case when we had this example, so this matrix B, and the matrix B was the identity 2 in the two-dimensional space, we have calculated its determinant and we saw that it's equal to 1. And this was not a coincidence, because the determinant of identity matrices is always equal to 1. Then the second property is that swapping two rows or columns of a matrix changes the sign of its determinant. So if you swap rows or columns in your matrix, so if you end up with matrix A and B, they are exactly the same, only one swaps the two columns or two rows, then you are changing the determinant of that matrix, the sign of that determinant, but not the value itself. It means that if you got A and you got B, and your A is equal to, let's say, A1 and then B, A2 and then A3, so it contains these columns, and then matrix B is equal to, let's say, A2 and then A1, A3, then the determinant of A will be equal to minus of the determinant of B. You can also say determinant of B will then be equal to the minus determinant of A. This is basically the idea of this property. Let's now move on to the third property, which says that if a matrix has a row or a column of zeros, its determinant is 0. So if you got a matrix A that contains these different values, A11, A21, A and M1, and then here you got suddenly a column that contains all zeros and then the rest are non-zero even. So in that case, you know that your determinant is equal to 0. So for a specific example, if you got, for instance, matrix 1, 0, 2, 0, 0, 0, 3, 1, 3, then the determinant of this matrix is equal to 0. And otherwise, if you got a matrix B that has a column of zeros, so column that is entirely of zeros. So let's say here we have 1, 1, 1, and we have a 0 vector here. So we got in here 0, 0, 0, and then 3, 4, 5. Then given that we have here this 0 vector, then the determinant of matrix B is equal to 0. And this is actually straightforward to be seen from these calculations that we saw. Because if you do if you pick this specific row, and then you do 0 times determinant of the remaining matrix, 0 times determinant of the other matrix, and then plus, so plus, and then so minus, and then plus, and then minus 0 times determinant of the third matrix, it is obvious that 0 times a determinant is 0, 0 times determinant is 0, 0 times determinant is 0, which means that you got a whole bunch of zeros to be added to each other or subtracted from each other. This means that if you have a row or a column with zeros, this already gives you an idea that your determinant is equal to 0. You don't even need to do calculations. So the final property of determinants is that if a determinant of a product of matrices equals the product of their determinants. So the determinant of AB is equal to determinant of A multiplied by determinant of B. This is basically what this property is about. So let's quickly go through examples to ensure that we are at the same page with all these properties and we can prove them. So let's say we have an identity matrix n by n, which is we are dealing with In. Now, according to this first property, when we calculate the determinant of this matrix, so the determinant of In is equal to 1. Let's actually look at a specific example. So here we got identity matrix in the two-dimensional space, in the R2. And we can quickly calculate the determinant of this I2, and we can see that it is equal to this diagonal element, so 1 by 1 minus 0 times 0. It's actually something that we did as part of my previous examples. So this is equal to 1 minus 0, and it's equal to 1. One thing that I wanted to show you before moving on to the next example about the swapping rows is that when we are swapping some of the rows or some of the columns, or 2 rows or 2 columns of matrix A, we are referring to this matrix by this notation. So we add this not in here and we say that this is basically the manipulated version of matrix A. So if we have, for instance, matrix A equals to A, B, and C, and those are vectors, and then we are swapping 2 of the columns. Let's say we are swapping this 2. We get B and then A and then C. Then this matrix we are referring as A naught. This is just a matter of notation. And we just learned that as part of the properties that the determinant of this new matrix is equal to minus the determinant of A. So if a matrix A has a row or column of zeros, then the determinant of it is 0. So let's actually quickly look at this specific example. In here we got A, which is having a column of zeros, and another column of B and D, where B and D are real numbers. So let's prove that its determinant is actually equal to 0. So the determinant of a 2 by 2 matrix, we have already seen, is equal to the diagonal elements. So 0 times D minus the off-diagonal elements, which is 0 times B. 0 times B. And what is number times 0 is equal to 0. 0 minus 0 times B is also 0. It's equal to 0. Therefore, the determinant of A is equal to 0. So when it comes to the determinant of a product of matrices, let's prove that the determinant of A times B is equal to the determinant of A times the determinant of B. So therefore, the first thing we need to do is to calculate this A times B. Let's quickly go ahead and do that. So let me add here this blank file. So A is equal to 1, 2, 3, and 4. B is equal to 5, 6, 7, 8. And I want to prove that the determinant of A, B is equal to determinant of A times determinant of B. First, I will be calculating this, and then I will be calculating this. So for the first one, what I need to do is that first I need to calculate the A times B, which is equal to 1, 2, 3, 4 times 5, 6, 7, 8. And then this is equal to, should be 2 by 2. So first I take this. 1 times 5 is 5, 2 times 7 is 14, 14 plus 5 is 19. Then for this one, I need to pick this row, so 3 times 5 is 15. And then 4 times 7 is 28. So 15 plus 28 is, so there we have 33, 43. So I got here 43. Then I'm going on to the next column, which is, in this case, 1 times 6 is 6, 6 plus 16 is 22. And now the second column, 3 times 6 is 18. 4 times 8 is 32, and this gives me 50. Alright, so now I have the A times B. Then, as a next step, what I need to do is to calculate the determinant of this A times B, which is equal to the determinant of this matrix 19, 22, 43, 50 that I just calculated. And what is this amount? The diagonal elements 19 times 50 minus 43 times 22. 19 times 50 is then equal to 950, and 43 times 22 is 946, which means that we end up with 4. This means that the determinant of the A times B is equal to 4. Let's quickly check what are the parts of the second amount. So for that, I need to calculate determinant of A, which is equal to 1 times 4 minus 2 times 3. 1 times 4 is 4. 3 times 2 is 6. So 4 minus 6 is equal to minus 2. Determinant of B is equal to 5 times 8, which is equal to 40. And then 7 times 6 is equal to 42. And this is equal to minus 2. And determinant of A times determinant of B is equal to minus 2 times minus 2, which is equal to 4. So we can see that now we just proved that the determinant of A times B is equal to 4. So we have seen that determinant of AB is equal to 4. And we see that that's exactly the same as determinant A times determinant of B, which is equal to 4. So we have just proven that this equation indeed holds. So the determinants, they are not just some calculations or some amounts, but they are actually important concept, and their interpretation is highly relevant from geometric perspective. So determinants have a geometric interpretation. And for example, determinant of a 2 by 2 matrix or 3 by 3 matrix, they represent the area in case of 2 by 2 or the volume in case of 3 by 3 matrix of the parallelogram that they are forming. So this is often referred as parallel piped. I hope I'm pronouncing this correctly. And it's formed by the column vectors of the matrix. So if we have, for instance, this matrix A, and then we have A, B, and then C and D, we have this A and C, which is the first vector, and then B and D, which is the second vector. And the two vectors, they actually form a parallelogram when it comes to the two-dimensional space. And the area that this parallelogram is forming, that is equal to the determinant of this matrix. So the determinants offer this scalar value that summarizes this linear transformation that we describe by this matrix. Because we saw that we had this AX is equal to B linear system that we were describing using this coefficient matrix, and this was our unknowns, this was our variable. And then this B was the amount that we were putting this as equal to. If B was equal to 0, then we were solving the homogeneous system. Otherwise, we had this non-homogeneous system. And in the geometric terms, the determinant of this matrix A, so the determinant of A, in case of 2 by 2 space, so in R2, when we got 2 vectors, basically, in our matrix A, this is equal to the area that is spanned by these vectors in the 2-dimensional space. In a bit, I will also show you a specific example such that we will be on the same page when it comes to this concept of parallelogram, the determinant, and these vectors that form the column space of the matrix A. When it comes to the 3-dimensional space, when we have R3, so we got 3 by 3 matrix of A, then the determinant of this matrix A is the volume that is formed by these 3-dimensional vectors, because unlike the 2D, in R3, we got these 3 vectors that form the A, let's say this one, and then this one. And then here, we can create this area covered by these 3 vectors. And the area that is formed by these 3 vectors from A, it is equal to the determinant of that matrix A. So in terms of the 3D, it's a bit harder to visualize it. But in case of the 2-dimensional space, I think this will help to improve our understanding of the determinants and make this interpretation from geometrical perspective. So given the 2 vectors A and B in the 2-dimensional space, the determinant of this matrix is then equal to the diagonal elements, we already know, minus the off-diagonal elements, right? So we are also saying, we have seen this notation already, very often you will see this value. This is the absolute, we already know this from high school, this is the absolute value. Because the determinant can also be a negative number, we have seen minus 20 or minus 2, and we know that the area cannot be a negative number. Therefore, we are adding this absolute term here. So, knowing, for example, that we have this matrix A, which consists of the elements 3, 2, and then 1, 4, we know that the determinant of this A is equal to 3 times 4, 12, minus 1 times 2, it is 10, and the absolute value of it, so absolute value of 10, is equal to 10, given that it's positive, and this is exactly what we have here. And this is referred as the area of the parallelogram that the 2 vectors are forming. And how does that look like in the coordinate space? So this is the parallelogram that we were referring by. And this area that is formed by this parallelogram is equal to the determinant of the A, the matrix A. So one thing that we need to keep in mind is the definition of parallelogram, which means that those 2 are parallel and they are the same. So this and this lines, those 2 are the same. And then, of course, the same holds for those 2. They are parallel and they have the same length. Therefore, this figure in here, this is what we are referring as parallelogram. And those 2 vectors that we can see in here, this one and this one, they form this parallelogram. And they are the 2 vectors that are part of the matrix A. Hence, if we got 2 vectors that come from the matrix A, so matrix A, and we got here this 2 vectors in a 2 by 2 matrix, then the determinant of this matrix is then describing the area that these 2 vectors are using or are spanning when creating this parallelogram. So The determinants, they play an important role in understanding the geometric properties of the spaces that spanned by these vectors. They provide valuable insights when it comes to the scaling effect of linear transformation, the orientation, and the locations of them in the coordinate system, as well as the practical applications in calculating areas, in calculating volumes. Welcome to another unit in our Fundamentals to Linear Algebra course, where we are going to talk about advanced linear algebra concepts. So, in the first module, we are going to talk about vector spaces and the projections. We are going to define the basis and a couple of examples of them. We have already touched upon this concept briefly when we were calculating the basis of a null space and the basis of a comp space. We are going to do a similar example in this case. And then we are going to look into this concept of the standard basis for different spaces, including the R2. We are going to introduce the concept of projections. What is the definition of projections? What is the formula? How we can calculate it? We are going to look into detailed examples of them. Then we are going to talk about the concept of orthonormal basis. In this module, we are going to introduce this concept, and we are going to understand the orthogonality, normalization. We are going to then discuss a very important topic in linear algebra, which is the Gram-Schmidt process. We are going to define it. We are going to see the overview, the step-by-step process of applying Gram-Schmidt algorithm. Then we are going to see an example of it and the calculations step-by-step. And then we are going to talk about applications of orthonormal basis, the application of Gram-Schmidt's process, and the importance of this orthonormal basis. This is the module 1 of this part. So, let's first define the basis. A basis of a vector space is a set of linearly independent vectors that span the entire vector space. Every vector in the space can be expressed as a unique linear combination of the basis vectors. So there are a couple of parts in this definition that are really important. And first thing that we need to mention here is this vector space that says it is a set of linearly independent vectors that span the entire vector space. This is very important because here the basis is simply this vector space that is a set of linearly independent vectors, which means that one of these vectors cannot be rewritten as a linear combination of the other one. So we have a linearly independent vectors, and they span the entire vector space. So, for instance, if we are in R2, then the basis of a vector space is then a set of linearly independent vectors that span this entire R2. So we then need to have 4 vectors forming a basis. So let's say we have a basis of vector space. For us to say that this is the basis of this vector space, let's say in R2, we need to first prove that these vectors are linearly independent, and 2, they span the entire R2, which means that span of these vectors is equal to R2. We can actually be even more specific. In an example of, let's say, having vectors A and B, we can say that this set that we have here, consisting of vectors A and B, in R2, form the basis of a vector space if the first criteria is that A and B are linearly independent. And the second criteria is that those two vectors together, they span the entire vector space of R2, which means that span of A and B vector space is equal to R2. On more specific example. And then the second part of this definition says that every vector in the space can be expressed as a unique linear combination of the basis vectors, which means in our specific example, when we had this A and B forming the basis of a vector space, this means that if we prove that this is indeed the basis of this vector space, then any combination, every vector, let's say a vector C that consists of this C1 and C2 elements, that this vector, this random vector from R2, C, can be represented as a linear combination of these vectors A and B. So let's say we have a coefficient K1 times A plus K2 times B. Then here we are representing this random vector C as a linear combination of these vectors A and B, which form the basis of a vector space, of this vector space. So we have previously spoken about the null space and calm space. So let's now go ahead and do one more example when we are calculating the null space and the calm space. And then we are again calculating this concept of basis of a vector space and a basis of the calm space. And then we will be finding the basis of a vector space with R2 example. So given that we have already looked into this concept, the basis of calm space and basis of null space, I will try to go through this example a bit more quickly to save time on more complex concepts. So let's say we have an example of a matrix, and that matrix is A is equal to 1, 2, 3, 6. This is our 2 by 2 matrix A. And the first thing that I want to do is to look into my matrix and understand whether I'm dealing with unique vectors or not. And by unique, I mean whether I'm dealing with two vectors that are linearly dependent or linearly independent. This kind of inspection always helps us to save time when we are doing our calculation for the null space and for the calm space and for the basis of a null space and basis of a calm space. Now here we can see that this is our A1, the first vector, the first calm vector forming the matrix A, and this vector is the A2. Another thing that we can notice here is that we can easily take the first column, A1, multiplied by 2 and get the A2, because 1 times 2 is 2, 3 times 2 is 6. That is that 2 times A1 is equal to A2. Which means that we can say that A1 and A2 are linearly dependent. Okay, so seeing this and knowing this can help us to quickly go through our calculations of the basis of the calm space and the basis of a null space. So let's go ahead and first calculate what is the basis of null space of A. So we have already learned that the basis of a null space can be calculated When looking into the first null space, so we need to calculate the null space, and then we need to calculate the basis of that null space. So this means that we need to get the NA. And we have learned that in order to get the NA, we for that need to solve the AX is equal to 0 problem. And this X will give us the null space of A. We have also learned that the null space of A is equal to the null space of RREF of A, which means that using Gaussian reduction or Gaussian elimination, we can quickly find the solution to this problem of AX is equal to 0 and find this X. This is simply solving a similar problem, only in this case the B, so this is equal to 0 because we are dealing with the homogeneous case. I won't do the calculation for this. We have done a ton of examples when we were doing this step-by-step calculation, getting the augmented matrix of A and then doing all these different row operations, normalizations, and then eliminations in order to get this complex matrix A to the point of basic representation from which either we can visibly see the solution to the problem or we can at least simplify it and describe it as a linear combination of vectors. In this case, if you go ahead and solve this problem, you will find that the X that solves the AX is equal to 0 problem is unique, and this X is equal to minus 0.894 as the first element and then 0.447 as the second element. This can be a good practice also to refresh the memory when it comes to the Gaussian elimination and reduction. The example itself is quite simple. The A is just a 2x2 matrix. By performing a couple of operations in terms of normalization and elimination, you can find this X for your AX is equal to 0. Given that now we know what is the solution to AX is equal to 0 problem, now we know what the null space is. Because in this case, all this help us to understand that the null space of A is then equal to the set, the vector set, where as part of this we got just single column, which is minus 0.894 and 0.447. This is the null space. This is the first part. I will say it 1.1. And then 1.2 will be to get the basis of this NA. And we have just seen what is the definition of the basis. So the basis of vector space is a set of linearly independent vectors that span the entire vector space. Therefore, given that we got just this single vector as a solution to our problem, we can see then very quickly that the null space of A is based on this, and then the basis of the null space is simply this entire set. So knowing what the solution is to our homogeneous problem AX is equal to 0, so let me also write down in here, then we know that the null space, the NA, is then equal to the vector minus 0.894 and 0.447. This is my vector X that solved this AX is equal to 0 problem. And this is simply the null space of A. And given that we have calculated and we have got this unique solution to our problem, we can say that any vector in R2 can be represented as a linear combination of this vector. So 1.2, any vector in R2 can be represented as linear combination of this vector x. Therefore, we are saying that the basis of no space of A is this entire set consisting of this single vector. So this is about the basis of a null space. Let's now quickly look into the concept of the basis of a comp space. So the first thing we need to then get is the comp space. So to get the basis of comp space, we need to get the CA first, which is the comp space of A. And what is a comp space of A? The comp space of A is the set of and the space of the vectors that we can see in here, in this A1 and A2. It's quite straightforward. So these two vectors, they form the comp space of this matrix A. So then the CA is simply this set of 1, 3, and then 2, 6 vectors. This is A1, this is A2. Now, we have just seen in the beginning, before even starting our calculations, that A1 and A2 are linearly dependent, because A2 can be written as 2 times A1. So one of these vectors can be written as a linear combination of the other one. This means that we got just a single linearly independent vectors. And why is this important? Because we have seen in the definition of the basis that for us to have a basis, we need to have a linearly independent vectors. So the basis of vector space, in this case a comp space, is a set of linearly independent vectors that need to span the entire vector space, in this case R2. So therefore, we need to look into the CA that we got in here and select one of these 2 vectors that can be considered as linearly independent. Let's say we pick 1, 3. Now we know that we can then write any vector in R2 as a linear combination of this vector 1, 3. So we can scale this vector 1, 3 and get a new vector in R2. Therefore, we are saying that the basis of comp space, space of A is then the set of 1, 3. Because 1, 3, so A1 is then linearly independent, and the span of A1 is R2. Now, when it comes to the basis of the entire R2, one thing that we can notice is that this A1, so 1, 3, it's not spanning the entire R2, because we cannot write any random vector in R2 as a linear combination of these 2. Therefore, we are saying that this is the basis of comp space, but we are not saying that this is the basis of R2. And the final element in this definition that I want you to focus on is that every vector in the space can be expressed as a unique linear combination of the basis vectors. So in here, we have looked into this idea of basis of a null space and the basis of comp space. And we saw that we are talking about specifically the null space and comp space. But when it comes to the entire space, for instance, the basis for R2, then the basis of comp space, for instance, is no longer helping us, because the basis of comp space, it consists of this vector 1, 3, and this 1, 3 alone is not satisfying the second criteria that says that this vector needs to span the entire vector space. Because this 1, 3 vector is a single vector, and this vector, it is not forming the entire R2. It's not the basis for R2. It's not spanning the entire R2. So given that the 1, 3 is not spanning the entire R2, because of that, we know that the 1, 3 is not, the set of 1, 3 is not the basis of R2. So this distinguishing of the basis of R2, basis of comp space, basis of null space is really important, because basis for R2, it means that we need to find set of linearly independent vectors that they together form the entire R2. They span the R2, which means any random vector that we can see in R2, we can represent as a linear combination of the vectors in this space. So in here, let me also prove that this 1, 3 alone is actually not forming the R2. It's not spanning the R2, which then concludes that it is not the basis of R2. And after this, I will then provide you an example where we have a set of vectors that span R2 and are linearly independent, which means that they are the basis of the entire R2. So first, I want to show you why this single vector 1, 3 is not the basis of R2. So being the basis of R2, we have the criteria that the vectors need to be linearly independent. So let me actually clear up some space here. So I want to see and find the basis of R2. First, I want to prove that this set, which is the basis of comp space, I want to prove that this is not the basis of R2. Then I will also, as part of the second part of this proof, look into the case when we do have vectors and this set of vectors, it forms the basis of R2. So the first criteria of the basis of R2 says that, let's call it 1.1, the first criteria says that this vector in this vector space, they need to be linearly independent. Well, that criteria is valid. Given that 1, 3 is linearly independent, this means that criteria 1 is satisfied. So whenever you got just one vector, this criteria is automatically satisfied. So then you have the 1.2, which says that we need to have this span of these vectors equal to R2. So is the span of 1, 3 the R2? Well, no. And how we can prove that? Because the idea is that any vector, including an example where I have, for instance, let's say 4 and 5, this vector, that I need to be able to find a scalar that will help me to create a linear combination, let's say C, linear combination using this vector 1, 3, which will then set this amount, this, to be equal to this, which means that I need to be able to write my random vector 4, 5 as a linear combination of this vector that forms my vector space. So let's see whether that is even possible. Well, here I got 4 and 5. If I do this multiplication in the right-hand side, I get C, and here I got 3C. Because C times 1 is C, and 3 times C is C. And this means that I have an equation 4 is equal to C, and 5 is equal to 3 times C. From this, I get that the C is equal to 4, and C is equal to 5 divided to 3. But that is impossible, because 4 is not equal to 5 divided to 3, which means that I'm proving in here, and I gotta prove that the any random chosen vector 4, 5 cannot be written as a linear combination of this vector that forms this space. Therefore, as random vector from R2 can't be written as linear combination of 1, 3 criteria 2 is not satisfied. Because for that, we had to say that the span of 1, 3 is equal to R2, which we saw that it's not the case. Because then we would have been able to represent this 4, 5 as a linear combination of this 1, 3 vector. Okay, so now we have proven that the 1, 3 is not forming the basis of R2. Let's now look into what then does form the basis of R2, an example of it. So we are familiar with the unit vectors E1 and E2 in the R2, which form the identity matrix I. And this is 1, 0, and this is 0, 1. Also 1, 0, 0, 1 in the form of a matrix. So in this example, we have a set consisting of E1 and E2, where this is this E1, this is the E2, and the set corresponding to this vector space is then 1, 0, and then 0, 1. And now I will be proving that this space, this vector space, does indeed equal to the basis of R2. So this is the basis of R2. So the first criteria of the basis is that these two vectors should be linearly independent. Now we can quickly remember from our previous theory that the two unit vectors 1, 0, 0, 1 are actually linearly independent. That's something that we have proven. And you can easily see it also from here. There is no way that you can find scalar C that you can multiply this vector with and get a vector 0 of 1. Because for that, for this 1 to become a 0, you need to multiply this with 0. But then 0 times 0 is not equal to 1, which means that there is no way that you can find a scalar c to multiply this e1 to get the e2. So let me write this down. E1 and E2 are linearly independent because there is no scalar c, which is a real number, such that c times e1 is equal to e2. So this means you can't write e2 as linear combination of e1 or vice versa. This means that e1 and e2 are linearly independent. And this satisfies our first criteria. So criteria 1 is satisfied. What we have also learned is that any vector in R2 can be actually written as a linear combination of a unit vectors that form that R2. In this case, 1, 0, and 0, 1. So let's assume that this random vector is C1, C2. So this is C vector. And what we want to prove is that we can always write this C in terms of a linear combination of these two vectors. And how can we do that? Well, let's say here we got a K1, which is a real number, and we multiply this by 1, 0, and then we add K2, and then here is 0, 1. So this is our E1, this is our E2. Can we do this? Well, what is this? This is equal to K1, 0 plus 0 K2. And what does this give us? Well, this means this amount, let me write it over, K1 times 1, 0, which is the E1, plus K2 times 0, 1, which is our second vector, E2. This is equal to K1, 0 plus 0, K2, and this is equal to K1, K2. So I got on one hand this vector C1, C2, which I want to write as a linear combination of K1, E1 plus K2, E2. If I take the K1 equal to C1 and K2 equal to C2, well then in that case I can prove, so this is basically equal to C1 and C2, which means if I take this K1 and K2 equal to C1 and C2 respectively, and those numbers are given, then I can represent this vector C as a linear combination of E1 and E2, which is what I had to prove in order to say that the span of 1, 0, which is the E1, and 0, 1, which is the E2, is equal to R2. Because any random vector that will be provided to me with an element C1 and C2, and those are just real numbers, can be written as a linear combination of these two vectors. This means that the span of these two vectors is equal to R2. And this is basically the second criteria, so criteria 2 satisfied. And if the criteria 1 and criteria 2 are both satisfied, it means that this vector space of 1, 0 and 0, 1, this is the basis of the entire R2. So let's now talk about the concept of projections. By definition, a projection of a vector A onto another vector B is the orthogonal projection of A along B. It's denoted by proch and then B underneath. Here we see the index and then A. So projection of A onto B. So here is the A and here is the B, and represents the component of A in the direction of B. So component of A in the direction of B. All right, so in order to properly understand this concept, the intuition of it, let's actually make use of the R2 space. So let's first start by picturing in our flat world the R2 coordinates, so the Cartesian coordinate system. So let's say here we got our y-axis, here we got our x-axis. So this is the x, this is the y. And here, of course, we need to keep in mind this is just an example. When it comes to the projections, we can always go beyond R2. But for keep it simple and truly understand these concepts and this intuition behind the projection, I want to simplify this and do the example in R2. So here, imagine that we got this line, and this is a line that goes through the center. Let's call this line B. So B is a line in R2. Let's say this is that line. And now imagine that we have this vector, which is part of this line. Let's say this is this line. And this line is the representing by, on this line we got this vector B, and this vector is basically part of that line, as you can see. This is the vector B on this line B. So we know from this concept of the line spanning the R2 and then vectors, we know that in this case, independent what is the magnitude of this vector, what is the direction of this vector, we can represent this line B by this linear combination based on this vector. So linear combination of this vector, which is in this case D set, then here we got some C, where C is a real number, multiplied by this vector B. Knowing that this C is just a real number. So let's make it actually green. So we can basically say that this entire line B can be represented as the set of these linear combinations of these vectors. So for instance, if this is 1 and we do the C is equal to 2, then we can get this part of, so we can get this vector. Otherwise, if C is equal to 3, we can get this vector. Or C is equal to 4, this vector. And then and so on, which means that we can always come up with a linear combination forming a part of this line. Therefore, we are saying that this line can be represented as all these linear combinations of this vector B, which is part of this line. And here, the C is just a scalar, so a number, which is a real number. So the C times vector B represents this entire line. So we will need this in a bit. But for now, imagine this line and part of this line, which is this vector B. So imagine then that we got yet another vector, which is, let's say, in here. Again, going from the center, but this time in this different direction. So in here, this is vector A. We call this vector an A. So you can see that this vector A is actually much longer than the vector B. And we see that vector A is not lying on the same line as B. So B is lying on the line B, and A is not lying on the line B. Now let's say we want to project this vector A onto this vector B, which means that we want to project this A in this direction. So we want to bring this vector A onto this line. Let me actually use a different color. And the word of the projection actually does make sense in here, as you might notice, because we are trying to cast the shadow of A onto this line of B. And how can we do that? We can only do that if we connect this vector A like this with this orthogonal line, let's say by using a different color of this. So with this perpendicular line, we then will be connecting the vector A to the line B, because we want to project our vector A onto this direction. So this perpendicular line that you see in here, that goes from vector A to the line B, where on line B we have the vector B. So here is the line line B, and this perpendicular line, it goes from A to line B, and on line B we have the vector B that is represented like this. Then the projection of A onto line B is this shadow vector that you see in here. And the word projection, or the name projection, actually does make sense, because we are projecting this vector A onto this line, and it creates this shadow. So we are casting this shadow on here. And this vector is what we are referring as projection of vector A onto line B. Notice that we don't say projection of A on vector B, but instead we are saying projection of A on the line B. Then another thing we can notice is that we are getting this projection of A on B, so this vector, by taking the vector A, so vector A, and subtracting from that projection of A on B. That is the formula for this vector that we refer as a perpendicular that goes from A to line B. So when drawing this perpendicular line from A to line B, we are referring this as A minus projection of AB, because you can see that this vector is simply this vector minus this vector. That is the mathematical expression for this perpendicular line. So how we can then find out what is this C that we got in here? Because we understand that to get this exact formula for the projection of A on the line B, we need to understand what is the scalar, specifically what value are we using to multiply this vector B to get to this point. So what is that C? What is C? What is C such that C times B is then equal to projection of A on the line B? Because we can have different sorts of linear combination of vector B on this line B. And in fact, B, this line B, is the set of all linear combinations of this vector B. And I want to know specifically what is the vector that we see in here. What is the shadow vector? Because this is the projection of A on the line B, what we see in here. Now, how can we do that? Well, let's first formally define on this specific case, what is the projection of A on this line B? So, projection of A on line B is some vector that is also on line B, where A minus projection of A on B is perpendicular or orthogonal to, this is basically the definition of the projection of A on line B under this specific example. So in this case, the way we can find this projection is by looking into this C. So this is what we are interested. This specific C times B vector. And knowing C and knowing B, we already know what B is. Knowing C, we can then describe this specific projection. So one thing that we can know is the condition under which we say two vectors are orthogonal. That's something that we already have learned as part of the previous lessons. So let's go ahead and find that amount. So now what we need to do is to calculate this value of C, because value of C calculation will then lead us to the exact vector that we are interested in, which is this projection. So our end goal is to find out what is this projection of A on B. This is what we want. And for that, we need to calculate this C because we already know the vector B. So let me quickly remove this part. Because here we will then do our calculation. So one thing that we need to make use of is this part when it says orthogonal. Because we know that if two vectors are orthogonal, then their dot product is equal to 0. So we know that this vector is orthogonal to this target vector, which means that we can say that the vector A and then minus projection of A on B multiplied with vector B, that this is equal to 0. This is something that we know by definition of orthogonality. Two vectors are orthogonal, it means that their dot product is then equal to 0. Now let's make use of that part. So this means that we need to describe this projection of A and B. We need to make use of the fact that we know that this projection of A onto B is actually some linear combination of vector B. So let me actually go ahead and remove this part. We already know the definition. So let us go ahead and calculate that C that we need in order to find out what is this entire projection. So few things that we need to clear out is those formulas, because then we can make use of them to find this C. So we know that by definition, the projection of A on the line B, it is this vector that we get when we draw this perpendicular line from vector A onto line B. And we said that this line is equal to this amount. This is simply the vector A minus this vector, the shadow vector, which we said it's defined by projection of A and B, this thing. So we can make use of that because we also see in here that this, we are saying, is orthogonal to this vector. So given that this vector A minus projection A, B is orthogonal to line B, then it's also orthogonal on this specific vector, which is the projection itself. So from this, we can make use of the fact that two vectors, when they are orthogonal, their dot product is equal to 0 in order to find this value of C. So firstly, we just said that the A minus projection of A on the line B, that this multiplied by this vector B is equal to 0, because those two lines, they should be perpendicular. But at the same time, we know that this is simply the linear combination of this vector, because this line is perpendicular to this one. And this line is some linear combination of this vector B. Because if I have here a vector and then I have the longer version of that vector on the same line, which is then a linear combination of this original vector, let's say this is my vector B, then this second vector that I have in here is then equal to some C times vector B. This is also exactly what we said in here. We said any vector on line B can be represented as a linear combination of vector B. And this is exactly what we are seeing in here. So this projection is simply that C times vector B. This is something that we have already said. So we are just making use of that to fill in that value. So this then results in A minus this C times B multiplied by this vector B is equal to 0 formula. So here we are simply making use of the fact that the projection of A onto B is the shadow vector, which is then equal to some linear combination of this original vector B, which is on this line B. Then I can easily find the scalar C from here, because we know how we can easily calculate this dot product. So let us actually go ahead and do that. Let's first multiply this A by B, and then minus, so I'm simply opening the parenthesis, C times, then I got B by B, and this is equal to 0. So C times B times B is then equal to A and B, which means that C is equal to A times B divided to B times B. Now, when we have the C, we can easily derive the formula for the projection of A on the line B. So, this is the first part. This is the second part. So then the projection of A on B, so projection of A on B is equal to this C times the B, and we just found out that this is equal to, the C was equal to A times B divided to B times B, and now we need to take this C and then multiply by vector B. This is then the projection of A on B. This vector. So, projection of A on line B. So, you will notice that this is the same that we just got. So, whether you compute the projection of A on the entire line B or projection of A on the specific vector B, as we are using the vector B as a source for drawing our line, this is the same as the projection of vector A on vector B. And this is the same formula as we see in here. So this is the projection formula that we have just found out. So projection of A onto B is given by this formula, A times B, so the dot product of the vector A and B divided to the dot product of the B with itself and multiplied with the vector B. And this is in here, this is something that we have calculated time and time again in our examples. So if we go back to our example, then here we can see that this is our vector B, this is our vector A, and we are saying if we take the vector A and we project it onto this vector B, then we can calculate this projection, which is in here, the formula for this entire vector, which we are calling projection of A on B, or projection of A on B. This can be found out, so the length of that vector we can find by using this formula. So the dot product of vector A and B divided to the dot product of B with itself and then multiplied with vector B. So again, a dot product. And this is, of course, something that we get as a vector. So this is a vector, something that is equal to this entire vector in here. This vector. So I know that this might look a bit messy because it contains many moving parts, but I wanted to provide this detailed explanation and this step-by-step process, even if it is a bit confusing and a bit messy in the beginning. because this helps us to understand what this formula is about and what is the intuition behind it. Because what we are doing is that we are making use of the fact that the line can be represented as a linear combination of all the vectors that we use in here. So this is vector B, and this entire line B is a linear combination of this vector B, and we can make use of that in order to find that scalar that we are multiplying to create this single linear combination that will end up giving us this vector that we see in here, which is the projection that we are interested, which is this line. This is the projection that we are defining by this projection A onto B. And we can get that by making use of the fact that this perpendicular line that we are creating in here, which is simply the vector A minus this projection, this is this vector, this projection vector, that this is perpendicular to this line B. And if the vector B is part of this line B, this means also that this line A minus projection A is also perpendicular to that vector, vector B. Making use of that formula, we can then make use of the product of the two. We know that the dot product of two perpendicular vectors is equal to 0. Making use of that, we can then obtain this specific scalar C that we need in order to get the final formula for our projection. We are interested in this C because knowing C, we can then multiply with this vector B to get our final projection. And we have found that that projection A on B is defined as the dot product of the A and B divided to the dot product of the B with the B and multiply with the vector B. And this is again a vector. Now let's look into a couple of numeric examples to clarify this topic and practice with it. So given vectors A and vectors B, find the projection of A onto B. So without looking into answer, I will quickly go on to that example itself. So vector A is this vector 3, 4. You can also represent this by our more common notation, which is 3 and 4. And then vector B is 1 and 0. So let's quickly draw our coordinate system. This is our x-axis, this is our y-axis. And then what is the A? The A is 3 and 4. 3 and 4. So this is our A. And what is the B? The B is 1 and 0. Which means that our line B is then C times the vector B, given that the C is a real number. And one thing that you can notice is that the line B is actually our x-axis. It is this line. This is our line B. This is our line B. So the projection is then this line. This is our projection because we can know that by drawing a perpendicular line in here from A to the line B, we can get then the connection between our vector A and vector B and create our projection. So this is then the A minus projection of A on line B. And this part is then, this projection A on B. And how we can get this projection? Well, we just learned that the projection of A on B is equal to dot product of A with B divided to dot product of B with B itself and multiplied by B. This is the formula that we can use, and even if you don't remember the formula by heart, you can make use of this visualization to figure out what that formula is. Because we know that if this line is perpendicular to this one, then A minus projection of A on B multiplied by this projection A on B should be equal to 0. And this projection of A on B is equal to some scalar C multiplied by vector B. That's something that we see in here. The first thing we need to do is to compute the dot product between A and B. A times B is equal to 3, 4 multiplied by 1, 0. This is the dot product, which is then equal to 3 times 1 plus 0 times 4. And this is equal to 3. The next thing we need to do is to compute the dot product between B itself. So B times B. And what's that? That is 1, 0 with 1, 0 multiplied. This is equal to 1. 1 times 1 plus 0 plus 0 times 0 is equal to 1. Then the third thing that we can do then is to obtain the final value, which is projection of A on B is then equal to 3 divided to 1 multiplied by the vector B, which is 1, 0, which is equal to 3, 0. And this actually makes sense visually too. As you can see in here, this is the 3 for the x-axis, and here we have the center 0. So this projection is then the vector 3, 0. So even without calculation, we could see just from plotting the on the coordinate system the vectors A and B that the projection of A on B will be this vector 3, 0. But we have followed the formula in order to do calculation step by step, which is something that you can see in this answer too. So the projection of this vector A onto B is then this vector of a length 3 in the direction of B. So you can see that it is of the length of 3. So this is the 3 on the direction of B, so on the line B. Let's now move ahead and look into a different example, but this time we will do the calculation in a quicker way. So we got two vectors, 4, 3, and B is equal to 2, 0. And we need to find this projection of A onto B. So the first thing we need to do is to calculate the A times B, which is equal to 4, 3 multiplied by 2, 0. And that's equal to 4 times 2 plus 3 times 0, and it's equal to 8. The second thing we need to calculate is the B dot product with B, which is equal to 2, 0, 2, 0. This is then equal to 4. And the final part is to take and from this 1 and 2 these values and then bring them all together. So then the projection of A on B is equal to 8 divided to 4 multiplied by the vector 2, 0. And this is equal to 8 divided to 4 is 2. 2 times 2 is 2. 2 times 0 is 0. So we are getting this 2, 0 vector. So projection of A on B is then this vector 2, 0, which is actually on this x-axis, similar to what we had before, only with the length of 2 on, towards the direction of B, which is then equal to 4 and 0. And this is again similar to what we had before, where we got the projection of A on B that end up on the x-axis, but now with a length of 4. So now our projection has the following vector, so the following magnitude and direction. So this is the step-by-step process that I just followed, if you want to do it a bit slowly. And this is the final result. So the interpretation of this projection is that this projection A onto B is simply this 4, 0. This means that the A's component in the direction of B it spans 4 units along this x-axis that we saw in here. Because this is the value x, this is the value of y. So this projection shows us that A's influence in the direction of B is completely horizontal with this magnitude of 4, because we saw that we end up with the projection on the x-axis again. So this was 4, this was our projection vector. And if you plot this entire vector A and vector B on this x-axis and y-axis, then you can clearly see that the horizontal line that we end up with, the projection of A and B, is very similar to what we had before in here. Let's now talk about the concept of orthonormal bases. So let's now define what the orthonormal bases are. So by definition, orthonormal basis for a vector space is a basis where all vectors are orthogonal or perpendicular to each other, and each vector is of unit length. So as you can notice here we have a special type of basis. It's called orthonormal basis, because in the beginning of this section of this module, we defined formally this concept of basis. We talked about the concept of calm space, and then the basis of a calm space, the null space, the basis of a null space, and then we talked about the concept of the basis of the entire space, for instance, the R2. And now we are defining a special type of basis, which we are referring as orthonormal basis. And this orthonormal basis, as you can see from this definition, it contains 2 criteria for it to be orthonormal. So an orthonormal basis for a vector space is a basis where A, all vectors are orthogonal or perpendicular to each other, and B, each vector is of unit length. We already have learned that when we have vectors, let's say vector A and B perpendicular, it means that A and B, their dot product is equal to 0. That's the first criteria that we need for calling our basis an orthonormal basis. Then the second criteria is that each of these vectors, they need to have a length of 1. If we have this condition satisfied, then we are saying that our vectors, they help us to form this orthonormal basis. If we got 3 vectors forming this vector space, it means that we need to have the A times B equal to 0, A times C equal to 0, and then B times C equal to 0. This is if we are in case we are using 3 different vectors that define our vector space. In this case, let me make this part smaller. So let's put the length of B in here. In this case, the second criteria becomes that the length of A is equal to the length of B, and then is equal to the length of C, and is equal to 1. So depending on the number of vectors that you use to form your vector space, the proof that you are dealing with orthonormal bases will be different. Here we got just 2 vectors, here we got 3 vectors. But in both cases, we first need to prove that we are dealing with vectors, each of which are a set of orthogonal perpendicular vectors, and all of them pairwise, they need to be perpendicular. And at the same time, the second criteria says that they all need to have a unit length. So their length should be equal to 1. We need this orthonormal basis in order to simplify our calculations, including the calculations of projections and transformations that we just saw before when we were discussing this concept of projecting a vector onto a line or projecting a vector onto another vector. Because we were in this basic case when we had just two vectors in R2, and calculating a projection in R2 is very easy because we can make use of this formula, A and then B, the dot product of them, and then divided to dot product of the B, and then times the B. This was quite straightforward, right? But when it came, so this is the projection of A on B. But when it comes to projection in higher dimensional space, let's say you have R5 or you have R100 or R1000, then it becomes much more difficult to do those projections and to calculate the projections. And for those cases, we can make use of this concept of orthonormal basis to simplify our calculations, and we will see that in a bit. So let's first understand this orthogonality and the normalization part. So orthogonality refers then to the part of when we are saying that the vectors should be orthogonal to each other, and the normalization refers to the fact that the length should be 1. This is basically the set of two criteria that I just discussed. This is the summary slide that will give you an indication what is meant by that. So if we have two vectors, V and W, then we say that the first criteria is that those two vectors are orthogonal, which means their dot product is equal to 0. And we are saying that their length is equal to 1, which we are referring as a normalized vector. So if the vector has a length of 1, then we are calling a vector V normalized. So if both of these criteria of normalization and orthogonality is satisfied, then we are saying that we are dealing with an orthonormal basis. So now when we have learned this idea of projections, also this idea of orthogonalization and the concept of orthonormal basis, we are ready to discuss the concept of the Gram-Schmidt process. So the Gram-Schmidt process is this method for orthogonalizing a set of vectors in an inner product space and turning them into an orthonormal set. So let's say we have a set of vectors. We want to bring and transform all these vectors onto this orthonormal set of vectors, which means that we want them to be orthogonalized, so we want them to be perpendicular, and we want them to be normalized because we know that these two criteria were specified, right? So the first criteria was that we need to have vectors orthogonal. Hence, we are doing orthogonalization. And the second criteria was that they need to be normalized because we want the vectors to have length 1. So we are doing normalization. This process of turning this set of vectors onto this orthonormal set by using this method of orthogonalization, which is something that we are referring as a Gram-Schmidt process, this is something that we can use in order to simplify later these different sorts of transformations which we need in order to perform a bit more advanced transformations like matrix factorization, different decomposition techniques. So given this set of linearly independent vectors, this process, which we are referring as Gram-Schmidt process, produces this orthonormal set that is spanning the same subspace. So we have the same subspace. It's just that we are turning the set of vectors into an orthonormal set of vectors that is spanning the same subspace. So the Gram-Schmidt process, step by step, looks like something like this. So given a vectors a1, a2 up to an, the first thing we need to do is to start with a vector v1, which is equal to our first vector a1. And first we need to normalize this vector. And how we can normalize this vector? Well, we need to take this vector and we need to divide it to its length. So the Gram-Schmidt process, step by step, will look like something like this. So in the first step, what we need to do when starting with these vectors of a1, a2 up to an, so in Rn, we need to first take the first vector and we need to normalize it. And how we can normalize the vector and ensure that its length is equal to this length of v1? Well, we need to take that vector and we need to divide it to this length. Because when we take the vector v1 and we divide it to its length of v1, then we will ensure that the length of that vector is equal to 1. We can actually prove that very easily, but I won't do it in here. Feel free to go through the process, assuming that the length of the vector, what you want to achieve at the end, is that the length of a vector v is equal to 1. This is something that we want to achieve. And this normalization process can be done if we find a way to ensure that we get this E1. Because E1 means that we end up with this vector 1, 0, 0, 0, 0. This will be for first vector, so v1. This is E1, so the 1 is really important here. So we want to normalize this vector v1 by ensuring that we get the E1. So we go from v1 to E1. And the way we do that is that we take the v1 and we divide it to the length of v1. And in this way we get the E1. So the normalized version of v1 is E1. So then for each subsequent vector ak, which means a2, a3, a4 up to an, we need to subtract its projection on all the previously computed orthogonal vectors. In this way, by using this step 2, we are ensuring that all these different, each pairwise set of a1, a2, and then a2, a3, etc., they are all orthogonal to each other. And we know that this projection is something that we got when we had these two perpendicular lines. So we had this vector, we're projecting onto this vector. We got that by finding this perpendicular line and making use of that. Using this property, we are then making use of that in order to see how we can ensure that the subsequent vector that we have is always perpendicular to this one. So let me actually write down what is in this formula. So here, vk is equal to ak minus the sum of all the projections. So then we need to normalize the vk to get the ek, and then we need to repeat this step 2 and 3 for all vectors, which means that first here we apply this normalization on the vector a1. So v1 is equal to a1, and then we get the normalization by getting this e1. So e1 is the normalized version. And then we need to apply a bit different tactic for our v2, v3 up to vn. And then let me actually write down this for this general case. So what this process is, the gram, let me ensure that I'm not making a typo, Schmidt process, step by step, means step number 1 for vectors a1, a2, a3, an. So we are in the Rn. Then step number 1 basically says take the V1 and set it equal to this first element, V1. This is A1. Then what we need to do is to normalize it to get the E1. So normalize V1 to get E1, which is equal to 1, 0, 0, 0, and then ... 0. And the size of this n by 1. And how we can do that? By taking this vector V1 and divided it to the length of V1, which basically means in this specific case, A1 divided to the length of A1. This will then give us our E1, this vector. This is basically what the step 1 entails. Then in the step number 2, we have for each subsequent AK, where K is just an index referring to whether we are dealing with K is equal to 2, so A2, A3, and then ... AN. This is what basically the K is used for, to refer to which vector we are dealing with. We need to subtract its projection on all previously computed orthogonal vectors by using this formula. So let's actually do a couple of those cases to see what is going on. For instance, for K is equal to 2. So K is equal to 2, and here is the formula, by the way. So VK is equal to AK minus sum. K is equal to, K starts with 1, and then let me use a different index. So I is equal to 1 till K minus 1, and then projection of AK on E1 or EI. So the EI that we have just computed, because every time you are then normalizing every time your vectors, and then you are finding out what is the projection of your vector A onto that EI, and then you are subtracting that from your vector. So what this means in practical terms, when for instance your K is equal to 2, it means that V2 is equal to A2 minus sum of I is equal to 1, and then K is equal to 2, K minus 1, this means this is 1, projection of A and then 2 on A1. Given that this is 1, this is simply equal to A2 minus projection of E1, that's normalized version of E1, and then A2. So projection of A2 on E1. And then in the step number 3, we need to go from VK to get EK. So basically we are ensuring with this step number 2 the orthogonality condition. And with step number 3, let me add some space in here. So in the step number 3, we are then saying let's normalize this VK. that we have just computed in here. Because we remember that the second criteria after orthogonality is normalization, that the unit or the length of the vector should be equal to 1. So then vk, in this case, for k is equal to 2, for k is equal to 2 means that we need to go from v2 to e2. And the way we can do that is by taking the v2 by v2 and then divide it to the length of v2. This will then give us the e2. This is the normalization part. And the step number 4 basically means repeat step 2 and 3 for all case. Which means that if we go back, so we are done with v2, so we have obtained v2, and then we have obtained a normalized version of v2 by getting this e2. We are ready to come back and do the same for k is equal to 3. And for k is equal to 3, in step number 2, we got v3 is equal to a3 minus, making use of this formula, sum over all I is equal to 1, k minus 1 is equal to 2, and then projection of this time a3, see, 3, k is equal to 3, and then on e2. Actually, it says ei. Let me remove this, otherwise we would have made a mistake. This should be I, because then I will change per k. This is the entire idea. We need to subtract all the projections. What this basically means is that we need to take a3, and this time, given that here we have 2 instead of 1 in here, we need to have an extra step, which means a3 minus, and then what this formula basically says, this is the sum of the projections of a3 on ei's, where i's goes from 1 till 2. So projection of a3 on e1 when k, so when I, this is the I is equal to 1 case, plus projection of a3 on e2, this is the I is equal to 2 case. This is basically what this summation says. This is this element. And we have seen this as part of the high school, but also the pre-algebra course. Okay, so now when we are clear on how we can calculate the v3 in the step number 2, for k is equal to 3, we are ready to go on to the step number 3. And what was step number 3? The step number 3 for k is equal to 3 was saying, let's take the v3 and normalize it to go from v3 to e3. And how we can do that? By taking the v3 and dividing it to the length of v3 to get onto e3. And this cycle goes on and on until we cover all the k's, so all the vectors. So the idea is that we first, for our initial step, we set the v1 equal to a1, we normalize it. Then starting from the k is equal to 2, we then go first on and on, we orthogonalize it. By formula in here, by using this, we can ensure that each of these vectors is then orthogonal to all the other vectors. So for k is equal to 2, we ensure that this vector that we get is orthogonal to all the other ones. And then for k is equal to 3, that the third vector is orthogonal to all the other ones. And we are doing that in step number 2. So for each k, we basically are ensuring that in this case, we have a vector that is orthogonal to all the other vectors in this set. And for each vector, we are also normalizing it to satisfy the second criteria, because we had these two criteria to create this orthonormal set. So we are doing this in a subsequent way. So first for k is equal to 1, so basically for a1, and then we are doing this for k is equal to 2, so a2, and then until k is equal to n, so an. What we are doing every time is that we are obtaining this v1, and then we go from v1 to e1 to normalize it, and then here we are getting the v2, here to go to e2 by normalizing it. So this is basically the step 2 and step 3, and then we do this every time up until to the point of obtaining vn, and then from vn we go to en to normalize it. So this is the idea of this entire process step by step, to start with v1 as part of the step number 1, and then as part of step number 2 for each subsequent vector ak, so k is equal to 2, obtain the vk and then normalize it. For k is equal to 3, obtain the v3 and then normalize it to get e3, up to the point of the last vector, which is an, the vector an. We compute the vn, and then we normalize it to get the en. And this is what this part is, which is the step number 2 that says repeat steps 2 and 3 for all vectors. It means that every time when you increase your k, when you go on to the next vector, we first compute the v, so vk, and then you normalize it to get the ek, and then you go back to the step number 2 and 3, because you then again need to calculate the vk and then ek, and then for the next case. So this is something that you will see also a lot when you are writing the pseudocode for your algorithms, because in many cases you need to do this repetition of the steps. So you, for one vector you do something, or for one iteration you do process, and then you go back and do for the next one and for the next one. This process is what we are referring by repeat step number 2 and 3 for all vectors. So let's now look into an example. Let's apply this Gram-Schmidt process to vectors a1 and a2, where a1 is 1, 1, 0 and a2 is 1, 0, 1. So let's go ahead and do that. So a1 is equal to 1, 1, 0. a2 is equal to 1, 0, 1. We want to apply this Gram-Schmidt process to create this orthonormal basis for the subspace that is spanned by a1 and a2. So now we have this set 1, 1, 0 and 1, 0, 1. And what we want is to create an orthonormal basis. So creating orthonormal basis with Gram-Schmidt process. So here we got only 2 vectors. So obviously it's this, and it's the very simplified version of it. What was the first step in our case, in our algorithm? It was to set the v1 equal to a1. What we need to do, step number 1, we need to set the v1 equal to a1. And we need to normalize the v1 to get e1. That's what our goal is. So let's go ahead and do that. v1 is equal to a1 and is equal to 1, 1, 0. That's our a1. So 1, 1, 0. And in order to normalize V1 and get the E1, we know that this is equal to V1 divided to the length of V1, which is then equal to, take the V1, so that is 1, 1, 0, and then divide it to the length of V1. And you can very quickly see that given V1 is equal to V1 times V1, that's something that we'll learn in the very beginning of our Fundamentals to Linear Algebra course, that the length of V1 is simply the dot product between V1 and V1, and it's equal to 1, 1, 0 times 1, 1, 0, which is equal to 1 plus 1, so 2. So this is then equal to 1, 1, 0 divided to 2, which is equal to 1 divided to 2, 1 divided to 2, and then 0. This is our E1. So we are done with our step number 1 because now we have V1 and we got E1. So what was the step number 2? In the step number 2, we need to set the k equal to 2. This is the next k, so for A2. What we need to do is we want to get V2 and normalize V2 by getting E2. And how can we get that? Well, first let's find what is the V2. Well, V2 was, and using that formula that we saw before, which was this formula, so it's equal to AK minus, and the sum, I is equal to 1 till k minus 1, and then projection of AK onto EI. So let's take this formula over. This is equal to A2, because k is equal to 2, AK minus sum, and then I is equal to 1 till k minus 1, and then k minus 1, which is equal to basically 1, given that k is equal to 2. And then projection of A2 onto EI. And this is equal to A2 minus, given that we got k minus 1 is equal to 1, so the limit for our summation is equal to 1. So this one. This means that like before, we got just one part as part of our summation. So minus, and then projection of, let me actually keep the same color. I want it to be consistent. So projection of A2 on the E1. So you see here the I is equal to 1, and the limit of the I is k minus 1, which is equal to 1. So we got here just E1. So we got the V2 formula. We can then now calculate it because we know A2. And the A2 is this, so 101, 101. But now we got a problem. We don't know what this is. So let's quickly go and calculate this part. So projection of A2 on A1, and we learned from the projection formula that this is equal to A2 times E1 divided to E1 times E1, so the dot product, multiplied by E1. And what is this? This is equal to 101 multiplied by, and what is the E1? E1 we just calculate in here, so it is 1 divided to 2, 1 divided to 2, and then 0 here, divided to, and then 1 divided to 2, 1 divided to 2, and then 0, multiplied by 1 divided to 2, 1 divided to 2, and then 0 here, multiplied by the same vector. So E1. So these two cancel out. These two also cancel out. And as you can see, we are getting that the projection of A2 on E1 is equal to this vector. We can also manually check that actually. So let's do that. So let's see, we are not canceling out these vectors. And instead we are manually calculating this. So here we got 1, 0, 1 multiplied by 0.5 and 0.50. This is equal to 1 times 1 divided to 2 is 1 divided to 2. 0 times 1 divided to 2 is 0. 1 times 0 is 1. So plus 1 divided 2. This amount is 1/4 plus 1/4. This multiplied by the vector 1 divided to 2, 1 divided to 2, and then 0 in here. This is equal to 1 divided to 1 plus 1 divided to 2 is equal to 3 divided to 2. And then 1/4 plus 1/4 is equal to 1 divided to 2. Multiplied by 1, 2, and then 1, 2, and then 0. What is this amount? Well, those two cancel out. So we end up with 3 times, and then 1 divided to 2, and then 1 divided to 2, and then 0. This is then the projection. 3 divided to 2, 3 divided to 2, and then 0. So let me remove all these calculations. And then we can take over the projection value, which is 3 divided to 2, 3 divided to 2, and then 0, to get our vector V2, which is equal to 1 minus 3 divided to 2, 0 minus 3 divided to 2, and then 1 minus 0. And this is equal to, here it is 1, here it is minus 3 divided to 2, and here it is minus, and then 1 divided to 2. Because 3 divided to 2 is minus, it is 1.5, and then 1 minus 1.5 is simply minus 0.5. So this is then the vector V2. Then what we need to do is to normalize this vector to get the E2, which is then equal to V2 divided to V2 length, which is simply equal to V2 divided to V2 times V2. So the dot product. And this is equal to, let's take the V2, which is minus 1 divided to 2, and then minus 3 divided to 2, and then 1, and then divided to, and this amount, let's quickly calculate that. It is equal to, so the length of V2 is equal to minus 1 divided to 2 squared plus minus 3 divided to 2 squared plus 1. This is equal to 1/4 plus 9 divided to 4 plus 1, which is 4 divided to 4. And then this is equal to 1 plus 9 is 10, 10 plus 4 is 14, so 14 divided to 4. This is the length of it. So 14 divided to 4. So then this is equal to this vector, to this 3-dimensional vector, minus 1 times 14, minus 1 divided to 2 times 14 divided to 4 is equal to, this is 7, So minus 7 divided to 4. And then minus 3 divided to 2. I think I just made a mistake here actually. So minus 1 divided to 2. So the first element, and then divided to 14 divided to 4 is actually equal to this multiplied by 4 divided to 14. So you take this element, then divide it to this one. And we know that A divided to B times C divided to D is equal to A times D and then B times C. So we are basically flipping this side. This is from pre-algebra. And then here, this is equal to two, and then is equal to minus 1 divided to 7. Then let's do the second one too. So we got minus 3 divided to 2 divided to 14 divided to 4 is actually equal to minus 3 divided to 2 times 4 divided to 14. And then if we remove this, this is then 2, this is 7. This cancel out. This is equal to minus 3 divided to 7. Minus 3 divided to 7. And then finally we got 1 divided to 14 divided to 4, which is equal to 4 divided to 14. This is equal to 2 divided to 7. So 2 divided to 7. And this is our A2. And given that we got just 2 vectors, so we have already reached the end of our solution. So now when we have already the V1 and the V2, the E1 and the E2, we have basically completed the process of this Gram-Schmidt procedure. Because we have already only 2 vectors, that means that we need to have V1 and V2 and then E1 and E2. And this is all that you need in case you got 2 vectors. If you have 3 vectors, of course, the process will include the same process of step number 2 and 3, so the V2 and the normalization of it 2 times for your case equal to 2 and case equal to 3. And then if you have more vectors, then every time you will have more of these steps. But at the end, what we want to have is this set of vectors that are orthogonal and at the same time they are normalized. In this case, we say that these vectors form this orthonormal basis. Now, why is this important, the applications of orthonormal basis? Well, firstly, it simplifies a complex vector operations. And this is the basis of many more difficult mathematical concepts like Fourier series or quantum mechanics. It's used also when it comes to this orthonormal basis, also signal processing, and it's a critical process in numerical methods, especially in machine learning algorithms and in data compression. So we will see this process to be used also as part of decomposition techniques, which is really important when it comes to different algorithms, whether it's optimization algorithms, but also algorithms that are used for recommender systems, for example. And those concepts, they all come together, and we will see later on when we will be discussing the concepts of decompositions and matrix factorization. So this orthonormal basis and this Gram-Schmidt process, they are really foundational in linear algebra. They provide the tools for simplifying and also solving these higher dimensional problems efficiently. Their application include different fields of science, engineering, demonstrating their versatility and utility. Let's now talk about the special matrices and their properties. So we are going to talk about special matrices like symmetric matrices and their example, diagonal matrices and their corresponding example, but also the orthogonal matrices with the corresponding example. So when it comes to the special matrices have unique properties such as being symmetric or all non-zero elements on the diagonal, like diagonal matrices, or orthogonality in matrices, which means that we have orthogonal matrices. So when it comes to the symmetric matrix, it means that the matrix A, is equal to its transpose, the AT. So A is equal to AT. In this case, we can confirm and say that the matrix A is symmetric. So in this case, we have matrix A, and we know that the way we need to transpose this matrix is to taking these rows and making them the columns of our transpose matrix. So AT is then equal to 2 minus 1 and then 0, then the second row, which is minus 1 and then 2 and then minus 1, and then the third row, which is 0, minus 1 and 2. So the third row then becomes my third column. So as you can see, those two are the same. So I'm using then the definition of the transpose of the matrix. And then here, then we end up with two matrices. They are actually the same. So we can see that the A and the AT, in both the first column, they got 2, minus 1, and then 0. The second column, minus 1, 2, and minus 1. The third column, 0, minus 1, and 2. So their columns and their rows, they are the same, which means that we are dealing with a symmetric matrix. So whenever we want to check whether the matrix is symmetric, we just need to take the transpose of it and see whether the matrix is equal to its transpose. In that case, we are dealing with symmetric matrix. Do also note that for matrix to be symmetric, it needs to be a square matrix. So it needs to be 2 by 2 in the 2-dimensional space, or 3 by 3 in the 3-dimensional space, or n by n in n-dimensional space, which means that the number of rows should be equal to number of columns. Because otherwise, when you flip your number of rows with number of columns, in case there is no square version of that matrix, so m is not equal to n, in that case, A will have a dimension of m by n, and then AT, so AT will have a dimension of n by m, which means that there is no way that A can be equal to AT. This is not then possible. Therefore, we need to have a square matrix for them to be symmetric. Let's now talk about diagonal matrix. So a diagonal matrix has a non-zero element only on its diagonal, which means that in this case, we have this non-zero element on the diagonal. So let's call it D11, D22, and then D33. This is equal to 3, this is equal to 5, this is equal to 7. And all the other elements, as you can see in here, they are zeros. So the concept of diagonal matrices is very simple. Therefore, we will then go through the next example, which is about orthogonal matrix. Now, this is a concept that we haven't yet seen and we've spoken about. So let's go through it a bit slowly. So an orthogonal matrix is a square matrix whose columns and rows are orthogonal unit vectors. So orthonormal vectors. And its transpose equals its inverse. So there are two parts of these elements. So firstly, it says that for the matrix to be orthogonal matrix, it should be a square matrix. So square matrix. And then its columns and rows are orthogonal unit vectors. So columns and rows are orthogonal unit vectors, which means they need to be normalized. So normalized. So we have seen when forming this orthonormal basis that we had this process of this condition of orthogonality. The vectors had to be orthogonal. and they had to have a length of 1, which means that they had to be normalized. We can see exactly the same in here. So hence the name orthonormal vectors. So they are orthogonal and they are unit vectors, which means they are normalized. So then the final condition is added in here, which actually is not so much a condition, but rather than a property, something that we can prove, that once we have all this, we can also say that if we are dealing with orthogonal matrix, then Q T times Q, so the dot product of the transpose with that matrix Q is equal to the Q times QT is equal to I. Why? Because the QT is equal to the Q minus 1. Because the transpose of that matrix Q is actually equal to its inverse. And given that we learned that the Q minus 1, so the inverse times Q is equal to Q inverse times Q is equal to I, and given that here we are learning that QT is equal to Q minus 1, we are then making use of this to claim this. So instead of minus 1s that we are used to when we are dealing with inverses, here we have T, the transpose. So in this case, this orthogonal matrix that we have just learned about, this is the square matrix whose columns and rows are orthogonal and they are also normalized, meaning that we are dealing with QT is equal to Q minus 1. It will look like this. So this Q1. You can see that here we got the first row, here we got the second row. And if we calculate the dot product between this row and this row, we can quickly see that we are getting a value of 0. So we can prove that they are actually orthogonal, those two rows. Let's go ahead and actually prove that. So let's call this R1, let's call this R2. This is row 1 and row 2. And I will leave the column version, so Q1 times Q2, that dot product on you to prove that the columns are perpendicular. I will work with the rows. So R1 times R2, for me to prove that they are orthogonal, I need to prove that this is equal to 0. Can we do that? Well, let's try. So 1 divided 2 square root of 2, 1 divided 2 square root of 2, multiplied by 1 divided 2 square root of 2, needs some bigger space in here. So 1 divided 2 square root of 2, and then minus 1 divided 2 square root of 2. That's how I can calculate the dot product between R1 and R2. So R2 and R1. You can see that the elements in here are the same, and here the elements are also the same. So then this is equal to 1 divided 2 square root of 2 times 1 divided 2 square root of 2 minus 1 divided 2 square root of 2 times 1 divided 2 square root of 2. I'm simply taking this minus, and given that the dot product is basically plus and then this amount, I'm just taking this and bringing up in here to avoid one more step, given the space is quite limited. Now, what do we see in here? This value is the same as this value, which means that this is equal to 0. And we know that the two vectors, to be orthogonal, they need to have a dot product equal to 0. So here we have proven that dot product of R1 and R2 is equal to 0. So this proves that R1 and R2, so the two rows of this matrix, so R1 and R2, are orthogonal. We can also prove that the second criteria of orthonormal vectors is also satisfied in here. We can prove that when we look at the length of this vector and of this one, then they are of the unit 1. So let's actually go ahead and do for one of them. So let's prove that for 1 divided to square root of 2 and then 1 divided to square root of 2, this is a vector, that the length of it, this is, let's say, our first row, so this is R1, then the R1 length is equal to 1 divided to square root of 2 squared plus 1 divided to square root of 2 squared. This is equal to 1 divided to 2 plus 1 divided to 2. And what is 1 divided to 2 plus 1 divided to 2? It's equal to 1. So we have proven that the length of R1 is equal to 1. You can quickly and easily also compute that for the second row, and you will then also prove that the R2, the length of it, is also 1, which is then the second criteria, which said that for the vectors to form this orthonormal basis, so to be orthonormal vectors, they also had to have a length of 1, so they had to be a unit vectors. In this case, then we can make use of the property that the Q2 transpose is equal to Q inverse. And this then results in Q2 transpose times Q2, which is equal to Q2 times Q2 transpose, which is equal to the identity matrix, and specifically I2, because we are in the R2. So both this Q2 and the previous example, those are orthogonal matrices. And in here, we have proven that the rows are indeed orthogonal, and we have also seen that the length of them are unit vectors, meaning that we have automatically got this. I will leave this one to you to do those proofs, so to ensure that the row 1 and row 2 are orthogonal, so they are perpendicular, which means they're the product of their, the dot product of these two vectors is equal to 0, and also that they are normalized, which means the length of them is equal to 1, and this means that then this holds. You can actually even go ahead and practice the material that we learned as part of the previous units by calculating the inverse of this matrix and checking that the inverse of this matrix is indeed equal to the transpose of the matrix, so that Qt is equal to Q minus 1, because we learned how we can compute the inverse of a matrix, because the inverse of a matrix was equal to 1 divided the determinant of this matrix times, and then a manipulated version of it, which was, in this case, 0, 0, and then we need to have here 1, so minus 1 times 1, and then 1 times minus 1, so we have to multiply this and this by minus, so 1, and then here minus 1. So in this way, you can also prove that this inverse is actually equal to the Q2 transpose, because then you can prove that indeed, and you can see for yourself, that this formula is indeed actually equal to the Q2 transpose, because then you can prove that indeed, and you can see for yourself, that this formula is indeed true. In this module, we are going to talk about matrix factorization. We are going to discuss the significance of matrix factorization. We are going to define matrix factorization. We are going also to discuss the common applications of matrix factorization across different fields, and then we are going to see detailed examples of matrix factorization. So, let's talk about why matrix factorization matters. So, matrix factorization techniques, they are essential for various reasons. They are used for simplifying matrix operations, like solving linear systems, or when we have this many matrices, but we want to simplify these operations that we apply to these matrices, and we want to solve the problem, then we can make this complex matrix operations more manageable and make these calculations more manageable by using matrix factorization techniques. We can also use matrix factorization directly to solve system of linear equations efficiently. We can also use matrix factorization to perform eigenvalue decomposition, singular value decomposition, or called SVD, and other operations which are crucial in machine learning and data analysis. So, eigenvalues and eigenvectors, you might have heard already, they are part of also PCA, which is the principal component analysis, and this comes from fundamentals of statistics. And the PCA is used as a dimensionality technique, and in fact, it's one of the most popular dimensionality techniques that you will find in the industry, used in the data science, used in data analytics, machine learning, even in the deep learning. So, matrix factorization can also be used to reduce the computational complexity. By making use of this factorization, we can then simplify the process and also make it more efficient for computation. And it's especially important when we are dealing with this high-dimensional data, when we have many features or we have a very large model and complex model, then this matrix factorization technique can make a huge difference in our data processing process. So these techniques underpin many algorithms in numeric analysis, in optimizations, and beyond. So whenever it comes to machine learning or data science or many other fields, you will see this process and this term matrix factorization appearing a lot. Even in the example of a streaming company, Netflix, which I'm sure that you are aware of, Netflix is using matrix factorization to build a recommender system. And matrix factorization usage in building recommender algorithm for personalized recommendations is actually one of the most popular applications of matrix factorization. Therefore, I wanted to specifically discuss this topic as part of our advanced linear algebra course, and some of the concepts might seem a bit more complex than the ones that we have discussed as part of the previous units, but once we go through them step by step, and I will give you all the details and all these examples, this entire process of these different matrix factorization techniques should become much more clear and straightforward. So we will be discussing not just one, but multiple fundamental matrix factorization techniques, beside of talking the high level where they are used and how you can choose for what type of applications. So we are going to demystify this entire concept of matrix factorization, and we are going to start from high level, then we are going to go into the deepest details. Let's now formally define the matrix factorization. So, matrix factorization refers to decomposing a matrix into a product of two or more matrices, revealing its structure and simplifying further analysis. So, what is this idea behind matrix factorization? The idea is that if we have a matrix A, and we want to simplify our process of calculation or multiplication, anything that's related to this A, but this A in itself, it contains this weird numbers, or it is just too complex, it contains this ton of different numbers. You don't recognize whether the columns are linearly independent. It's not very readable from the first view, and you just want to make your life easier when performing this calculation. Well, for that, you can make use of this matrix factorization to write this A in terms of some other matrices, let's say, and I'm calling here randomly Q or T. So it's equal to, for instance, the dot product of these two matrices, Q times T, where Q is much simpler and the T is also much simpler. So those may contain vectors that are, for instance, this can be a diagonal matrix, or it can be a matrix with specific properties. When using those, you will feel much more comfortable. So it will be easier for you to use them in order to multiply with other matrices. It can be easier for you to solve this problem. But of course, if you are in the two-dimensional space, let's say you are in R2 or in R3, then most likely it will be quite straightforward for you to use the A itself. But if you are in the R100 or R1000, then of course this entire computations, they become super complex. It will be difficult to understand and compute these linear combinations, find out whether you are dealing with linearly independent columns, find out the null space, the column space, the basis of the null space and column space. And all this, they might seem much more difficult when you are in high-dimensional space. For in those cases, we can then make use of matrix factorization to make the entire process much more simplified and also more efficient, this entire calculation process. So common types of matrix factorization include lower upper matrix factorization, or in short, LU, QR factorization, an infamous type of factorization, which is called orthogonal triangular factorization. And then we have SVD, singular value decomposition, yet another infamous matrix factorization. And then finally, the eigen decomposition, also another super popular matrix factorization technique. So the QR, SVD, and eigen decomposition are in fact highly popular decomposition and matrix factorization techniques that you will see appearing in the 90% of all the statistics-related and machine learning-related books. So this just comes to prove how important these concepts are when it comes to properly learning and mastering these more applied science-related fields like machine learning. So if you want to go beyond the level of knowing algorithms, but rather than to also be able to edit the algorithms, tweak them, adjust them, be able to understand machine learning algorithms, deep learning algorithms, data science at its core, and in order to become a professional, well-rounded professional, then this eigen decomposition, the singular value decomposition, and the QR matrix factorization techniques are techniques that you want to know and you want to understand at least high level, such that you can easier grasp more advanced concepts that come from the applied sciences like machine learning and AI. So let's first discuss at high level what this QR decomposition is. So what the QR decomposition does is that it decomposes a matrix into an orthogonal matrix, which we are referring by Q, and then an upper triangular matrix R. So in here, you can see that we have these two different matrices. So we are basically saying A is equal to this product of this matrix Q and R, where the first one, this matrix Q, this one should be orthogonal matrix. So this part is really important. And we have learned as part of the previous module the definition of orthogonal matrix. We learned that the rows or columns, they had to be orthogonal to each other. And we also learned that they need to have a length of 1. They need to be normalized. And we learned that this means that the transpose of those matrices is equal to the inverse of these matrices. So this was just the last part of the previous module. And this is exactly what this matrix Q is about. So we are saying that we will decompose I into these two matrices as a product of these two matrices Q and R, one of which, this matrix Q, should be an orthogonal matrix, which means the rows and the columns, they should be orthogonal to each other. So their dot product, each of them, should be equal to 0, and they need to be normalized. So the length of them should be 1 for each of those rows and vectors. And then the second part of this decomposition is this matrix R, which says that the matrix R should be an upper triangular matrix. And what is the definition of upper triangular? Well, in this case, you can think of this R as this matrix where we have here all zeros. And then here on the diagonal, you have numbers, non-zero numbers. And then here, let's say 1, 2, 3, 4, 5. And then here in the upper part, you will also have numbers. So unlike in the lower part of this matrix R, where you will have zeros, in here, you will have also non-zero numbers. Let's say 7, 10, 8. And I'm just writing these numbers randomly. So, of course, in the real case, when we have this matrix A, and we go through this process of QR decomposition, of course, we will have an appropriate Q and an appropriate R where these numbers will be different, and they will be specific numbers that we will be calculating. But the idea is that we need to get this upper triangular matrix R for this calculation to make sense. So we will then be using this QR decomposition for solving linear least squares problems, for instance, which is part of the linear regression too, because linear regression from machine learning and from statistics, it is based on the least square technique. The estimation technique that we are using for linear regression in machine learning to solve this linear regression problem is called ordinary least squares. So the algorithm is based on this idea of least squares, which is trying to minimize the squared residuals of the model. And that can be done by using this idea of QR decomposition. So it helps us to provide numerically stable solutions for this type of problems too. And QR decomposition is used extensively in signal processing and statistical analysis. Let's now briefly talk about the LU decomposition. So LU decomposition decomposes a matrix into a lower triangular matrix. So this is the opposite of what we had before. We can have an upper triangular matrix like we had in the QR decomposition. We can also have a lower triangular matrix. So you might have already guessed how it will look like. I won't go into that. Very soon in the QR decomposition example, you will see the idea of the upper triangular. I will also show the idea of a lower triangular. So the composition in case of LU is done by decomposing a matrix into a lower triangular matrix L and an upper triangular matrix U. So basically, the difference between the QR decomposition and LU decomposition is that in the QR decomposition, we are decomposing a matrix into orthogonal matrix and an upper triangular matrix, while in case of LU decomposition, we are decomposing a matrix into a lower triangular matrix and an upper triangular matrix. So here you can see that we no longer have this idea of orthogonal matrix, but instead of that, we are talking about lower triangular matrix. So in that aspect, LU decomposition is different from QR decomposition. So what the LU decomposition does is that it facilitates the solving of linear equations and matrix inversions. It is common in engineering and in physical sciences for systems of this linear equation to be solved by using LU decomposition. And in fact, if you are learning quantum mechanics, that this LU decomposition can definitely help you to better understand many concepts. But if your target fields are machine learning, deep learning, or artificial intelligence, then for those, using QR decomposition will be much more often a case than using this LU decomposition. Let's now talk about the singular value decomposition. So what the SVD does is that it decomposes a matrix into three matrices. So first one is the orthogonal matrix U. The second one is a diagonal matrix. And then the third one is this V star, which is the conjugate transpose of an orthogonal matrix. So for now, this might seem a bit complex, and you can see that unlike the QR or LU decomposition, where we got just two matrices as a result of our decomposition, in case of SVD, we got three matrices, like the name suggests too, by the way. So three parts. And this might seem a bit complex, but we are going to go through this process step by step, and I'm going to provide you detailed examples such that this will all make sense. But for now, let's focus at the high-level usage of SVD. So singular value decomposition is one of the most popular decomposition techniques, and it is also directly used as part of machine learning algorithms to form those machine learning algorithms. It is also used in the data compression, in the noise reduction. So when we are trying to clean our data and remove the noise by using SVD, because SVD can help us to identify those outliers and then remove them from the data by performing noise reduction. And it is also used in the principal component analysis, the PCA. The same dimensionality reduction technique that I just mentioned related to the eigendecomposition, because SVD and the eigendecomposition are highly related to each other. So this SVD is used as part of this PCA algorithm, and PCA is the most popular, the infamous dimensionality reduction technique that is used both in the advanced statistical studies, in the statistics in general, also in finance, and is also used as part of many machine learning and deep learning applications. So knowing PCA is a must if you want to get into data analytics or data science, machine learning, and AI. But also, it will help you also to understand many other concepts when it comes to these fields. So the SVD provides insights into the structure, but also the rank of the matrix. So we are going to see this as part of our example too. Let's now also briefly talk about the eigendecomposition. So eigendecomposition, which is highly related to these concepts of eigenvalues and eigenvectors, it decomposes a matrix into these eigenvalues and eigenvectors, which then shows the matrix's fundamental properties, which are related to this idea of correlation. What kind of information does this matrix contain? What is the variation? In what direction is the variation the largest? And this eigendecomposition, which is then related to also this idea of SVD and in general these dimensions and correlations, is critical for understanding linear transformations, the stability analysis, and systems of differential equations. But beside this mathematical side of concepts and understanding these mathematical topics, the eigendecomposition is also the basis for many algorithms in numerical linear algebra, but also many applied linear algebra topics, like in the data science, in machine learning, and is used heavily in artificial intelligence for feature extraction, for dimensionality reduction, related again to the concept of PCA, because PCA is based entirely on this concept of eigendecomposition. PCA is the direct result of computing the eigenvalues and eigenvectors. So without knowing what are the eigenvalues and eigenvectors, you cannot perform PCA, because the first step of the PCA is the computation of the eigenvalues and eigenvectors. And then using different rules, which we are referring as the elbow rule or Kaiser rule, we can then use these eigenvalues and eigenvectors to understand what are the features in our data that contain the most variation, so the most information, and then we can use that in order to understand what are the most important features in our data and reduce the dimension of our model by selecting these most important features. Because what PCA basically does is that it uses these eigenvalues and eigenvectors to understand how we can create a linear combination out of our features and understand the amount of those linear combinations that contain the most variation, and then select those and select the largest amount of information in the data, and then skip and drop those uninformative linear combinations while still keeping the most information. And this definition of the most will then be decided by these different rules. This is just high-level insights, background information on what you can expect when you are talking about applying this highly technical linear algebra concept of eigendecomposition into an applied science field like data science or machine learning or AI. But we will see this later, and I'll also make comments regarding this. And though PCA won't be discussed as part of this course, because here we are talking about linear algebra. But PCA is part of the Fundamentals to Statistics course, and in there we are no longer providing all these different details on how you can perform this eigendecomposition. Therefore, knowing how to perform eigendecomposition will then set you for success to actually understand the mathematics behind the statistical concepts like PCA, and also later on understand how you can use that PCA in the machine learning concepts and in AI concepts like autoencoders, and how you can relate your autoencoders to this concept of PCA, how they are related, what are their commonalities, and what are their differences. So everything is about the choice and choosing the right tool for your problem. When it comes to the decomposition tools, matrix factorization tools, we have seen that there are many options, and the question is, which one should we pick in what cases? So choosing the right tool is really important when it comes to these different matrix factorization techniques, because there are many choices, and each of them, they can be used for different sorts of problems. So therefore, in order to understand which one you need to pick in what kind of cases, what kind of requirements you have, and what kind of problem you are trying to solve, that in those cases, you will need to have this knowledge that you will learn as part of this course in order to make that right choice of the tool. So the choice among QR decomposition, the LU decomposition, the SVD, and eigendecomposition, it really depends on your specific problem's requirements and the data characteristics. So are you dealing with a complex data? Are you dealing with a simple data with low dimensions? What is the goal that you want to achieve? What is the problem that you are trying to solve? Is it to reduce the dimension of your feature space? Is it to solve a problem with linear equations? Is it to solve a quantum mechanics problem? Or is it to incorporate this as part of your machine learning algorithm? So QR and LU decompositions are usually preferred for solving linear systems, while SVD and eigendecompositions, they help us for deeper insights when it comes to the data and what kind of information it contains, how we can reduce the dimension of the data, or how we can use it as part of machine learning algorithm for noise reduction, identifying outliers, etc. So this type of algorithms like SVD and eigendecomposition, it helps us to also intuitively, using geometry and our knowledge of geometry, to visualize the data. For instance, the PCA helps us to visualize this high-dimensional data using just a couple of principal components. Let's say we have 10 features in our model, so we have a dimension of 10. We are in R10. But we want to visualize our data. By using PCA, we can then reduce the dimension and come up with 3 principal components, which are a linear combination of our original 10 vectors. And then we can use these 3 principal components to visualize our data in 3D. And this basically helps us to geometrically visualize our data and then make presentations, make much more sense of our story, so to do storytelling for our data, and much more. And these 2 models and tools, they are invaluable when it comes to applications in machine learning, in deep learning, in data science, and artificial intelligence. So matrix factorization techniques, they are super important when it comes to computational mathematics. They are also directly affecting the data science, AI, and many other algorithms. So they are not only important in terms of the problem that they are trying to solve, but also in order to make the computation process, so when coding in Python or in other programming languages, to make that process much more efficient. They also help us to make these computations efficient and provide insights into different properties that we have in our data. As part of this course, we are not only going to discuss 1, but actually 3 of these 4 decomposition techniques and these matrix factorization techniques in detail. We are going to talk about the QR decomposition. We are going to not just discuss it, but also to learn it step by step and we are going to do a detailed example with all the steps involved such that you will feel confident doing a QR decomposition all by yourself. Then we are also going to do an SVD decomposition as well as eigen decomposition, and then we are again going to discuss them in terms of their mathematical formulation, the definition, but also the application, step-by-step process, and a detailed example such that you can conduct each of those matrix factorization techniques and these decomposition techniques by yourself, manually doing all these calculations. This understanding and these examples and these concepts will help you to not just be able to formulate what these techniques are about, but really and truly understand and then use them later on, whether when doing your own research, writing scientific papers, or tweaking the algorithm all by yourself when inventing new algorithms. I won't be discussing this LU decomposition technique because we already know that the QR and LU, they are both used for similar type of problems. Therefore, to save us time, I have selected carefully the most important decomposition techniques and matrix factorization techniques that you will most likely be dealing with in your future career in applied sciences.